Okay, so I think we should start. So my name is Céline Fiorini. Welcome to this first scientific symposium of PEPR LUMA. We are very happy to be here at Sorbonne. We would like to thank deeply Sorbonne for its hospitality, and more particularly Anna for all her help during the preparation of these days. So I will give the floor to Mrs. Elisabeth Angel Perez, who is Vice President of Sorbonne.
Thank you very much and welcome to you all. It's a very great honor and pleasure to be here and to welcome you to Sorbonne University. It's great to know the vast community that you represent, so it's fantastic for these first annual days. First annual days of the PEPR LUMA, Light and Matter, in my best French priority research program and equipment and light matter interaction. So thank you, Céline. Thank you, Rémi, for organizing this magnificent event. Thanks to Anna and I suppose Stéphane Lechrome, who should have been in the circle as well. LUMA, as you probably all know, but perhaps some of you have come from other parts of Sorbonne University or other parts of French laboratories in Paris, but probably you do know, LUMA is a flagship exploratory research program supported by France 2030, co-led or co-operated by the CEA and the CNRS, and bringing together what I would call a vibrant community, vibrant national community of over 1,000 researchers. So we're very proud at Sorbonne University to be part of this, to be one of its partner institutions, alongside Aix-Marseille, Bordeaux, Lyon 1, Lille, and Strasbourg. This program embodies a collective ambition to explore, understand, and harness light as a tool to investigate and transform matter. I'm myself a specialist of theatre, and I know nothing about the chemical nature of light, but I do know about its transformative power. So it does that across physics, chemistry, biology, material science, and beyond. It builds on France's long-standing leadership in light-matter interaction, a field which is recognized by quite a number of Nobel Prizes, the most recent of which was awarded to Swedish-French Anne Lhuillier, who gained her PhD here, her alma mater, I would say, and who has been collaborating for many years with the LCPMR, the Laboratory of Physics of Matter and Radiation. LUMA's strength lies in its interdisciplinarity. And as such, it's perfectly in line with with Sorbonne University major scientific strategy, a strategy which is about promoting groundbreaking research at the heart, but also at the interface of disciplines. Its three scientific challenges, smart photoscience, photons for green technologies, and light for protection, address key societal issues from renewable energy to health, from environmental sustainability to the preservation of heritage. And we have just launched a program called Sphinx, which is about precisely the preservation of cultural heritage, material and immaterial, but material as a matter of fact, in which would be a partner of collaboration as a matter of fact. As a university committed to interdisciplinarity and societal impact, Sorbonne University is fully engaged in LUMA. You have our support. Our laboratories contribute to several major projects, and we are also deeply involved in the network of distributed platforms that make LUMA unique among the PEPRs, and it's quite something that has to be foregrounded, the open access to a certain extent of a wide range of platforms. These annual days are not only a scientific gathering, they are an opportunity to strengthen and to invigorate our community, to share ideas, to launch collaborations, and collectively to shape the future of light matter science. So we're thrilled to host this event. Thank you to all of you. Thank you to the organizers, but thank you to all of you for your presence, for your dedication, for your contributions. Special thanks to the keynote speakers coming from farther away, maybe, with fascinating talks and approaches. So I wish you very, very fruitful and inspiring days. Make the most of it, and thank you for your attention.
Thank you very much. So maybe I don't miss. Oui, merci. Okay, so if I'm. We will now begin with the introduction. So before beginning and telling you more about LUMA together with Rémi, I would like to present all the governing board of LUMA. So I don't know if they are here. Yes, please. So our two program managers, Sarah, can you come here? And Lorraine. And our communication lady, Mathilde, who is behind. So this is thanks to all of them that we were able to organize this day. So thanks a lot. And if you, in case you have any question, so please do not hesitate to go and see Sarah, Lorraine, or Mathilde behind you. So PEPR LUMA, it was also already a little said during the previous talk. LUMA stands for lumière and matière, and as you know, light is around us for everyday life, but also in science, light plays a big role, not only for characterizing matter, but also for shaping the property of matters. So the ambition of LUMA was to develop, to go between two axes. First axis is try to develop new sources, mainly attosecond sources. Try to develop new types of light, for example, so-called chiral light, so beam with angular momentum. So this is one big part of our activities. And on the other way around, the idea was to develop new photoactive materials. So, for example, it can be molecules, it can be assemblies of molecules, supramolecular assembly, it can be nanoparticles, and it can be hybrid system. And all this, in fact, has the objective to bridge different domains, scientific domains, from physics to biology, going through chemistry. So LUMA was launched last year in Bordeaux. This is the budget is about 40 million euros, which was distributed into different projects that will be presented today. But also the budget is also used for the access of different platforms. Rémi will tell more about this. So altogether, this is about 400 people. 26 institutions, university, and so on. And so the idea is to really promote interdisciplinary science and to structure all the scientific communities that know each other, but sometimes that would gain in discussing much more with each other. So LUMA is organized around 4 thematic axes, which are summarized here, and that you can see on the kakemono over there. So chirality, photochemistry and materials, energy and environment, and health. In order to have a taste of all these different topics, we are very proud to have 4 keynote speakers today with us. So Professor Leif Hammarström, who will speak about, give some kind of context about artificial photosynthesis. We will also welcome Marina Klimova, speaking about light for diagnostic in biology for imaging. And the third talk will be given by Majed Chergi from EPFL, speaking about ultrafast spectroscopy. So this will give you somehow the international context of all the axes of LUMA. And then this will be completed by 4 so-called highlights from people that are within the project funded by LUMA. So you will have a talk from Cyriac Genet about optical twist and chiral system, regarding chirality, a talk from Anne-Sophie Duval regarding photodynamic therapy in link with a moonshot related to the topic 4, which is health. Stefan Acke, we will speak about ultrafast spectroscopy in link with the topic number 2, photochemistry and materials. And then, no, I missed, in link with chirality. And the last talk will be given by Olivier Sopera about plasmonic chemistry. So, and you will also have some highlights of the so-called moonshot of each of these different topics.
Thank you, Céline. Thank you, all of you, actually, for being here and joining these first annual days of PEPR LUMA. I will just tell a few words now about the infrastructures included and provided by the PEPR LUMA. You probably know already quite a lot because we communicated a lot about these infrastructures, but still we can tell a few words now. We have, because it is the second main body of the PEPR LUMA. One main body is what Céline explained, these thematic research activities. The second main body is about these infrastructures. One first is called ultrafast, and it brings together some techniques and some instrumentation related to spectroscopy, pump probe spectroscopy, time-resolved spectroscopy, from the very, very ultra-fast scales, attoseconds, to more longer scales, which are very useful for many topics, microseconds, milliseconds, and in between, of course, we have the very interesting time scales about the femtosecond instrumentation. It also involves other kind of instruments and platforms about nano fabrication, optical lithography, and so on. Second part is called operando prototyping. And this one is, I mean, you have probably more diversity of instruments related to in situ characterization under illumination, such as NMR, EPR, and others. And also testing possibilities of devices under operation up to larger prototypes, especially in the field of photoelectrocatalysis and so on. I will not tell more because today we have 2 spots, highlight spots about the platforms and infrastructures. One at noon about the operando platforms, and the second at 3:30 p.m. on the ultrafast. And maybe even most importantly are the posters that you will see in the hall. All these posters are there such that you can meet the staff, technical, scientific staff of the platforms who are there to introduce their instrumentation and so to the possible users. So it is the good time to discuss together, see if there is some interesting experiments to be done with your samples and with your instruments. Practically speaking, we built an infrastructures hub, so it is a portal. It gathers the national network of these 26 platforms on operando on one side, ultrafast on the other side. It is, and this is maybe the key word of today, it is open to everyone, not only those who have been already funded by projects and everything. So everyone in the scientific community, whatever the discipline, of course, the national scientific community in academia, but then it's open to everyone, and it is covered by LUMA. It means that it includes, of course, the support from the platforms, from the staff, scientific, technical staff. But LUMA also covers the operating costs, the mission, I mean the accommodation and travel for the users who want to go to the platforms to do the experiments. So it is really open and fully covered. In the, practically speaking, for this application process, it's an open call. You can apply anytime. You have to fill a project, a form and a project in a few pages about what you want to do on this platform. And it will be evaluated by external reviewers. And if granted, then you have a number of days to do your experiments on the platform. This will be much more explained at these 2 spots on platforms today, and you can discuss in the hall. Céline.
Okay, so as said by Rémi, all these platforms are really rich environment. And our idea when discussing was, well, making an experiment on a platform is sometimes not so easy. You need to prepare things, you need to check and make few experiments before. So our idea was to launch a new call enabling, towards mainly young scientists, and enabling to get some money to prepare all these future platform experiments. So the idea is to give something like 10 kilo euros, it can be to pay a training period, it can be to buy few, small equipment and so on, so that you can be prepared to go on a platform, and in between you can already speak to the different people of the platform to know exactly what the platform can help, in which sense the platform can help you, and what you have to do to really get the best of the platform when going there. So this call is open right now. Like the access to the platform, you can do it you can make your demand whenever you want. There will be a first deadline on November 20. At this deadline, we will have a look on all the project, and we will select some of them. It will depend of the number, of course. And there will be a second deadline in April next year. So the idea is to make something simple. So this is only one, few details to fill on a form, and a small document to explain what you have in mind, what you will do, what will be your expenses. This will be like for I would say, regular access to the platform. This will be evaluated by external scientists, and we hope to do that quite rapidly so that you can access to the platform within the 6 months of your demand. You can scan the QR code here, and you will have more detail on our website. Just a few words about other ongoing action. Once again, towards young researchers, the idea was to help young researchers to develop their own networks, so not only nationally, but also internationally. So you can ask for grants to go in a lab, mostly, for example, in Europe, to make some complementary experiments. Here again, I think you can apply whenever you want, with a deadline on November 20. And the expenses that can be covered are around 5 kilo euros. Next ongoing action regards symposium, scientific workshop. The idea is to help you promote the science that is done within LUMA, so we can help you at different levels. Can be financially, it can be also to make some communication, to help you in organizing the session. What we ask you is to come to us 6 months before the event you want to organize. And the last new action, which we would like to speak about today, is the so-called Club Jeune, so mainly for non-permanent people, PhD students, postdocs. Once again, the idea would be that you, in fact, take action with us, trying to help us to organize some symposium, develop some interaction with international labs, and so on. So you will know more about this club, I think, on our website. And also, we will speak more about this tomorrow. So if some people are interested, once again, do not hesitate to come to us and we can discuss what we can organize. This is something that we really launched today. So we need ideas, we need also people motivated. And I will give the floor to Rémi.
Yes. This is the last slide. Don't worry, we are still on time. But I want to tell you one word. I want to take a moment. Actually, this is the conclusion, but it is, of course, not a conclusion. It's actually a beginning. I want you, please, to remember, it's a kind of emotional moment for all of us. We started this big story, actually, this adventure, started already something like 4 years ago. And 4 years ago, I don't know if you remember, when the government launched these PEPR tools, and then we wanted to promote light matter interactions science, not only chemistry, but also physics, but also biology, and even more, medicine, and so. And it was very difficult, you all know, because many of you participated to this adventure. We started with a blank page. And in a few weeks, in a few months, even in a few years, because we were not selected at the first round, we were selected at the second round, the year after. We worked hard to make it possible. But then, when it started, officially, this PEPR LUMA started administratively 2023, so it's already more than 2 years. But we had something like an empty grid. We needed to fill it with real science somehow, real projects. Of course, it was not empty grid because we had already some platforms that we have already selected during the writing of the project. But then we had to fill it with big consortia of research that we call the moonshot projects, through some call of expressions of interest through the INR, and then additional call for expression of interest to complement the platforms, and then another one call for proposals for additional research projects, which are actually now starting. This month, we have all the kickoffs of these projects. And now, we are at a time that the PEPR LUMA is fully implemented. So maybe some of you could think that it's really too long. I mean, 2 years and something to start effectively is too long, but keep in mind that we wanted to keep this PEPR LUMA open, fully open. I mean, these open calls, even the calls for expression of interest, calls for proposal, were open to all your ideas. We could not select all of them, but actually it was open. And we want to continue to keep it open with this access to platforms, to infrastructures, with these partnerships, with events, but this very new call, action that we want to promote young researchers together with the platforms that Céline described, and so on and so on, mobility, club, jeune. So all this is open to everyone. We want to keep the community all together. We want to create new, energy together, and the real science start now. It already started for some of you. The moonshot projects have already started 1 year ago. But basically, now we can start the real science, and I think and everything is described in this brochure, this project, and so the thematic research and the platforms, all are there. So please take one, or even take one more if you had only one, and distribute around you. This is, I think, a unique chance for all of us to promote our science, interdisciplinary science, and it's a unique chance actually to show that light matter interactions is not only beautiful, I think we are all convinced that it is beautiful, but also useful and fruitful, and we can communicate quite a lot with the society, with the government, whatever, so that PEPR LUMA can continue many years after the effective end of PEPR LUMA. Thank you. I hope you will enjoy this day. I hope you will agree with the general spirit, and I'm happy that we will all discuss together today. Thank you. Chairwoman is Valérie Blanchet.
Hello, bonjour à tous. So it's my pleasure to start this 2 days. And so the keynote will be delivered by Professor Majed Cherghi from EPFL Lausanne University, and as well working in Electra and Fermi in Trieste. So, and your title is From Linear to Nonlinear X-ray. Did you keep this one?
Yes.
Okay, good.
For the introduction. I'm quite impressed by the audience and also by this auditorium. It feels like the United Nations, but much better. I haven't been back to Jussieu since, I don't remember. I took classes here when I was doing my master's degree. I don't dare say the year. It was 1978, I think. So it's quite impressive, the changes that one sees. Okay, so my talk is about X-rays, and I realized in a somewhat late that I was the only one who was going to speak about X-rays. So I will do some introduction at the beginning, so that I try to convince you that X-rays are nice and that you can go from linear to nonlinear spectroscopy. And if you get this message, that's enough. The rest is not interesting. Okay, so there is this famous saying by Francis Crick, who was a co-discoverer of the double helix DNA structure. If you want to understand function, biological function, he meant, study structure. And so there are many techniques that give you static structures of biological objects, and that's already extremely powerful. But if you want to really understand biological function, you need to have it moving, and it's not going to move, as usual. Never mind. So this is an animation that shows the transfer of water through a channel in a cell membrane. What I want to say is that basically, I don't know why. Never mind. That if you want to understand things, the function of things or the reactions, you need to have them moving. And that's an old problem in science, which was first treated by this gentleman here in Paris, Etienne Jules Marais, who was a physiologist and an anatomist, so he was a scientist, who wanted to understand animal motion. And in order to describe animal motion, he wanted to take snapshots. And so he developed the shutter camera. And the shutter camera was called at that time le fusil photographique. And he took snapshots of all sorts of animals, including a very dangerous one here. And also, like cats, the famous, snapshots of cats falling paws up and landing on them. And if you take the cat, I like cats very much. If you take the size of a cat, let's say 30 centimeters, and you take the shutter speed that was in the millisecond range. Now you scale down the size of the cat to that of a molecule, so from 30 centimeters to 0.3 nanometers, then you will see that the millisecond scales down to picoseconds, sub-picoseconds. Later in his life, he also looked into fluid flow, did really beautiful films of the motion of flow. So, so it depends on of course, and we heard it already, it depends on the problem, scientific problem you have to treat, what time scale you're interested in. So again, animals, we're talking about milliseconds, but breathing takes microseconds to sub-microseconds, fluorescence light, emission thermal effects, nanoseconds, the isomerization of retinal in our eye, the vision, takes like 200 femtoseconds. Then if you go to lighter and lighter atoms, you have faster and faster timescales, like the vibration of water is about 10 femtoseconds, and you can go even further down into lifetimes of core transitions. And so in order to reach these timescales, there were different methods developed through history, from the stop flow to flash photolysis to relaxation methods, and that gave rise to a Nobel Prize to these three gentlemen in 1967. Then came the laser at the beginning of the 60s, and the laser quickly reached the femtosecond range, and that gave rise in 1999 to a second Nobel Prize in time-resolved studies of chemical reactions. So both of these are in chemistry, to Ahmed Zewail. And then, so these were all done, these studies were done mostly with optical domain spectroscopy, i.e. infrared, visible, ultraviolet. What we're interested in is going into the X-ray, and the light sources for the X-rays, especially pulse light sources, were synchrotron radiation, which could reach, which reaches still about 30 or 50 picosecond in pulse duration. You can go further down between 2000 and 2015. There was a laser slicing scheme that allowed extracting femtosecond pulses from synchrotrons, but soon came the free electron lasers, and they basically cover the entire range, and now they're going also into sub-femtosecond timescales. You also had lab-based sources, laser plasmas, that could generate femtosecond X-ray pulses. And more recently, we have broken down below the femtosecond, and that is the attosecond time domain, and as was already mentioned, a Nobel Prize was awarded in physics in 2023. So I don't know if there is going to be, after 20 years, another Nobel Prize in zeptophysics, maybe, I don't know. We'll see. Okay, so what can you do with X-rays in terms of structure? So you have one technique, which is X-ray diffraction, in which you have, so if you want to do it in the time domain, you have a crystal, you excite the crystal with a short pulse, and you send the X-ray pulse to probe the motion that you have generated in this crystal as a function of time delay between the light pulse and the X-ray pulse. And so you could have, I don't know, melting, so the diffraction spots are going to blur away, and maybe recrystallization, so they will reappear maybe in another phase, or you can get coherent phonons, so you have the crystal breathing, and so you can get these diffraction spot oscillating, like was shown in this very first experiment using time-resolved femtosecond X-ray diffraction, where they saw the coherent phonons in a bismuth solid. But that's for solids, and in chemistry, this is not always what you want. So you want to go to solutions, and you can, oh gosh, why is this doing this? So you can go to solutions, and you have a liquid jet with a molecule you want to study, and you do the same thing as here. You pump with a laser, you probe with a time-delayed X-ray pulse, and now you detect the rings because you have a disordered system, and then you can retrieve the information about the solute, the solvent, and this is a nice example in the case of a cobalt complex, where again they saw nice coherent vibrations in the system. Now, this is one approach, but the title of my talk is about spectroscopy. So the other technique that is very much used in the X-ray domain is X-ray spectroscopies, and the simplest one is X-ray absorption, where you come from a core shell into the continuum, and you get these edge absorptions, so K shell, L shell, M edges, give rise to these nomenclature, and basically you get this edge every time you cross into the continuum. And with X-ray absorption, I'll go back to this in more detail, you can get the electronic structure of the atom, its oxidation state, and the local geometry. The other technique which we use a lot is X-ray emission. Once you have created a hole here it's going to be refilled either by K alpha, K beta, or valence to core emissions. And this X-ray emission is a very nice fingerprint of the oxidation state, but also of the spin state of the system. And then you have the XPS, famous X-ray photoelectron spectroscopy, or UPS if you want. That gives you, and that's very important, the absolute binding energies, because you reference respect to the ionization continuum. And you get also very important information about the chemical bond by looking at different atoms, identical but inequivalent atoms within molecules. So core level spectroscopies are very rich. There is a whole zoo of acronyms, many, many more. Some of them you don't want to say in the presence of children. We have, I will focus now mostly on X-ray absorption, just to make the point about what you can get as information out of it. So you know from undergraduate physics textbooks this type of spectra. This is the X-ray absorption spectrum, where you see the K shell absorption and the L shell absorption. I want to point that Charles Barkla obtained the Nobel Prize for discovering X-ray absorption in 1911. That was 2 years before Lauer and the Braggs, I think, who discovered X-ray diffraction. So he had no dispersive elements when he did his discovery. He used metal filters, and he found that there were edges. And when he found two edges, the first two edges that he found, he took the first two letters of his name, BA. And then he thought, well, maybe the people will discover new edges. So if you start from B, you go to A, then there is nothing afterwards. So he switched to KL. That was quite nice of him, because then people discovered the M edges and the N edges and the O edges. So anyway, if you zoom into one of these edges, you have a lot of fine structure. These are under the edge, or if you want the ionization threshold, bound-bound transition, atomic transitions. Then you go into the continuum and you get these modulations, which are due to the fact that you generate a photoelectron. And this photoelectron here, this is the isolated atom. And once you have a neighbor, this photoelectron will backscatter onto the neighboring atoms and give rise to modulation of the absorption coefficient, which are classified as Xanes and XFs. And basically, I mean, in a nutshell, you have this situation where the photoelectron, this is a classical picture, is backscattered, and you have interference between the outgoing and the backscattered wave, just like you have on a still water in a pond. So the Xanes has the advantage that it has a high, it's in a region where you have a high, a high scattering cross-section, so you get multiple scattering. And so with Xanes, you can get the local structure, the three-dimensional structure, whereas the XFs region is only one single scattering event. And so you get mostly bond distances and coordination numbers. So why is X-ray spectroscopy so interesting? You can apply it to any medium. It's element specific, so you tune to specific absorption edges of atoms. You can detect optically silent species, something that we very much exploited. And you get very much information about electronic structure, which you don't in X-ray diffraction. You don't get that much information about the electronic structure, in particular the density of unoccupied or occupied states, the valence, the nature of the valence orbitals. When you come from a core to the valence orbitals, you are interrogating the valence orbitals. And these are the guys that are doing the chemical bond. So that's very important. Any changes in the molecule or the system is going to be reflected in your spectrum. Degrees of oxidation, local symmetry, spin state, and in a way, if you want to call it a drawback, you only get bond distances and angles of the local geometries, not the global structure like you get in scattering method. But we didn't care because we were interested in ultra-fast phenomena, and the short time scales correspond to short length scales. So that's fine as far as we are concerned. So over the years, that started about 25 years ago, we looked at different phenomena like intramolecular charge transfer in metal complexes of interest for solar energy conversion. We looked at the spin crossover dynamics. This is interesting for magnetism. So these are molecules, metal, mostly with iron or cobalt, that undergoes, delta S equals 2 spin changes under the effect of light, temperature, or pressure. We studied them under the effect of light here. Bond formation in bimetallic complexes, plasmons in metallic nanoparticles, solvation dynamics, how the solvation shell changes after you excite a solute. Protein dynamics, I'm going to go into more details now. Transition metal oxides, we looked very much into both sensitized and non-sensitized transition metal oxides, different type, titanium dioxide, nickel oxide, cobalt oxide, and also more recently, perovskites. I'm not going into the details here. What I want to say is we did the first phase of the work with synchrotron radiation, and then later on, around 2010, the free electron lasers came into operation. The first one was in Stanford, and there was one in Japan, and later on, others came into operation. This was a hard X-ray machine. As you can see, the length of the machine is in kilometers. And one of the first soft X-ray machines was in Trieste at the Electra Center. And then in Switzerland and in Germany, 2 more machines came into operation. Basically, they are laser-like. They are not actual lasers, except for the Electra free electron laser, because it's seeded by an optical laser. Anyway, the big advantage of these machines is that compared to synchrotrons, where you reach the 50 to 100 picosecond pulse duration with typically 10 to the power 6 photon per pulse, here you go into the sub-100 femtosecond, and you have 6 orders of magnitude more in flux in the hard X-ray regime, and 10 orders of magnitude compared to the slicing, which was a technique used to extract femtosecond pulses from a synchrotron. So it's a big, big advantage, and that also justifies a drive towards nonlinear X-ray optics. So after this long introduction, I'm going to give you some examples. One is about linear pump probe X-ray spectroscopy of heme proteins. And the second is about nonlinear chemistry techniques. And then I will tell you something about more recent X-ray studies that we started in my group on chirality. So heme proteins are very important because we have them in our blood. And this was a work that Linus Pauling did publish in 1936, and he said that Michael Faraday had investigated dried blood and had noted that he should try recent fluid blood. If he had determined the magnetic susceptibilities of arterial and venous blood, he would have found them to differ by a large amount. And that's very important because this is where you have a switch in the structure of the heme. So let's introduce the heme first. So this is hemoglobin, and it's composed, it's a tetramer of 4 myoglobin-like proteins. And myoglobin, the bioactive center, is this porphyrin. So you see it here with the iron atom and the ligands, typically oxygen, but you have all sorts of ligands that bind to this iron, NO, CO, H2S, CN, what have you. And what happens is when we breathe, we take in oxygen. The porphyrin goes, so typically it is planar when it has the oxygen bound to it. When you release the oxygen, it goes domed. So this is arterial blood, this is venous blood. And what happens is really that this is what I call the transition state of the respiratory function. At the very beginning, what happens is you go from a low spin when you have a ligand bound to the iron to a high spin. And when you go to the high spin, you populate antibonding orbitals, and the iron N bonds elongate, and therefore it turns the porphyrin into a dome. Now, why has this to do with the respiration? Is that this iron pushes on this histidine. This histidine is bound to this helix. This helix then sends a message to the other units, monomers, that oxygen has been uptaken by one of the monomers. Now, a phenomenon happens called allostery in hemoglobin, that once one monomer has taken up an oxygen, the affinity of the others to take up oxygen increases. So this is a cooperative reaction in biology, very fascinating, which is not fully understood, but the hint that was given by Max Perutz, one of the guys who determined the structure of myoglobin, is that it should be some mechanical signaling via this F helix that is on the other neighbors. But anyway, let's go back to the very initial event, which is of interest to us. And in fact, hemoglobin and myoglobin should be really very important to any ultra-fast spectroscopist, because, not because, I mean, they should be close to their heart, not because it's only, blood, they are the main constituents of blood, but because the very first femtosecond studies ever done were done by, on hemoglobin and myoglobin. So the first paper appeared in 1976. That was with a 500 femtosecond pulse by Chuck Schenck, the guy who developed the femtosecond laser. They published this paper, and then there was nothing published until here in France, Jean-Louis Martin picked up the problem again and pioneered the femtosecond studies of heme proteins using femtosecond lasers. It was quite an achievement if you think about it. And it was also the very first system to be studied by time-resolved X-ray absorption spectroscopy. So that was done at Cornell, at Chess at that time, at the synchrotron, with millisecond resolution. Never mind. I mean, they photolyzed myoglobin with a CO ligand, and they looked at the change in the edge, which is due to a change from planar to domed, as I mentioned before. So despite this long history of studies, starting from the early 80s, there were still questions. How fast is doming when you release a ligand by a pulse? Is a process driven by electronic effects, or is it a thermal effect? And there's been a debate about that for ages. And I dare say that we came in with the X-ray because we were the first ones to look specifically at what the atom does. And I'm not going to go into now showing you the results and the spectra and the transients. I just want to summarize what we found. We studied different type of heme proteins. This is myoglobin with an NO ligand. All these are ferrous heme proteins. We looked at cytochrome C. Cytochrome C is very important for electron transfer in the body. And again, a ferrous porphyrin. And you see that there is some pattern which is very similar in the cascade, and that this cascade proceeds via spin states. So you excite the pi star of the porphyrin, and you end up in an intermediate spin of the metal, and then a higher spin of the metal, and then you relax back. Now, this step of the relaxation is very different from porphyrin from heme to heme, because it involves some chemistry. In this case, you have an NO ligand. This case, you have a methionine ligand. They don't recombine the same way, and that is mainly the last step. But the important ones are these steps. And if you look at the literature, optical domain studies also hinted to similar values. This is with a CO ligand. This was an X-ray work, sorry, also by the group of Levantino et al. And this was an optical work. And again, you see a very similar pattern in the time scales of the initial cascades. And that reminded us of a class of system we studied a lot, which are the spin crossover iron II systems, we and others. And we found that the spin switch from S equals 1, S equals 1/2 to S equals 2 is extremely fast, and typically on the time scales of a few hundreds of femtoseconds. So the photophysics of heme proteins is very much identical to that of spin crossover states. So you know, whenever you feel dizzy and you go into a high spin state, this is all governed by spins. It's not so much, there are not so much thermal effects in heme proteins. So with this, I wanted to give you an example of what X-ray spectroscopy can do. You have to combine, of course, we use the optical domain spectroscopy, transient absorption, and fluorescence subconversion, which we combine with our X-ray absorption and X-ray emission work. So you get all these fingerprints of the spin states in a very clean way. Now, I want to switch to nonlinear spectroscopy. One would ask first, why do you want to go to the extreme ultraviolet or the X-ray domain? These domains are those of the core transitions. So, in fact, again, so I want to stress that the advent of free electron laser is putting us in the same situation as the advent of optical lasers in the 60s, where thanks to the laser, we saw the birth of nonlinear optics and spectroscopy, and here we're exactly in the same situation. So one first obvious advantage is that you get element selectivity. So now you can look in a nonlinear process at atoms, specific atoms. You are structure sensitive. You can access large momentum transfers that I'll come back to in a second. And you have to bear in mind that when you go to short wavelengths, concepts like inversion symmetry have to be adapted to short distances. So sometimes crystals that don't have global inversion symmetry or do have global inversion symmetry lack it when you go at the level of reticular planes in a crystal. And you can probe, depending on the type of radiation you use, bulk versus surface effects. So the history of nonlinear core level spectroscopy starts quite a while ago, well before the advent of free electron lasers. There was a spectacular experiment done, the parametric down conversion in the early 1980s, which is a parametric down conversion has some variance resemblance with difference frequency generation, where they put they use an X-ray tube on the diamond crystal, and they got emission of another X-ray photon and an XUV photon, when the sum of the two corresponded to the incident radiation. I think it was copper K alpha or something like that. Really very impressive work. And then 10 years later, this was repeated at the synchrotron. But we can say that now, over the past 10 to 15 years, all the major nonlinear tools that we know in the optical domain have been demonstrated in the X-ray domain. So stimulated X-ray emission, stimulated X-ray Raman, two-photon absorption, Rabi cycling, this is more recent, and second harmonic generation. So I like second harmonic generation in particular because we are working on it. So in second harmonic generation, as you know, you come in with an incident beam, and you detect the double frequency after passing through the sample. This is a Chi-2 technique. The other Chi-2 technique is sum or difference frequency generation. And there was a spectacular experiment done, published in 2012, where they had a diamond crystal, an X-ray beam at 8 kilovolt, and an optical beam at 1.5 kilovolt. And they managed to see the sum of the two in analyzing the emitted light. And they matched in order to have a good phase matching, they also matched their vectors with the inverse of the lattice, with a lattice wave vector. And that was quite impressive and was not repeated until this year on silicon crystals, which are quite similar in some of their properties to diamond. So this is very nice because Chi-2 techniques allow you to really now look into surface or interface chemistry with atomic selectivity. You can look at catalysis, and you can use it also for chirality, which is one of the avenues we're pursuing. The other nonlinear techniques are four-wave mixing techniques, which are Chi-3 techniques. And one of the most popular one is transient grating spectroscopy, which I'm going to tell you about, and was pioneered at Elettra by the team of Claudio Masciovecchio. And recently we published a review of all these techniques at the XFEL's in Nature Physics Reviews. So transient grating spectroscopy is one of the first nonlinear optical techniques to be developed. Basically, you have two identical wavelengths beams that come under different directions, so different wave vectors, and you interfere them on the sample. So you're going to form an interference pattern of excited, unexcited, excited, unexcited regions. And then in order to follow the evolution of this, so that could be an excitation, electronic excitation grating, a thermal grating, a magnetic grating, whatever, you come with a third beam and you diffract onto this grating. And as the grating fades away, you can follow its evolution in time. And you detect this probe pulse in a different geometry, so this is a background-free technique. So as I said, you have different types of gratings. Now, if you use optical light, so the grating period is given by the wavelengths of light and the crossing angle. If you use visible light, typically you get gratings of 1.4 to typically 1 micron. So transient grating spectroscopy is very much used to look at the transport phenomena in solids and liquids and even gases, and it's extremely well established. But if you go now to shorter wavelengths, you see that in the soft X-ray range, typically 12.4 nanometers, you can make grating steps of tens to hundreds of nanometers. So now you are starting to enter really regions of transport phenomena at very short distance scales, so nano to meso. And if you could do it also in the hard X-ray, and I will show you that we did it, then you go into the nanometer scale. Now this is very important because people who are looking at transport have no clue what happens at very short distances, especially when phenomena change from ballistic to diffusive transport. And I always think that, maybe I'm a bit idealistic, that transient grating nano and microelectronics have no idea how heat is managed in these nanostructures or excess charge, all these things. So this could be a way of looking into it. So these are the advantages of going to shorter wavelengths. And as I said, you have high momentum transfer. That is, you can look at high frequency responses, high temporal resolution, element selectivity. And by the way, transient grating spectroscopy was the stepping stone towards multidimensional optical spectroscopy when it was in the optical domain, and people are hoping that it will be the case for core level spectroscopies. That is, when you use two different wavelengths instead of identical wavelengths that you can tune, so you can do 2D spectroscopy. Anyway, okay, enough for the publicity. The first experiment that was done demonstrated transient grating spectroscopy in the extreme UV was done, as I said, at Fermi, at the Elettra Center, and they used two photons at 45 eV, which they cross onto the sample, and they probed them with an optical pulse, and they got these nice responses with electronic response and optical phonons and acoustic phonons and so on. So this was really a proof of principle. But now, when you create a grating which is in the tens of nanometer scale, and you come and probe it with 400 nanometers, the spatial information that you gained from making this grating with short wavelength light is lost. You see interesting things, but you don't have the spatial information. So the next step in this group was to go to an all EUV transient grating experiment in which the optical pulse is replaced by an EUV pulse. And in order to do this, they used their extreme UV optics, where you have the beam coming from the free electron laser, you split it in two, you generate the probe beam here, and the rest of the beam here, you split it again in two, and you generate the two pump beams. So you cross these two identical beams. All three beams are identical in reality, but one is time delayed, the green one, with respect to the other two. So you can probe the system as a function of time after impinging the grating on it. And compared to the optical response in this experiment, they got a different response with the EUV probing. This response at short time is pure electronic, whereas here they only get the structural response. That's because when you use an optical probe, your index of refraction is strongly determined by the charges you have in the valence and the conduction band, and it's much more sensitive in the optical domain than in the X-ray domain or the extreme UV domain. But anyway, these are beautiful proof of principles. What happens when you go to the hard X-ray? Now, the hard X-ray, you don't have optics like that. So you have to really scratch your head. So Chris Vettino, with whom I collaborate since years, had the beautiful idea of using the Talbot effect. The Talbot effect was developed in the 19th century. It's basically you have a grating and you have a plane wave coming onto it, and then you have different orders of diffraction. And these different orders of diffraction will overlap each other's at regular distances called the Talbot distances. And the Talbot distance is determined by the spacing of the grating and the angles, and the wavelengths. Well, the angles too. And so you can place your sample at one of these Talbot planes, and you can reproduce the mask onto the sample. And so we did this first to do a permanent mask, and we found that indeed you can reproduce a step of the grating on the sample, and then you can then use this to do transient grating spectroscopy, like here. So you come with incident beam, you create the grating, and you probe it with an optical beam. So the first demonstration of this process was published 4 years ago, and you see the response of the transient grating. So this is, at this stage, we did this experiment, by the way, at 7 keV, probed at 400 nanometers. We didn't bother about going into very, very tight gratings. We just wanted to see that we created a grating with these high energy photons, and we could probe it, and you see coherent phonons. This is a bismuth germanate compound. But then, again, as I said before, if you do it with an optical probe, you've lost the spatial information. So the next step was to do an all hard X-ray transient grating spectroscopy experiment, where we took a silicon sample and we created so we had this was done at the Sakura free electron laser in Japan, which could produce two color X-ray pulses at 5 and 7 keV, 5 femtosecond pulses, pulse widths, and the time delay could be tuned between the two. And what we did here is we create a Talbot carpet, send the probe beam through it. We detect the transient grating, but we had the other advantage of being able to detect diffraction peaks sideways. So we had two detection schemes, one of the transient grating, but one also of the actual grating of the crystal. And what we found is very noisy, but it's very interesting. You find this response with a sharp peak at the beginning and then oscillations. And if you look carefully, you see that the peak appears with some delay, typically 15 femtoseconds, and these are the two detection channels, transient grating or diffraction. And this oscillation is typical of the optical phonon that you have in silicon. It's been observed by optical methods and other methods. But the interesting thing is the first peak of this oscillation appears after 15 femtoseconds. And that's a time scale for electron-electron scattering and the transfer of energy from electrons to phonons. That's never been measured in real time. And this is one of the first manifestations. And we believe that these techniques will be extremely useful to understand how these, the hot photo and Auger electron that you generate by the first X-ray pulse are going to transfer their energy to the phonons. Okay, so that was for transient grating spectroscopy. Can we do it in the liquid phase? Yeah, because the liquid phase is important for chemistry and biology. So we did an experiment. I'm going to skip some of the slides because I'm running out of time, where we took this ferrioxalate molecule that undergoes a photochemical reaction. When you're excited, you have a bond breaking of these ligands and a recombination, and we wanted to follow the reaction. I'm not going to go into the details. What I want to show here is that we see very clearly a transient grating signal with a certain temporal evolution. And if you scan across the iron edge of the solute, you see that you have an increase. Basically, the intensity maps out the absorption edge of the iron. And we're still analyzing these data. They're not completely analyzed. This is work in progress. But I just wanted to stress the fact that we can do this experiment in the liquid phase. This is quite important for future experiments. Of course, the pump beam in all these transient grating experiments is a core level transition. So, you know, if you're bothered about that, that's a different issue. But if your goal is to look at transport processes, once you have generated whatever, charges or heat, or then this is really ideal, and especially for going into small grating steps. Okay, now my last few minutes, I will tell you about chirality. So after I retired from EPFL, I moved to my activities to Elettra in Trieste, in Italy, after earning a new ERC grant called Chirax. So I don't think I need to tell you about chirality here. I mean, it's the fact that you have objects that are mirror images of each other, but they cannot be superimposed on top of each other. And that plays a very important role in pharmacology, in drug design, and in medicine. And the way to detect chirality is still, to this day, at least, and let me stress, for molecules in solution, which is very important for biology and biochemistry and chemistry. The way we detect them is by doing circular dichroism spectroscopy, where you have left and right-handed circularly polarized light that are absorbed by the sample, and you look at their difference. And this difference is tiny because in the light-matter interaction, I mean, we're in the LUMA PEPR, so I have to talk about the Hamiltonian of light-matter interaction. You have the term due to the electric dipole, and here you have the term due to the magnetic dipole, and then higher terms due to the electric quadrupole. And these terms are really tiny, and that's why the response is so small. So our idea was to try to enhance the sensitivity, again, for molecules in solution. So we thought, okay, let's extend CD spectroscopy to the X-ray range. For one thing, these higher order terms, magnetic and quadrupole, scale as A over lambda. And so if lambda goes down, then you should get an enhancement corresponding to the wavelengths of the signal. But that's the tourist brochure. The reality is very different because the transition dipole moments for valence and core transitions are very different. So the signals that you get in the X-ray are not so intense or so anticipated to be so intense. But nevertheless, you have element specificity. And the fact that another element specificity is that the dichroic response depends on the chemical environment for a given atom. So if you have identical but inequivalent atoms in a molecule, which traditionally you distinguish by the chemical shift, but sometimes it's not always easy to separate, you know, in energy, the different chemical shifts, then here you have an additional parameter to play with, which allows you to look at the dichroic response of these identical but inequivalent atoms. Again, I insist, we are talking about solution. In isotropic media, the electric dipole, electric quadrupole contribution vanishes. Now, I show you this? No. Okay, let's jump. So to illustrate the fact that different identical but inequivalent atoms have different responses, there are several simulations that were done over the years. There are actually more simulations on the subject than there are experiments in the X-ray domain. And here you see noradrenaline, for example. You see here the absorption spectrum at the carbon edge, where you see highly congested regions. And if you now run a CD spectrum, an X-ray circular dichroism, you can very easily disentangle what is what under these blobby features. There was a calculation even done for C84, where they could predict disentangling the X-ray absorption spectrum of these identical but inequivalent atoms. So we looked into the literature, and until recently there were only very, very few studies, and you can count them on the fingers of one hand, that were done on powders of amino acid residues, because you have to tune into the oxygen, nitrogen, or carbon K edges. You have to work in the soft X-ray, and therefore you have to work in the vacuum, and that's why people mostly used films or powders of these compounds. And these are the few studies that were done. They are not always so convincing, because if you have a solid sample, then you have radiation damage, and it's very difficult to get the mirror images typical of circular dichroism spectra. Only one study looked at XCD at the carbon edge, and that was for a disordered system, for a dilute system, that was gas phase methyloxyrane in 2004, again at Aletra, and they got these XCD spectra. And we looked more recently in the hard X-ray, but that's not circular dichroism. We did helical dichroism of enantiomeric pure powders of an iron spin crossover compound, and we got the mirror images for different topological charges. I mentioned this because someone spoke about in the introduction about the fact of using light to drive chirality. So this is the first, to my knowledge, the first study of X-ray helical dichroism on molecules so far. But in the liquid phase, there was nothing. So in 2015, these flat liquid jets started appearing, where you can now do X-ray absorption spectroscopy with these thin jets. Typically, we are talking about micron-thick jets that you inject into vacuum, and we decided to use them to do X-ray circular dichroism spectroscopy. We did about 3 experiments within 1 year. The last one was done at Pléiade in Soleil. But I'm showing only one result, the one that we have well analyzed so far, and this is alanine, I think. Yes, it's alanine. No, cysteine, yes. L-cysteine, so the left-handed cysteine. These are simulations, absorption spectrum and CD spectrum, and these are the absorption spectra and CD spectra that we got at the beam time at Bessy. Last May, we had beam time at Soleil. We have very promising results, but the analysis is not finalized, so I'm not going to show them. Now, I stressed a lot about X-ray work, but in reality, we have always, whenever it was necessary, we've combined a lot of techniques, and that brings me back to some philosophy. The legend of the 6 blind men and the elephant, and each one touches a part of the elephant and says, okay, this is a rope. The other one says this is a pillar, this is a pipe, this is a wall. They all are right in a way, but they don't get the global picture. So you really have to combine all these techniques, which we did in my lab, to account for the totality of truth, if possible. And with this, I'd like to thank my collaborators at the different. So here, this is my team at Aletra, and all the collaborators, different synchrotrons and free electron lasers with whom we collaborated, and theoreticians and many other people. And I thank you for your attention.
Thank you, Majed. So now it's a time for questions. Is there any? Yes, Elisabeth?
Hello, thanks for the beautiful talk. I'd like to ask you about the CD in solutions. So you quite rightly mentioned that electric dipole transitions will disappear in isotropic media. But if I don't really quite understand the mechanism, if you suggest that it's electric dipole, magnetic dipole, but we're looking at core continuum transitions. So magnetic dipole transitions should be forbidden by the selection rules. So can you explain what part I'm not understanding?
So I'm not sure I got your question, you say?
So you presented these results on circular dichroism in solution and said that these are arising from electric dipole, magnetic dipole interference. But if we're looking in the X-ray range, as opposed to the UV visible range, we're looking at core continuum. So I guess you're looking at 1s to continuum transitions, which would be forbidden by the magnetic dipole, which can only occur.
Oh, yes. Yes. So that's interesting. Thanks for the question. So when in light atoms, the energy gaps between these different orbitals, different levels, core levels, is small, and therefore you get configuration interaction and core relaxation that also play a role. So you do get mixing between the different orbitals, and you borrow, therefore, some intensity. But we're doing experiments. We've done some experiments at the sulfur L edge. So you go from P to that seems to work also quite well. So yeah, good point.
Any other questions? Yeah.
Yes, Majed, many thanks for this really nice talk about the last part on the CD of cysteine in solution. I mean, just from this simple spectrum that you showed, what do you learn about the molecule, about the structure, or its potential dynamics? I mean, did you play with pHs? Did you look at various core levels? I mean, what do you learn from just this picture? I mean,
okay, very good.
Beyond the fact that this is a tour de force, I know it's super difficult, but
I can stop you there. We don't learn anything. I mean, this is no. X-ray CD of liquid solution has never been done, so we are struggling, because it's far from easy in demonstrating it. First, I can explain the reasons. I mean, when you scan a CD spectrum, you scan left polarization, then you scan right polarization. When you do this, and the signals are very weak. Already in the optical domain, it's not a trivial technique. If you are doing this at the synchrotron, you have to scan first, switch the polarization, scan again. During the scan, lots of things can happen. You have the decay of the photon flux. You have instabilities in the liquid jet. Then you have a minute to switch the polarization, do another scan. All sorts of things happen. And we are really still struggling with this. So we're quite proud of this result, even though we are not yet at, learning what the molecule does and look at these effects, because we're not yet completely, rock solid about the data acquisition strategy. You need to have a lot of references. This is a dilute system. In reality, the reference is not the I0 beam, but it's the I0 through the pure jet, and it's impossible to record at the same time a solution and the pure solvent. So you see all sorts of artifacts come into play, and you have to be really, really careful about reproducibility. So we are at this stage. Yeah. And I didn't have time to discuss it, but in fact, we want to go on in this line, but we are now working on another line, which is to use Chi2 techniques. So combine optical and X-ray pulses and do some more different frequency generation, because in this case we anticipate background-free, better signal and direct information about the chiral solution. So it was already demonstrated in the 60s that Chi2 techniques can be applied to liquid solutions provided it's a chiral solution. And you get a response from the bulk, not from the interface only. Yeah? Okay.
Thanks.
There is another question by Anne.
Thank you, Majed, for sharing these beautiful results. I have a question also on core shell CD, because for electronic CD, when you have similar orbitals, they can couple in some sort of exciton coupling with opposite CD signals. So I was wondering whether if you take similar or identical carbon atoms, do their core shell CD give opposite signals too, or for example?
Yeah, it depends on the environment. Yes, I mean according to theory, yeah? Because we haven't had the chance or the privilege of demonstrating this yet. But according to theory, I mean you can see here, for example, under this feature or under this feature, you have different differential responses. I don't know if this answers your question.
We can discuss later. Thank you.
Any other one? Okay, I have one. How long did it take to record the? Roughly.
This X-ray CD.
Yeah.
After 2 weeks of measurements.
Oh, yeah. Okay.
No, but I mean we recorded. No, it takes recording the spectrum takes. Let's say 5 minutes, and then 5 minutes with the other polarization. Okay, but then you get lots of data and you have to analyze it. We took 2 weeks of, it wasn't difficult to get the absorption, the nitrogen. By the way, sorry, I forgot to say this is nitrogen KH. It wasn't difficult to get the spectra, but to see what makes sense took some time.
And I have another question about the X-ray transient grating and X-ray diffraction. Would it be interesting to, instead of to use an optical light to probe the grating, to go, I know that it's more demanding in terms of photons and stability, but to go to the X-ray probe, meaning that you create some change of the indices due to all the electronic excitation, and then probe to another age.
Yes, it's been done, by the way. So you mean do the grating with an optical pulse and probe it with an X-ray?
No, everything X-ray, but not the same KH, or not the same.
Ah, yes, but in fact this was done here. It was not at an edge, by the way. Sorry, we were not tuned to a specific edge, but we used 2 colors. Here we use 2 colors. Yeah. So we did try also at the European XFEL to use 2 colors tuned to different edges, but for a reason that have nothing to do with the edges, the experiment didn't work.
Is there last questions? No? Okay.
There was one here.
Regarding your point about helical dichroism, could you maybe tell a little bit more about what helical dichroism enables compared to more conventional circular dichroism?
Yes. Well, I mean, you come with different orbital angular momenta. I didn't describe the experiment. Yeah, here. So we did this at the synchrotron at the Swiss light source. And we had these spiral zone plates that allowed us to choose the topological phase of the light. Now, the whole difficulty of this experiment is you are using a ptychography beamline, because you need to make sure that you have the right phase, So And these ptychography beamlines are not always adapted for X-ray spectroscopy. That means scanning spectra. So that was quite... okay, so anyway, you see that if you have orbital or angular momentum, L equals plus or minus 1, L equals plus or minus 3, you see this mirror images and so on. Now, the big advantage of helical versus circular dichroism is that you can choose. You see circular dichroism, you have S plus or minus 1 and 1/2. Here you go from 0, plus or minus 1, plus or minus 3. So you can really adapt. We don't, I'll be honest with you, we don't fully understand these spectra. Jeremy is still working on the theory. But I think there is a wealth of information about higher order effects in the system that one could pull out. I mean, this is really the beginning, in my opinion, so, yeah.
Okay, we will thank again Majed. And now we welcome Olivier Sopera from University of Mulhouse, and he will speak about the plasmonic photopolymerization from fundamental investigation to application in sensing.
Thank you very much for the kind introduction. So it's not easy to try to do it. And giving you a short overview of what we have been doing in Mulhouse about plasmonic photopolymerization, so which is a topic that is for me. That is a topic for me that is quite interesting because it's really at the border of different fields from plasmonic, material science, photochemistry. And I want to express today how we are trying to understand and to use this tool to understand how plasmonic can be coupled to some nanochemistry, and also how we can go to practical application using this process. Using plasmon to induce chemistry at the nanoscale is not new, and there have been many examples in the literature in the field of energy, using a plasmon to start photocatalysis reaction for energy conversion, in environment also for CO2 reduction and the way to couple this CO2 problem, and also many applications in biomedical like photothermal therapy and drug release. What we are interested in is to couple the plasmon phenomenon with polymerization and photopolymerization. So for that, we are using two kinds of nano objects. One can be metal nanoparticles. In that case, what will be exciting is LSPR, localized surface plasmon resonance. But also, we are interested to use metal thin film, for which we can excite surface plasmon resonance. So why plasmon resonance is interesting in this field of photopolymerization? Because what we have around this kind of structure, for instance, is a very highly confined electromagnetic field, which is not limited by the diffraction. So the idea is really to try to use this as a very small light source at the nanoscale and try to start photopolymerization reaction. It's also spatially localized. In this case, in this example, for instance, for spherical nanoparticles that is excited in linear polarization, you have the excitation in the direction of the polarization. So it's highly spatially localized. So that means that beyond the temporal and the chemical reaction that we can start, we will be also very interested to see spatially where the reaction is taking place. And also, the field is much enhanced around the nanoparticles in the resonance condition, so we can use really this energy to start new processes. And really, our objective here is really to use the near field as a nano source of light to start a polymerization reaction, and also to use it to probe the plasmonic response, and especially spatially. So to make the story very short, we can use three pathways to start the polymerization reaction, starting from a metal nanostructure. One is to excite hot carriers and then start redox reaction to make it simple. Another phenomenon is also to use a thermal reaction, and now we are much interested also to use this. I will not talk about this today, but this is ongoing work by Céline Molinaro in our group. Today I will focus mostly on photopolymerization pathways. So really the idea to enhance the electromagnetic field around the particle and use it to start locally the chemical reaction. But we always have to keep in mind that the three pathways will always be possible in all systems, and it's always difficult to be sure, 100% sure, that we are using one pathway and not the other one. So like I said, we are in this talk, I will just show example for which we are really trying to be in this photopolymerization process. So the idea is really to use conditions for which we cannot induce far-field polymerization, but at the same time, we have a nanoparticle that is embedded in a photopolymer, and the enhancements of the field around the nanoparticles make the field much higher, so the light intensity much higher around the nanoparticle. So we have a chance to start the reaction. So all the key is really to play with inhibitors. So we have inhibitors in the reactive medium. So in the example I will show later, we are using acrylate photopolymers, and they are known to be strongly stopped by reactions with oxygen. So the idea is really to find conditions for which in the far field we cannot start efficiently the photopolymerization because of this inhibitor, but in the near field, because we have more energy, we can start efficiently the reaction and make polymer parts. And at the end, we wash everything so that we can remove the non-reactive part and keep only the polymer that is formed in the near field. So this is a typical example that we have been doing during the last year. So the idea is really to start with a nano triangle. So you can see the dimension, something around 60 nanometers. We put this nano triangle inside the photopolymer, we shine the light. We can choose the polarization along X or Y. And these are the simulation. And if we compare the simulation of the field with the polymer lobe that we obtain here, so this is the gray part in the TM images. In this polymerization, in this polarization, we have the polymer in this apex of the triangle, and if we turn the polarization, we can have the polymer in this direction. So I really want to stress out the scale, so I should have put it again here, but okay, this is 60 nanometers, so we can really make photopolymerization using visible light at a scale that is really a nanoscale, so much lower than the diffraction limit that we are expecting in classical optics. So then the interest of this approach is that we can really play with many parameters. One of them is the shape of the nanoparticles, and also playing with the polarization and the shape of the particles. We're very interesting to see what is with this different geometry of nanoparticles. And also something we're not really expecting is that the polymerization process is very different for all the objects from the isotropic or anisotropic state. What I mean by that is that on nanoplates it was very difficult, and we could not find condition to really have the polymerization for this object in the polarization direction, whereas for the triangle, for the B pyramid, we can really have something very confined. And to go a little bit further, we also try to demonstrate that this principle can even be done in a kind of a 3D configuration. If we are using a B pyramid, so these objects are known to stay on the substrate really with an angle. So that means that the two apex of the B pyramid are not the same. This one is really stuck on the substrate, so in close contact with the substrate, whereas this one is a little bit away from the surface. And we could show with the TM, and also by changing the angle of the view of the images, that effectively the two polymer lobes was not looking the same, and we could demonstrate that this guy is really this one, whereas this polymer lobe corresponds to the one that we are forming on the substrate. We are very happy of this result, because that's the first paper that we published in the frame of the Sunrise project with Stéphane Parola object, and we hope we will have many others after. And coming back to Sunrise project, really the challenge and what we want to further develop in this project is really to push this resolution and the photopolymerization down to the limits. And what we like to demonstrate is that we can go to the single macromolecule level. For instance, it's a very early stage of the polymerization. We observe this kind of very tiny polymer lobes, in this case on spherical particles. And we are really thinking that it corresponds to only one single photochemical reaction, because we have so few photoinitiators that it really corresponds to the number of events that we can expect. And then playing with the polarization of light, we are really expecting to be able to play and to push the limit of the photopolymerization to really the extreme limit. And so for us, it's a very nice tool just to study this kind of reaction at the nanoscale. But also because I'm coming from material science and photopolymer, we are also interested the last year to change the materials around the particles and use this process to graft functional materials, different functional materials for different applications. So this was done through many collaborations. In this work, we were collaborating with people from macromolecular chemistry to show that we can use what we call living photopolymerization to make core shell structure with different shells, and using system that we can restart the polymerization for the surface in a second stage. So we make a first layer, and then we can make a second layer by grafting, covalently grafting the polymer on the object. With Renaud Bachelot in Troyes, also they managed to, using this approach, they managed to demonstrate also that you can graft quantum dots and go to the level of a single quantum dot graft to a nanoparticle. And that will bring me to the second part of the talk. We're also interested to graph functional material that could be used for sensing application. So the idea was really to try to couple these nanoparticles with what we call molecularly imprinted polymers. So these synthetic materials can really be considered as plastic antibodies, because the idea is really to mimic natural antibodies that you can find in the nature by replacing the amino acids by synthetic monomers, because you can find in this vinylic monomers the same kind of functional groups that you can have in amino acids. So the idea is really to build polymer that can have the same recognition function as proteins in the nature. So for that, what we do, we start with a template molecule that, for instance, I will show later examples. So usually it's an organic molecule. We bind this molecule with functional monomers to create a complex, and then we make the polymerization of this molecule around the molecule. And because we use reversible bonding between the molecule and the polymer, we can, at the end, extract the molecule and giving rise to the imprinted polymer, which is really a polymer with imprint at the nanoscale, at the molecular scale of the molecule that later we want to detect. Okay? So in this polymer, we really have this molecular imprint that will capture the same molecule if we are in contact again. So we can make this polymer, of course, by thermal processes, but coming from photochemistry, we adapted the process to make them by photochemistry. And of course, the idea later was to try to use the near-field photopolymerization to couple this material, this MIP, to nanostructure. So we did exactly the same as I shown before. So starting from metal nanoparticles covered by the photopolymer, we shine in conditions for which we can have only the optical near-field photopolymerization, so no near-field polymerization. So with that, we can really graft a very thin layer of the MIP, and at the end, we can rinse to remove the template molecule from the polymer and end with nanoparticles with this molecular imprint. So in this example, we started with methylene blue because it's very easy later to make SERS measurement and characterize the rebinding by SERS. We have this peak that is clearly correlated to the concentration of the methylene blue that we have in solution. So with the CERS measurement, we can really measure the concentration of the methylene blue molecule that we have in solution. So because it's a synthetic polymer, it's a robust material, we can reuse it. We can, when it is rebinded, we can regenerate it. It's a quantitative monitoring, and we can have a specific response. For instance, we tested with some other dyes, and we could demonstrate that we have the response only for the methylene blue. But okay, for this kind of sensor, you need CERS. So we're also interested to shift to some maybe more simple way to detect the molecule. And for that, we shift to SPR. So the idea is really the same: to use the near field photopolymerization, but to functionalize in that case not nanoparticles but metal films. So I will not talk about the Christmas configuration, but just to show you an example about another configuration that we have been working on that is based on an optical fiber. So the idea is really to have a D-shaped optical fiber on which we have a metal film, a very thin film, that we can excite through the light that is guided through the fiber. So the idea is really, again, to use the near-field photopolymerization to prepare, in situ prepare the MIP film, okay, by the light that is driven through the fiber. After we develop everything, so we end with this molecularly imprinted polymer film that is directly inserted at the edge of the fiber. So this is a picture of the small device. So what is really nice with this process is that we can really tune the thickness of the layer by changing some parameters like the irradiation time or the power, and we can change it and adapt it from 30 nanometer to 41 nanometer. So it's really very easy to tune this thickness. And then to demonstrate the interest of this approach, what we did was to try to make the MIP for a template that is the PFOA. So PFOA is one of the worst of the PFAS molecule that we can find in the water and in the environment everywhere. They are called, well, these molecules are so stable that they are not removed, they are not destroyed, so they are really accumulate in the water, in the field, and even in the air. And the problem now is to be able to have some devices that could make the measurement of this molecule at the same time in a specific way, but also to be selective enough that the device could make the measurement in the field directly and to give a very quick response. So we prepared the MIP for this molecule and use this configuration. So to polymerize on top of the metal film and after to try to detect the molecule. So the measurement is just taking a drop of solution and put it at the surface of the device. And we could really show that by monitoring the spectral change, the shift of the resonance of the SPR that we are exciting in this configuration, we can really then make a correlation with the concentration of the PFOA molecule that we have in the solution, and we can go to very low concentration in the sub-femtomolar range, which is much more than what we need. Also, the interest is that because we can change the thickness of the film very easily, we can also change the range of the concentration that we can address, and we can see it more clearly here. These three ranges are corresponding to different thickness, from 30 nanometer to 41 nanometer. Today, the regulation for the drinking water, for the water that we use, is there. So we are really in the middle of the regulation for the thickest device. But as we show here, if we decrease the thickness of our layer, we can really go to much higher resolution, which is a way to detect the PFAS in a much more advanced way in some environment or in industrial processes. And also what we wanted to show is that because we are using MIP that can be seen a little bit like this toy for children, we wanted to demonstrate that this sensor can be selective to only the molecule that we are using, so the PFOA to make the template, and that was actually the case. So I cannot go into details, but we tested in competition with this molecule. So it's the same molecule, but with less carbon atoms, and also we changed the polar head of the molecule, and we could really show that we in this case we really have the response for the template molecule in the femtomolar range, but no response to the analog molecule. So this is really something that is interesting, because even with 100 times more concentrated solution of the analogs, we could not detect them in the medium. So now we patented that, and also now we are really starting to try to work in real life samples with all the problem that comes with real life samples. I mean, the interference, salts, pH, and so on. And we are really hoping that we can make industrial device very soon with this technique. And just to illustrate in the last slide, the interest of this approach is that we can really tune the material by changing the template and then address other molecules that we want to detect. For instance, we had some very promising results with S-propanol, and in that case, what we tested was the specific response to the two enantiomers, and we really could show that we have a response to the enantiomer with which we make the template, and not the response to the other one, even with 100 times more concentrated solution, and also more in biological application. We also could show that for the testosterone, we can have the same kind of sensitivity in artificial saliva, showing that we can really go to a practical application. So with that, I will just conclude my talk. So I hope I managed to convince you that we have here a very nice tool to couple polymer with metal nanostructure, not only because it's simple and versatile, that can be applied to many different materials, but also because it's very efficient, because we are using the optical near field to create the material. So we really put the functional material exactly where we need it for the latest application. And it's also, for us, it's really a great configuration to investigate the photopolymerization at the nanoscale, and that will be the objective of the Sunrise project from our side. And with that, I'd really like to thank all the people who participate to this work, and especially Céline, Amin, and Abdallah, who will be the PhD student that will be in charge to continue the work. With that, I'd just like to thank you for your attention and be happy to answer some questions.
Okay, so we have a few minutes for some questions. Yes, Majid.
Thanks for the nice talk. I was wondering, why do you use gold nanotriangles? There are identical silver nanotriangles with much sharper edges, i.e. higher fields, and it's cheaper.
It's cheaper, but what we like with gold is that it's quite stable. And we don't really bother about the oxidation and the possibility to have silver oxide around the particle. So that's why we like gold, but we also play with other metals, yeah, of course, yeah. Thanks.
Thank you, Olivier, for the bright presentation. Actually, you showed very well this monitoring, sensing with your systems for PFAS or PFOA, for example. Is there any way to take advantage of photochemistry, not only for detection, but actually photo degradation at the same time, or something like this?
That's something I already had in mind, because you could have a way to immobilize very specifically one molecule and then use the plasmon to try to destroy it. My only concern is to keep the polymer alive and not destroy also the polymer that is still an organic material. So you have to find a way to specifically kill the molecule that you have captured without damaging the selective layer. There are also some work, people making MIP with inorganic materials, or with sol gel materials, for instance, that could be, definitely.
Polymerization,
or just for the, sorry?
The surface enhanced Raman scattering detection.
Actually, we are using for both. So we really need the gold structure to help us to make this nano layer of functional materials. But at the end, we are using also the gold nanostructure to have the and
because in this case, I'm wondering about the 40 nanometers thickness of the polymer layer, because in the 40 nanometers, you don't have, let's say, enough distance for the field enhancement.
Okay,
gold film.
but that's typically the reason why the thicker MIP film will give the less sensitivity, because in that case we have more imprints, so we don't saturate so quickly the material, but then of course it will be less well coupled to the metal, so we have less sensitivity, and that's really by playing with this. The film thickness, we can really then adjust the range of concentration that we are addressing at the end with the sensor. I don't know if I respond to your question, but
yeah, perfect. Thank you.
Thank you for the very nice presentation. My question is about your methylene blue SARS probe. I wonder if your methylene blue still retains its photo-oxidizing, radical generation ability while it absorbs in a particle, and if there's some way to use it.
Sorry, I didn't get. So for the methylene blue, what you mean? Yeah.
It's a photosensitizer,
yeah,
so
okay,
it can generate single oxygen and radicals. Does it still do it when it's absorbed on the particle? And if there's some way to use it?
I don't know, because as soon as we put it inside this polymer shell, we just remove it and then absorb it again. So I honestly, I don't know. Maybe, yeah.
Thank you for the talk. I was very curious about the results that are very low concentrations. Can you comment a little bit on the timescale of the response of your sensors?
Yeah, I didn't mention that, but usually we have a kind of saturation after only a few tenths of seconds. We didn't optimize at all this parameter, but it's quite quick if we compare to some other configuration that we have with MIP. So what we believe is that when we go to the thinnest layer, we don't even have the time for the diffusion inside the film. Most of the imprint should be really at the surface. And so the equilibrium is done, very quickly with even very few molecules. But at the lowest concentration, we start to have some question about the time that you need to have enough molecules to riding. Yeah.
Thank you.
So we will thank again Olivier. And now it will be the short presentation of the moonshot sunrise done by Nathalie and Dario.
Thank you very much, Valérie. Before I begin, I'd like to express really a sincere thanks to all of the LUMA governance for putting together this beautiful days, giving us photosciences, what a great stage to be able to showcase all of our results and experiments. So thank you very much. So we have a moonshot project that's co-coordinated between myself and Nathalie. We have a team composed of 7 partners. These are located in Bordeaux, in Paris, of course. We have 2 teams, as well as in Saint-Étienne, Lyon, Mulhouse, from which we just heard of from Olivier's group, as well as more recently in Marseille. The project has to do with improving photochemistry. Now, in photochemistry, we have since a long time, like in practically every area of science, right? We have certain dogmas, these truths that we use to kind of guide our trains of thought of how we see photochemistry and experiments. And some of them are actually very old, like, for example, the law of photochemical equivalence by Albert Einstein and Stark, which simply tells us that one photon gives us one photochemical event, which kind of stands to reason, right? We also know since over 100 years that resolution using light is limited by the diffraction to about 1/2 of the wavelengths. This is the Abbe diffraction limit. And even before that, Grotius told us that how much photochemistry we have actually depends on how much light is absorbed. Now, all of these principles are really rooted in our thought, and they help us guide how we see experiments. But when you think about it, they also limit how we see photochemistry and experiments. And when you, of course, understand that these laws of physics cannot be changed, they have to be respected here on Earth, anywhere in the universe, today or in the future. But nonetheless, thanks to advances in technologies, now we see them differently, and we can actually go beyond that. So we don't break these laws, but we somehow twist them a little bit, and we manage to go around them and circumvent them. So now we can use singlet fission to be able to generate 2 events from one single photon. Okay, less energy, but still 2 events. We can use, of course, super resolution imaging, and we'll hear about some of that from Marina's talk later this afternoon, to be able to see things incredibly detailed, like we've never been able to see them before. And as we just heard from Olivier, we can't change the way molecules absorb light, but we can change the way they interact with light, and we do that with osmotic interactions. And so the idea of our project is really to combine all of this and use this to improve how we can do photochemistry and how we see photochemistry. So the goals of the sunrise, of course, improve photochemical selectivity, activate inert compounds, like we heard maybe about the PFAS, exploit plasmonic interaction to control excited states, and then go beyond the resolution that's limited by light for this on large scales and apply it to things. So the project is, of course, divided in work packages. I'm not going to go into much detail because Nathalie will tell us a little bit more about our recent projects, so progress in this field. We have basically 4 main scientific work packages. The first one is oriented on the synthesis of the nanoparticles. This is done by Stéphane Parola's group in Lyon, in collaboration also with Olivier. We also have approaches to going beyond diffractive nanolithography using additive or subtractive photochemistry that's done at the PPSM. At the same time, we can do, or we will be able to do, single molecule polymerization like we just heard about, and then also go to plasma-coupled triple up conversion, thanks to some work by Antibuides in Bordeaux. We have, of course, the idea to put all of this together and try and do something that is practical. So we enlisted the help of Florent Maloggi at the CEA in NAM, and together with Nathalie's group in Saint-Étienne, they're actually going to apply the fabrication of these nano-resolved structured materials on large scale to be able to do photochemical transformations. So we could, of course, continue going on and telling you about the project, but we thought you might be interested to hear a little bit about the science. And so Nathalie now is going to tell us a little bit about the recent progress that we've had over the last year in the
Thank you, Dario. So actually, maybe you noticed some arrows on the graphs, and some of the work package I've started last year, not all of them, so like this one, so I will not speak about the WP4, but now we would like to highlight some of the results, the main results that have been obtained within the Sunrise project during the year, and especially, so first in work package 1, so the work of Stéphane Parola is actually well, so the team of Stéphane Parola is actually well skilled for producing many kinds of metallic nanoparticles with anisotropic shapes, chiral properties, and also functionalizing them and including them in glasses also. So here we would like to highlight a result that has been produced with these bipyramids, so bipyramids gold nanoparticles, coated with gold that have chiral properties, and they actually collaborated with a team, with 2 teams in Brazil to produce a random lasing experiment. So in that experiment, we use a coupling between these chiral plasmonic nanoparticles with dyes, especially rhodamine 6G. And so this is mixed within a solution containing scattering nanoparticles, here, so titanium dioxide nanoparticles. And what they observed is
so the emission of circular polarized light with a very high degree of circular polarization, especially compared to the fact that the chiral molecules do not have a high dissymmetry factor. So this works led to an article that is now submitted. And the same team, and still in WP1, also studied the influence of the position of the emitter surrounding these chiral nanoparticles on the emission of circular polarized light. And for that, they surrounded the nanoparticles with very well-controlled layers, about 1 nanometer thick, produced by different layers of polyelectrolytes. And by controlling that, they could observe that there is an optimal distance at which the emission of circular light is obtained. And what is interesting there also is, this work was carried out during an internship project of M2 students, and this M2 student actually got a PhD position in the Tornado moonshot project. So this is to show that there are also cross-fertilization between the different moonshots. So here I will go fast because actually you have already seen that. So this was the first article within the Sunrise project where the team of Olivier Sopera working with the team of Stéphane Parola demonstrated the fact that actually local plasmon-induced polymerization could occur, and especially they highlighted the fact that it was dissymmetrical in that case due to the fact that one edge of the bipyramid is placed on the surface and the other one is just in the air, so producing different kinds of polymerization on both sides. Now, so it's not WP3, but it's WP2, sorry, so for the 2 next slides. The team of Vitor Brazilians actually worked and focused on identifying photocage catalyst for localized ring opening polymerization of biosource monomers into polyesters. And when doing that, actually they also monitored in situ the reaction of polymerization, and they identified that there was different action speeds of this polymerization, and also they could highlight some unexpected mechanisms like bubble formation. They used also different inline characterization techniques like UV visible spectroscopy and liquid chromatography, mass spectroscopy, to identify the uncaging of the catalyst, or also identify different intermediate species in the reaction. And what is interesting also, they collaborate with the group of Institut Fresnel now, so to study in situ using quantitative phase imaging the polymerization process, so they can detect very low amount of polymers directly forming on the substrate. And in that case, by following in time the process, they could optimize the process and select the right concentration of monomers in the solution. And so specifically on this phase quantitative imaging technique, so led now by Pascal Berthaud, who has moved at Institut Fresnel this year, actually they try to improve the sensitivity. And to do that, they especially use spatial filtering on the setup that actually allows to balance the continuous background with a scattered field, and this allows to improve significantly by typically 1 order of magnitude the sensitivity on the phase measurements. So this allowed for optimizing experiments, for collective experiments, and also to probe in operando the polymerization around the plasmonic nanoparticles, detecting really the formation of a nanometer thick layer of polymers, so very sensitive technique. So, and to conclude, because I'm already late, sorry, just to say that actually we hired only 1 PhD student in Sunrise from the beginning of the year, with the funding of Sunrise, but we work also with 2 other PhD students who were hired through supplementary fundings, also working with M2 students, and now we are growing more and more, so from 1 month, with a new PhD and postdoc student joining the project. So thank you very much for your attention. There is no question.
Yeah, no questions.
No time for questions.
Okay, we can switch to the last session that is dedicated to the platform of Operando. And as in charge of the project, I will do a short introduction, in charge, in fact, with Pascal d'Oliveira previously, and now with Jean-Philippe Renaud. I will do a short presentation. It was already scooped by Rémi partially, but just on the role, on the objective, on the goal of this platform, and we will get few presentation to illustrate a few of the platform, and obviously you have the poster session that you can look and you can discuss with the people in charge of the platform. Just in this project, there's something in this PEPR, there's a E that corresponds to equipment, and that was a very nice opportunity, what is not very often the case, to have money, large amount of money to invest in platform that can be very important for your research. And we have tried to work on this to define a large platform that can survive after the PEPR if it's really answering the scientific question that you need. And we have identified a few challenges that are important for the community that are listed here, and the one on the bottom correspond to mainly the Operando. But I should mention that Operando and Ultrafast are working exactly the same. It's just a limit that we have to define to write the project, but it's really a continuum between the 2 platforms. And if I try to describe quickly the platform, I can try to describe as a 2-part. One is to characterize, the goal was to characterize the matters under illumination, and we have in fact included all the up-to-date or state-of-the-art technique that you can use in your research with STEM, EPR, NMR. All the technique that you need are introduced in this platform, and also some other that transform the matter under illumination that are also in this large hub platform. I think we have tried to do our best to select the platform. You see all the list of the platform of the Operando platform that are distributed in France. And I would like to mention also it's not only very up-to-date material, but it's also a competence and speciality of the people that can help you to develop the project with you. And that's very important also that we have selected the people that can contribute to your research by giving you the good advice. And the contact is Pierre Dufour that is on the first line. And just to be short, what we have achieved at the moment for this, it's at least we have used this money to start new equipment, updating equipment, and we have 15 operations that are realized already or in progress. That it was a big challenge to put this and start this. We have some human resource where we have hired 5 engineers that will help to set up the state-of-the-art equipment to do new experiment, new stuff that you need for your research. And we have access fees that are important for the platform, because the platform, as Rémi mentioned, it's free for the users. And also we can pay for your travel. That means do not hesitate to go to this platform. It's very important for your research, but it's also important for the future of this platform to prove that it's very important for this field of the research. And just quickly, the flow to have access to this platform is the classical flow that you can find in the infrastructure with the criteria of access that are defined on the bottom. But I would like to mention also that the feasibility are done by the people in charge of the platform, and that's very important that you can discuss with them if you have any doubt on what you can do, or do not hesitate also to potentially submit a first project, but also discuss with them to improve your project, and they are there to help you to create some new potentially experiment or new result, and that's really a network of stuff. Okay, it's open to everyone, not only the people that are included in Moonshot or project, as Rémi mentioned. And just to illustrate, obviously you can take time to have a look on the poster and discuss to the people in charge of the platform. That's very important. They can give you some advice and explain what they can do for you. Maybe you don't imagine what they can do at the moment. That means try to discuss. And we have selected two talk of people in charge of platform to show you maybe two platforms that you don't know so well. And also one talk of user to show you what you can expect to do in this type of platform. And I called the first speaker, Anthony Beauvois, for Soleil, and he will explain the photocatalytic reactor for X-ray spectroscopy.
Thank you. Good morning, everyone. So I am Anthony Beauvois from Soleil Synchrotron. So Soleil Synchrotron is itself a national platform with a large portfolio of techniques, including diffraction, scattering, spectroscopies from infrared to X-ray. But in the framework of the Operando platform, we mainly focused on, not this one, sorry, this one. We mainly focus on X-ray spectroscopies and photocatalytic reactors. Our aim in the framework of this platform is to understand the lifespan of a catalyst under working condition. So to do that, we need the reaction condition. So it could be gases distribution system, of course, light sources for photocatalytic, and also eventually potentiostat for photoelectrocatalysis. As we want to progress operando measurement, we need also to measure the catalytic activity, so using, for instance, mass spectroscopy or gas chromatography to monitor the gases that are formed during the reaction. And finally, we need the X-ray spectroscopy to answer the question, what are the active seats, the active species of the catalyst? Why does the catalyst deactivate if it deactivates during the reaction? But the objective, the aim was to develop reactors that allow to perform these three parts at the same time, meaning reaction condition, catalytic measurement, and X-ray spectroscopy measurement to perform real operando measurement. So the objective was to design specific cells or reactors that are suitable for the measurement, X-ray spectroscopy, to apply reaction condition, and to measure the catalytic activity, reproducing the same activity that we can observe in reactor at the lab. This is really important for us to be sure of what we are looking at. So in this framework, in this platform, we identified 4 specific beamlines that are represented here as a function of the energy range they cover and the time resolution they can provide. So we have Hermes beamline, Lucia, Samba, and Rock beamline. So as you can see on this graph, there is a good complementarity of these beamlines that allow to cover or to study specifically. This is the aim of X-ray spectroscopy, as was explained by the first speaker this morning. So with this complementary beamline, we can probe up to 82 elements of the periodic table from the boron to the lanthanide elements. And in LUMA, we have an engineer that was employed at Soleil to develop specifically a cell for the Lucia beamline. The Lucia beamline works on soft, tender X-rays. So it's a primary vacuum environment, so it needs specific cell that allow to work under vacuum. So we developed these types of cell that allows to perform photoelectrochemical reaction. The cell here is in the vacuum vessel. So it has been validated from the chemistry point of view. So here we have the appearance of a photocurrent with titania, oxide titania. And very first results were done for the photodeposition of cobalt. And here we see that the cobalt is oxidizing with the movement, with the shift of the white line to the higher energy. So that's very first results that were done on the Lucia beamline. And now this cell is available for the community, for all the community who wants to perform such kind of experiment. But this is not the only cell. We have other also cells. For instance, these types of cell on rock beamline. So rock is a hard X-ray. There is no the vacuum bottleneck on the beamline. So here is a gas phase cell for photocatalysis that is available and open to the community for photocatalytic measurement, and we can provide X-ray, UV visible sources. We have potentiostat. We have also the mass flow controller, the mass spectrometer, sorry, or the gas chromatography to follow the gases that are formed. And all this equipment is available for the LUMA community, and especially in September 2025, a project has been performed on Lucia beamline using this cell. I don't have the results now because the beam time was done just a few days ago, but just to tell you that there is some project that can be done. And for the Soleil, there is, of course, as it is already a national infrastructure, to have access to this infrastructure, you have to use the Sunset. This is the portal from Soleil. So this is a 2 pages proposal, and there is 2 calls per year with a deadline around mid-September and mid-February. So the proposal will be evaluated and accepted or not by Soleil peer review committee. And so I encourage every people who want to submit a proposal to contact me so that I can guide them to the good beamline, and we will help them in the dimensioning the experiment for this specific for the proposal.
Okay. Maybe just a short question, if you have one. If not, you can discuss. There's a question.
Thank you. I just wanted to clarify for the proposal, it means that we need to specify the platform when we put the proposal, and then the beam line will be decided after the proposal is accepted, or is it just a part of the regular proposal?
No, it's part of the regular proposal. You should contact me, or if you already identify the beamline, you can contact directly the good beamline. But the best is to contact me so that I know the proposals that are submitted in the framework of LUMA. And something I didn't mention here, sorry, I forgot that. In the title of the proposal, when you submit it to the platform, in the title, start with LUMA. LUMA, sorry, and I don't know. And the title of the proposal so that we can put this in the LUMA framework, I would say.
Thank you.
Okay, we can continue with the, Thanks again. And we can continue with the next talk that will be presented by two persons.
Yes, thank you. Okay, so we are presenting the PhotoVivo platform, which gathers optical methods for the characterization of biological tissues, and our research works are dedicated mainly to cancer diagnosis, but of course we can definitely adapt to any other application, which we already have, of course, as we'll show you. We have several optical and spectroscopic devices that we will not have time now to present, but feel free to come see the poster to talk about some equipment that may be useful for your works. We have unique and highly innovative devices, such as, for instance, the spectral radiometer that we may use in case you need to measure the biological safety of innovative devices that you may develop in your own laboratories. Like, for instance, we develop medical devices and we need to make sure that they are safe for the patients and for the physicians that use them in hospitals. In clinical trials. We also have a quality management system, which my colleague is in charge of. And today we are going to focus on 3 specific devices. One optical imaging device that is based on the LCOCT method, I will show you right after. One optical spectroscopic device that we developed and patented for autofluorescence and diffuse reflectance measurement. Those are applied to skin cancer diagnosis. And an optical bench for absorption, scattering, and anisotropy coefficients measurements that my colleague developed and that she will present now.
This device is an optical, the dual integrating spheres setup developed by our team to estimate the optical coefficient of biological samples as a function of the wavelength. So it's an absorption coefficient, the scattering coefficient, and anisotropy factor. The measurement bench consists of a supercontinuum laser emitting from 440 to 2000 nanometers with 2 integrating spheres and several detectors. To ensure an appropriate optical path length, the samples is about 1 millimeter thick and its diameter should be greater than 6 millimeters. So the sample is placed between the 2 integrating spheres, so here, and the laser beam passes through the sample and allows us to measure the light intensity received by the photodetectors. And in order to obtain some information, 2 information, the transmittance and the reflectance. The transmittance, which is a part of the light scattered by the sample into the second sphere, and the reflectance, which is a part of the light reflected by the sample into the first sphere. The data is acquired with interface users that we developed also. To estimate optical coefficients, we use inverse problem-solving algorithm based on inverse add-in doubling method developed by Scott Prall. We have already performed some various types of biological samples, solid and liquid, like porcine blood, kidney stones, intralipid solutions, and live and dead yeast cells. So on the graph, we can see absorption coefficient spectra for different levels of oxygen saturation of hemoglobin, which we were able to measure with this setup.
I can propose also a focus on 2 other devices. So the first device that we have available for the community, just like all other equipments, is an imaging device based on LCOCT that was developed and patented by the French company based here in Paris, Damae Medical. It allows a 3D imaging of skin tissues with a 1 micron spatial resolution. So like you can see, you can detect the cells directly in vivo on patients. And so we can use this during clinical trials. And the aim of a project that is currently finishing has been to evaluate the interest of combining this device by the Damae company with the spectroscopic device that you can see here in a surgery room at the hospital in Metz. That is based on spectroscopy to measure autofluorescence and diffuse reflectance, because we know that we have fluorophores inside the skin tissues that are modified with cancer development. So we base our diagnostic criteria on the measurements of such fluorescence. And here you can see the different spectra of different classes of skin cancers. Thank you for your attention.
Time for a question.
Yes, I think it's working. Thank you very much for the presentation. And do you think, it's a very naive question probably, especially your tool you mentioned with this double integration sphere, and so wouldn't it be useful for samples which are not always biological,
of course.
Always for medical applications?
Definitely. We may characterize any type of sample, like we are part of the health topic of the PEPR program, but we may adjust to any type of application. So we were already contacted by people who do nothing related to health or biology. Yes,
okay,
of course.
Okay.
Yes, as long as it is transparent enough so the light can go through it.
Of course.
And can go through the sample and get some light absorbed, but detected by the second sphere, and some light that is backscattered if it's of interest.
Yes, thank you.
Thank you.
Okay, another question, or that's fine? Okay, let's switch to the last talk of the morning before the lunch. And where is the speaker? Oh, sorry. Okay, a user that will present his experience on one of the platforms. Okay.
Thank you. So thank you for giving me this opportunity to talk about my experience. So I'm Christian, and I'm a doctoral candidate from IPCM in Sorbonne. And so how I'm working with Guillaume is in Anna Proust, and we're studying basically photosensitization of polyoxometalates. And so we contacted and we partnered with LCBM in Grenoble to do some photoelectrochemical measurements on this system. So what we wanted to do is to see whether the photosensitization phenomenon that we were studying can be exploited and integrated into photoelectrochemical cells. So we contacted Muriel, Vincent, and Jennifer, and of the Sol-HiCat team, and to show us basically the know-how of preparing these systems, so preparing nickel oxide films and how to sensitize this film, so by grafting these dyes that we develop in our lab, and how to do some photoelectrochemical measurements, such as photocurrent measurements and also voltammetric measurements. And so this is just to show the kind of setup that they have in LCBM. So they have this in-house electrochemical setup that is also equipped with they're also equipped with a light source that is capable of doing some automatic shutting on and off that allows us to perform chopped light photocurrent measurements, such as these figures that you see right here. And so these are the kind of data that that we got, and they also showed us how to quantify the quantity of dye into the nickel oxide film. So the idea why I did this is to learn how to do these things and to perform them in our facilities here in Sorbonne. And so in the end, it was very successful. So, well, this is just a last slide showing like one of the kind of data that I got. So it was just a short-term stay, but they were able to show us the things that we need. So here in our laboratory, we're able to carry out the same experiments and use the data for my project. So.
One question for this last talk. See, nobody. Everybody wants to switch to the lunch. Okay, we can thank all the speakers of this session. And enjoy this break to have lunch and also have a discussion with the posters, people in charge of the poster. Sorry. Back here at 2, okay?
Okay, thank you for coming back on time. So we will start this afternoon session in a timely fashion. And we're incredibly excited to have Marina Klimova that's going to deliver a keynote lecture this afternoon. So please give me a couple of seconds to introduce her. Marina did her undergraduate studies in Russia and then went to the University of Nottingham in the UK, where she did a PhD with Michael George, studying the electron transfer in DNA in metal complexes. She then moved to Imperial College, where she was working with David Phillips, also doing transient absorption spectroscopy at the time. Imperial College obviously realized they had someone that was really special because they kept her all after that. And that's where she continued working for the rest of her career, and she's now a full professor there. I asked Grok to come up with 2 or 3 sentences to describe Marina's work to us, and asked him to do it for a 12-year-old student. And so here's what Grok has to say about Marina's work. So he says that Professor Marina Klimova is a smart scientist who studies tiny things inside living cells, like how thick and sticky the goo is that surrounds our body's building blocks, kind of like checking if honey or water flows better in different spots. She uses special glowing tools and cameras to take quick pictures of these hidden spots without hurting the cells, helping doctors figure out why the sicknesses like cancer happen and how new medicines can swim through to fix them. Her cool discoveries also help us learn about big problems like how pollution in the air changes the weather. So I think with that, we know all about what type of work she'll be presenting to us, and please join me in welcoming Marina for her speech.
Thank you very much, Dario, for this very kind introduction. I should ask Google or ChatGPT to write my proposals for me. I think I'll get much better success rate. Well, it's an absolute pleasure to be here. And I was really, really impressed by the breadth and the depth of the activities as you have as part of the PEPR LUMA. You'll see from my presentation that my work aligns, I think, mostly with the themes of health, but also characterization of photochemistry and material sciences. I'm hoping that there will be some slides, otherwise I'll have to do chalk and talk. But let me continue talking and tell you that we are mostly interested in using fairly sophisticated microscopy and spectroscopy techniques to learn about the biological processes within cells. So we use fluorescence lifetime as the main readout of the behavior of our molecules. And we try to apply it to a large range of problems, mostly to do with diffusion within cells, but actually covering a large range of different problems. So my talk, I hope, will be a little bit like British weather. You know, every few minutes it will change, right? So if you're listening to what I'm saying and you don't really interested or you don't like it, just wait for 10 minutes and hopefully it will, you know, the next topic is going to be better. But I do need my slides, I think. The slides here, but they do not project. Oh, fantastic. Great. So, as I said, we are extremely interested in using microscopy and spectroscopy to look at the diffusion control processes within cells. So, for most of you in the audience, that diffusion and viscosity is really, really important. You know, cells are extremely heterogeneous environments. There are lots of different organelles. Most of these organelles are then surrounded by lipid bilayers, the very hydrophobic border kind of control structures that then separate the organelles from essentially aqueous phase of the cell or cytoplasm. So in this complex system, perhaps it's not surprising that viscosity plays a large role in processes such as bimolecular reactions and signaling and diffusion. There's also really good body of evidence in the literature that abnormal viscosity is linked to disease and malfunction, both on the single cell and the organism level. So to us, this meant that trying to learn about hydrodynamic properties of cell environments is really important to understand the role of viscosity in disease and malfunction. But actually, looking at viscosity on a single cell and organism level is really tricky, because the cell organelles are tiny, and traditional mechanical ways for measuring viscosity will be very destructive, and also they'll require large amounts of material. So, of course, there are lots of techniques that are spectroscopic that have been developed, shown here, that use the length scales of individual organelles to try to probe diffusion control processes within cells. So you'll recognize most of these methods, perhaps, monitoring diffusion-controlled photochemical reactions that are viscosity-dependent, or FRAP or FCS, so recovery after photobleaching, or correlation spectroscopy. But all of these methods, when we started looking at them, we realized that they have two major limitations. First limitation is that these methods mostly measure things in single points instead of providing us the full image, the full picture of what happens within cells. And second limitation we identified is that most of these methods, they require the measurements to be acquired over time, several points, and then processed to produce the viscosity value. And that means that you cannot measure viscosity in real time, just as the process of biological importance occurs. So what I hope to show you today, that our method, that is based on fluorescence detection from molecular rotors, overcomes both of these limitations. And we can get good spatially resolved pictures, and we can do it fairly fast. So if we want to, we can monitor dynamic biological processes that occur and cause changes of viscosity. Okay, so what are molecular rotors? They are small synthetic fluorophores in which there's a large degree of conformational change that occurs in their excited states. And this is extremely important because this conformational change, such as internal rotation, leads to a depopulation of the bright excited state and brings it to the dark, non-emissive state. So, if our rotors are in a non-viscous environment, shown here by water, they rotate very, very fast. The dark state is being accessed very efficiently, and as a result, you see very small amounts of fluorescence. However, if we place our rotor in a confined or viscous environment, the rotation doesn't happen, and then the dark state is not efficiently populated, and you see a very large increase in fluorescence as a result. So, listed here, there are several groups of molecular rotors that we investigated and discovered in the course of the last 15 or so years. But before I move further with describing how we use rotors, I really need to discuss the fact that fluorescence intensity is not a concentration-independent parameter. So you can put your rotor in a heterogeneous system, and then the intensity of your signal that you record does not just depend on viscosity, it also depends on how much of the rotor you have in a particular organelle within your system. And this is not good enough, because in something like cell, we have no good way of determining the concentration of our fluorophore. So what we need instead is some kind of ratiometric approach that takes this concentration into account. And we suggested just such an approach based on the fluorescence lifetime. So fluorescence lifetime is a characteristic of how fast the excited state decays back to the ground state. And this is concentration independent in the absence of quenching or self-aggregation. And just like fluorescence intensity, fluorescence lifetime increases in a very steep upward curve as we increase the viscosity of the environment. So we first discovered it for this particular molecular rotor that is based on the Beau-Dupuy structure. And our Beau-Dupuy is quite special because it has a phenyl group attached to the fluorescent core of the Beau-Dupuy, and the phenyl can rotate. And as it rotates, the dark non-radiative state is being populated. And so in a non-viscous environment, the intensity and fluorescence lifetime are very short. However, if you increase the viscosity, the lifetime and fluorescence intensity go up. So you can build a calibration plot, in a way, by measuring fluorescence lifetime in solutions of known viscosity, such as methanol glycerol or toluene castor oil or lipids of different composition of different temperature. So what is plotted here is the lifetime as a function of viscosity, and I plotted it in a so-called Förster-Hoffman plot, where it's a doubly logarithmic coordinates. And you can see that this plot for our Bodepi rotor is linear dependent, so it means it corresponds to a power law in a very large range of viscosities, so from 10 to several thousand, in fact, centipoise. So we think that our rotor will be suitable for measuring viscosity in biological environment, because biology, we hope, operates somewhere in between 10 and 1,000 centipoise. But of course, you can modify the rotor structure or invent different types of molecular rotors that measure either lower or higher viscosity, if you, for example, had an idea to apply it to material sciences, where viscosities are in a different range. Okay, so one really important thing is that fluorescence lifetime is something that can actually be imaged in a very precise, spatially resolved manner, using a fluorescence microscopy technique called FLIM, fluorescence lifetime imaging. So in FLIM, we essentially use the pulsed laser excitation from a Ti-sapphire or a diode laser, depending on what type of microscopy we're doing. And then we use single photon counting to detect time-resolved fluorescent decays in every single point of our image. So it's a bit slower than confocal or wide field imaging, because we have to build a fluorescence time-resolved histogram in every single point of the image. But then as a result, you can fit the data using multi-exponential or mono-exponential decay, extract the lifetime, and of course the lifetime unequivocally corresponds to a certain viscosity. So this way you can create maps of viscosity in cells, in tissues, in heterogeneous materials, in aggregating proteins or polymerizing systems, you name it. Okay, so what do we do in my group? We look at the structures of molecular rotors, we create new structures, we collaborate with others that can provide us new molecular rotors. And then we characterize them and try to apply them to a large variety of different problems. And today I'm going to try to concentrate on our efforts in probing viscosity and conformation in biological type of systems. Okay. So our first goal when we sort of invented molecular rotors was trying to look at viscosities of those lipid bilayers. So the plasma membranes and internal organelle membranes that are surrounding organelles in cells and providing a really important permeability barrier and defining mechanical properties of cells and tissues. So for this, our Bodepi rotor is particularly perfect because it basically has the right lipid-like hydrophobic structure that it seamlessly incorporates in lipid bilayers or monolayers. And then we can record fluorescence images, and I'll emphasize again, instead of just looking at intensity, in every single point of this image, we record a time-resolved fluorescence curve, and then by fitting this curve, we can assign the lifetime. And when you see in the image the sort of artificial color scale that shows blue lifetime, it means you're dealing with low viscosities, and you can assign the actual number to it. And if you see red areas, then it means that you're dealing with high lifetimes and really high viscosities. Okay, so it's a quantitative method. Okay, so then we took our molecular rotors and said, well, great, wouldn't that rotor incorporate into the plasma membrane of the cell? And then we can measure the viscosity of the plasma membrane as it depends on different environmental conditions, including treatments such as cancer therapy. But unfortunately, our first design of rotor decided to behave completely different, because cells are sometimes a bit like little children. So these cells decided to take up our rotor and internalize it. And instead of staining of the plasma membrane, we see a staining of individual hydrophobic organelles, which are lipid droplets within the cell. But still, it was really useful. It was the first result that we obtained with rotors. We recorded time-resolved decay of rotor that gave us a lifetime of about 1.6 nanoseconds, which, according to our calibration graph, corresponds to a very high viscosity of about 140 centipoise. So we know for sure that our rotor is not in the aqueous phase of the cell cytoplasm, which is about 1 centipoise. But instead, our rotor is in those lipid-like bilayer domains within the cell, which have really high viscosity and low diffusion. And we can corroborate it with alternative measurements, such as diffusion-controlled reactions or fluorescence recovery after photobleaching, or FCS. But now back to the drawing board, right? We still want our rotor that stains just the plasma membrane of the cell. So to achieve this, we can modify the structure by keeping the functional part of our fluorophore intact, and instead modifying the phenyl group with different substituents, such as cholesterol, or this doubly positive charge through coordinated amino groups that essentially acts as a stopper, right? So the charge prevents the probe from internalization inside cells, and then we hope that this will allow it to stay in the plasma membrane. I should say also that for all the three rotors, we know from molecular modeling that even though the structure is a little bit different, and that determines their different localization within the lipid bilayer, their active rotating group is still in the same place, and so in model lipid membranes, they still measure exactly the same viscosity, which is shown here as a function of temperature. And importantly, if we mix our lipids in the right proportion of DOPC, DPPC, and cholesterol, so these are the three model lipids that probably make most of the living organism membranes, then we can have phase separation. So when our cells separate, our membrane separates into the liquid ordered and liquid disordered domains. And for each of these domains, with these rotors, we can really determine the quantitative values of viscosities in those phases and look at their effect of composition or temperature on these values. Okay, now back to the cells. Of course, I wouldn't be telling you the story if one of these rotors didn't actually work. So the rotor which has the stopper groups, so the double charge at the end of the alkyl chain, actually doesn't penetrate, doesn't internalize within the growing cells, and it allows us to stain the plasma membrane of these cells very, very efficiently and study some effects of chemotherapy, for example, which I'll mention shortly, and other factors that can affect the health of our cell. Another more or less unexpected positive side effect was that because of the two positive charges, our rotor is now a lot more hydrophilic, and that's actually really positive for in vivo work with these rotors, because the original rotor that doesn't have positive charges completely accumulates in kidneys and liver of live animals, and we can't study anything to do with cancer in live animals using this molecule. However, this more soluble derivative now accumulates really well in live animals in injected cancer cells. So we can actually look at something really useful for example, for animal models for cancer with this molecule. Okay, so here we used this slight tweaking of the structure to introduce cholesterol or double positive charge to change the localization of our rotor in the cell. And this is really successful. But the question is, can we do even better? Can we pinpoint the localization of our rotor even more precisely? And it turns out we can do. So here it's done using a halo tag approach. So we can transfect our cells with transiently with the DNA that encodes for a haloprotein that could be expressed in a particular organelle within the cell. We can design which organelle it could be. And then we can modify our rotor with something called a halo tag ligand, which really quickly and irreversibly covalently binds to the cavity of the haloprotein. And so simply by incubating the transfected cells with our halo tag rotor, we can achieve really nice organelle staining using molecular rotor, achieving different organelles stained and viscosity monitored using essentially the same probe, just different target halo protein. Okay, remember when I started my talk, I said that we are looking to address two major limitations in viscosity imaging in cell. And one is that we are not happy with just measuring a single point within the cell, and I hope it demonstrates to you that we can address this by targeting the rotors and by doing film images of our molecule. But the second limitation was that we would like to be able to do dynamic measurements of viscosity in a cell just as something changes, that is biologically and medically relevant. So it's important that when BODP or any other rotor that we use is in a viscous environment, the fluorescence intensity is fairly high, and so we can accumulate our film images within 1 or 2 minutes most of the time. And that means that we can image changing viscosity within the cell if the process that we are interested in, of course, is slower than the rate of our film image acquisition. So we are limited to this, 1 to 2 minutes, or maybe half a minute in best cases. But we can monitor dynamic processes within the cell just as they occur and the viscosity is changing. Okay, so just to give you some examples of this. So this is a monolayer of HeLa cells that were incubated with cisplatin to basically kill them using chemotherapy. And we can simultaneously monitor the viscosity within the plasma membrane of these cells, and at the same time we can extract lipids from the plasma membranes of these cells and analyze them using mass spec. And we see in both cases with fluorescence and with mass spec, we can see really drastic, statistically significant changes. So for example, upon action of cisplatin, initially within maybe 10 minutes to 1 hour, viscosity drops, and we see also an increase in unsaturated lipids extracted from the cells. However, if we continue growing the cells upon action of cisplatin, we see the opposite change. The viscosity of the cellular membrane increases dramatically. And we can reproduce these results in spheroids and even in vivo model in mice, which is done in collaboration with my colleague Marina Shimanova in Nizhny Novgorod in Russia. If we take a different chemotherapy agent, so here we look at Taxol, we actually don't see any increase in viscosity at all, and we see a decrease in viscosity. And we can again analyze the cells using mass spectrometry, and we now are fairly sure that this decrease is to do with the Taxol action as an agent that breaks the links between the membranes and cytoskeleton. And we're pretty sure it's not the lipid composition, but this breaking of the cytoskeleton to membrane linking proteins that causes the increased fluidity, so decreased viscosity of our membranes upon treatment. Okay, so another example of dynamic monitoring of viscosity. In this case, we decided to look at something unusual, namely the release of carbon monoxide. So we all know CO is a toxic molecule that attaches to hemoglobin, as we heard from Majed earlier today. But also CO is a very important signaling molecule within the cells, and it's being released during inflammatory response, for example. For this study, we teamed up with my colleague at Imperial, James Wilson-Neely, who has a really keen interest in monitoring CO in cells. And he does that by using transition metal complexes, for example, osmium or ruthenium. And the principle of his probes is that the initial complex is dark. However, when the CO is attaching to the ruthenium sensor, due to the trans effect, the fluorescence switches on really, really intensely. So what we've done together with James is we actually attached one of our rotors, the BDP, as the ligand of the complex. And we realized that not only the fluorescence switches on when the CO is being attached to the complex, but also the fluorescence lifetime of our BDP still reports really well in the viscosity of its surroundings. And so here, there are two series of cells treated to induce the formation of CO in them using two different ways. One is a CORM, a chemical based on transition metal complex that releases CO within the cells without starting any metabolic processes or any oxidation reactions. So you just see a large increase in CO within cells. And in this case, we see a large increase in fluorescence of our complex, but no change in lifetime, because we don't expect viscosity to increase or change or be altered in any way. However, if we incubate our cells with hemin, which is a molecule that acts on the iron hydrogenase enzyme that starts the oxidative reactions within the cells and produces carbon monoxide through these reactions, we actually see even larger increase in fluorescence, which means that even more CO is being produced intracellularly. But this time, we see a large decrease in viscosity at the same time. And this to us means that we are probably producing reactive oxygen species within the cell that are consistent with breaking the double bonds within the lipids and probably affecting the protein surrounding the rotor as well, which leads to lower viscosity as a result. Okay, so this is a really crazy experiment, but I've been contacted one day in my office by a space scientist from European Space Agency who read my papers, and he said, let's measure viscosity in space. So we never really quite managed to get the space work funded, but instead a couple of my students applied for funding from the program called Spin Your Thesis, and had access to a huge centrifuge that is localized in Netherlands at the European Space Agency. And essentially the centrifuge is so huge, and it can go up to a huge gravity conditions of about 15 to 20 G, but it's so large that you can fit the whole microscope in one of the gondolas of the centrifuge. So we applied for the Spin Your Thesis time, we got it funded, and we traveled with our cells and molecular rotors to this ESA facility, and we incubated our cells on the microscope stage and then took them up to 15 G, as you can see here. So in green, you see the ramp of gravity, and in black, you see the fluorescence intensity change as the gravity is being taken up and then down again. And we've had really nice reproducible results for several cell types that show that the viscosity within cells follows the ramp of hypergravity. So viscosity increases dramatically as you spin the cells, and then it goes to a large degree down. However, if you just extract lipid vesicles from the cells, from the plasma membrane-derived vesicles, you don't see these changes at all. So it's really the effect of hypergravity, like pressure, on cytoskeleton of the cells. So it's really, really interesting, and would be nice to be continued in space, but it's so hard to get it funded, so we did not yet succeed. Right, so I know many of you in this audience are really interested in photodynamic therapy, and so are we. And so I decided to show some slides that show that molecular rotors are actually good reporters in looking at what reactive oxygen species such as syngas oxygen or radicals do to viscosity within cells. So I don't really need to describe in detail for this audience, but just in case if there are some material scientists that don't know this, PDT is a clinical way of treating neoplastic diseases such as cancer with fast-growing tissue. And they include administration of a drug called photosensitizer to a patient. But then due to various processes, for example, lymphatic drainage or targeting, the photosensitizer specifically localizes just in cancerous tissue. But it's not doing anything unless you shine light on it, red light in this case, and then the photosensitizer is being activated by this red light and starts producing reactive oxygen species, such as syngas oxygen, type 2 photochemistry, or radicals, type 1 photochemistry. And these species are very oxidizing, and they destroy cancerous cells and tissues through the redox reactions that they start, and then that results in removal of the fast-growing tissue in healthy patients. Okay, so for this particular work, I'd like to talk about a molecular rotor that is also a photosensitizer. So this dye here is constructed as two conjugated porphyrin dimers linked through this conjugated butadiene bridge. And the two porphyrin units are in conjugation, however they can rotate. And it turns out that the rotation between the two units is viscosity dependent. But what's important to know is the conjugated form of the dimer, when the two units communicate, is the lower energy emission that emits at about 800 nanometers. However, if the two units are twisted, the communication and the conjugation between the two units is broken, and the emission from that state is at high energy, a twisted kind of state, at about 700 nanometers. So if you now imagine that you excite the twisted state, which is high in energy, it has two options. Either it emits light at 700 nanometers, or it rotates to a more stable planar conformer, and then the planar conformer can emit at 800 nanometers, right? So what we discovered is that you can calibrate the fluorescence responses of the porphyrin dimers based on viscosity, and in low viscosity environments, all the twisted excited state rotates into the planar, and you see predominantly the emission at 800 nanometers. However, at increasing viscosity, you see more and more progressively emission from the twisted state, and you can build a calibration plot of the dimer by dividing the intensity at 700 to the intensity at 780. And as you can see, again, it shows a really nice calibration curve in this doubly logarithmic Förster-Hoffmann coordinates over several orders of magnitude. So what we're going to do now is we're going to get our dimer to produce syngas oxygen, because of course it's 2 porphyrin units linked by a bridge. And so it's very efficient at producing syngas oxygen. But at the same time, we're going to measure the ratio of its emission at 700 to 780 and record the viscosity just as it changes as our cell dies as a result of photodynamic therapy. And we saw a very large effect. So in a healthy, non-perturbed cell, the viscosity is around 80 centipoise. However, as you continuously irradiate it and the cell eventually dies, the viscosity rises sharply until it plateaus at about 350 centipoise when all the photoinduced processes in the cells are complete. So this was really cool. And over the years, we answered ourselves some questions. You know, is the porphyrin dimer unique? Can we think of other molecules that do this? And the answer is yes, but I'm not going to talk about this now. But what I wanted to talk about today is, what is really the mechanism of this increase? Why does this happen? So for this, we decided to separate the function of the photosensitizer and the rotor. And we're going back to our good old depuis molecular rotor that is particularly good for measuring viscosity in lipid bilayers, right? And we're going to use a photosensitizer, which in this case I think was PPS, so a hydrophobic sensitizer that goes to the lipid bilayer nicely. And so we look at the large number of giant unilamellar vesicles that are large enough in size that you can see them using optical microscopy, and then we zoom in on one vesicle at the time and we irradiate it. And we see the changes in viscosity of that vesicle using depuis fluorescence lifetime. And so I hope you can see here very clearly that as you irradiate, the viscosity of this vesicle increases very, very substantially. And importantly, it doesn't happen if you add a quencher such as sodium azide. And it also doesn't happen if you make your lipids out of saturated lipid, which has, for example, methyl groups rather than double bonds. So has the same viscosity, but doesn't have anything that could be oxidized. On the other hand, if we now make our vesicles in the same way with depuis, but we use a different photosensitizer, so in this case methylene blue, that is known to produce a large amount of radicals as well as some of syngas oxygen. Then by zooming on a single vesicle, you actually see the opposite trend. You see a decrease in viscosity. And we know that this is because the radicals that are being produced are a lot more reactive than syngas oxygen. And instead of forming peroxides and polymers out of lipids, they actually cleave those double bonds. And that results in a decreased viscosity and a higher permeability of the lipid bilayer. We actually recently were able to produce those vesicles artificially. So we produced, with the help of Carlos Marcos, we managed to produce those vesicles made of completely oxidized, peroxidized or cleaved lipids and perform molecular dynamic simulations to confirm these conclusions. So we know type 1 photochemistry causes a decrease in viscosity, whereas type 2 photochemistry causes an increase. So now you can rationalize our data for PDT. In PDT, or in cisplatin treatment of cancer, we saw a type 1 peroxidized kind of photochemistry that increased the viscosity. However, in the presence of methylene blue, or in the presence of heme that produced the Ross response within cells, we saw a decreased viscosity, which is most likely linked to the radical production. Okay, so remember my kind of bid to do this measurement more targeted. So we can also make our sensitizer more targeted. So in this case, we are going to choose the genetically encoded protein called killer red that could be encoded in any particular organelle within our cells. And we are going to then choose at will which organelles we're going to irradiate and which organelles are going to be flooded with reactive oxygen species. So this picture here is to show that this is work in 2011, that killer red was demonstrated to produce mostly radical species, so no syngas oxygen at all. And so by adding killer red to our cells, we most likely produce reactive radicals that are going to initiate type 1 photochemistry. Okay, so this is again the work in collaboration with Marina Shermanova, and they're very good at producing this encoded cells with killer red, in this case, that could be localized in 2 different organelles, either in plasma membrane, here, or in the nucleus of our HeLa cells, right? And so in both cases, we're using Bodp that is localized in the membrane. So our readout is in the membrane, but our initial oxidative attack using killer red irradiation that produces reactive oxygen species is going to be different by organelle. And so here's the viscosity data, and what you can hopefully see from here that killer red localized in the nucleus actually causes a decrease in plasma membrane viscosity over time, whereas the plasma membrane localized photosensitizer causes an increase of viscosity. And this has been confirmed in cultured monolayers and also in spheroids. So that's pretty interesting, that different localization of initial oxidative attack can really change the course of what's happening to the cells in terms of their permeabilization and diffusion control processes within them. Okay, now let me try to change gear a little bit and tell you about a different health-related process to do with protein aggregation. So we all know about amyloid-related diseases when sometimes benign and soluble proteins, sometimes for some reason, starts to misfold abnormally, and that promotes its oligomerization and finally aggregation that can result in really serious health consequences in amyloidogenic diseases such as Alzheimer's and Parkinson's. So it's really well known that the mechanism of this sort of amyloidogenic aggregation is really complex, and it differs from protein to protein. And that makes it very, very difficult to study, especially because what's considered the most toxic species, the prefibrillous small oligomers, are not easily detectable by any kind of standard technique. So the gold standard of detecting amyloid aggregation is by adding a fluorescent dye called thioflavin T, or THT for short, that binds really strongly to fibrils, to beta sheets of fibrils, and it makes it light up and it reports on aggregation this way. So we hypothesized that if we use our molecular rotors, that even if they don't specifically bind to oligomers and fibrils, they'll be confined by the increasing crowding that is created by those oligomers and fibrils eventually being created. And we'll hopefully see a large increase in fluorescence lifetime as the aggregation occurs. And that's exactly what happened. So in fact, even the THT is in itself a molecular rotor, and even its intensity only reports on the fibril formation. The lifetime, it seems, can report on more intermediate stages, early stages of aggregation. So I'm only showing one sort of data graph here, but this is the so-called phasor analysis of the time-resolved decay traces shown here that correspond to aggregation of lysozyme, the protein involved in the disease called ALS. Here. And so I'm not going to go in detail through this sort of data analysis, but what I want you to notice here is that this trajectory of phases is not linear, and that means that it's not simply interconversion between 2 species, A and B, so free monomer and aggregated fibrils. It definitely has some other stages here that we call 2 and 3 and 4. And so what we can then do is use alternative techniques, a bit like Majid's example with the elephant, and blind people. So we use different techniques to try to understand what's going on. And so we can use single molecule AFM and nanopore detection to identify that actually what happens here is a decrease in viscosity that is caused by fragmentation of our mature fibrils that are formed of lysozyme. The slide here actually shows very similar data, which is hot off the press, recently published, when we looked at aggregation of alpha-synuclein, which is a protein involved in Parkinson's disease. And here we use 2 molecular rotors, which are both commercially available molecule, THT and DISC, which is a derivative of cyanine-free dye. And so while intensity of these dyes pretty much only responds to fibrils formation, we figured out that the lifetime of both of these dyes reports at much earlier events. It rises a lot earlier. And if we look at the phasor plots of these aggregations, the red points here that are due to aggregation of alpha-synuclein wild type. Actually, these points that we see on phasor plot cannot be matched by any kind of control conditions of producing mature fibrils, shown here in black, or oligomers type B, which are fibrillar oligomers. And so that tells us that these are due to this really early prefibrillar aggregates, oligomers type A, that have not been easy to detect at all using any techniques. And so we are now actively pursuing this work, looking at variants of proteins that are pathological and involved in, say, familiar forms of Parkinson's. Okay. When we look at molecular rotors, we worry a lot about temperature. And this is because the way they work is, in order for fluorescence to deactivate via population of the dark state, the molecular rotor normally has to overcome an energy barrier before it ends up in the dark state, which then becomes deactivated. So it's quite conceivable that changes in temperature, as well as changes in viscosity, can affect the photophysics of our rotor. So how do we counter for this? Well, the way that we try to control for this is we do control experiments, for example, shown here with depuis. When we produce solutions of methanol glycerol, of changing methanol glycerol content, so the higher glycerol, the higher the viscosity, and also change in temperature. So the higher the temperature, the lower the viscosity. But importantly for all these solutions, because they're bulk solvents, they're Newtonian liquids, we know the viscosity of them. And so we can measure the lifetime and produce this calibration curve of lifetime versus viscosity for all these different compositions in different temperatures. And I hope you agree with me that the overlap is actually pretty good. So from this we conclude that at least for depuis rotor, it doesn't really depend on the solution composition or solution temperature, and what it measures is exclusively viscosity, which is great because it allows us to use this rotor for temperature-independent measurements within the cell. So we can study the cell at 10 degrees or 37 degrees, and both times we'll get different viscosity values, but it's not because the temperature is different, it's because the viscosity is different. Okay, so then we thought to investigate a different structure of depuis. In this case, you see that it has extended conjugation. And the reason we've done it is because we thought we'll make a red-emitting rotor. But actually, what we actually got is the dyes where, by changing the substitution, we changed the height of the barrier between the dark and the bright state. And so for this extended conjugated depuis, especially depuis-3, the barrier is the highest. And as a result of this, our new depuis is now not a molecular rotor at all, but instead it completely depends on the temperature of its environment. So we wanted a red-shifted rotor, but we actually ended up with molecular thermometer, which is also quite useful, especially because due to the small size of the substitution, it's cell-permeable. And so we can now measure temperature within the cell if we want to. The accuracy of this measurement is not terribly high, so it's probably not really good enough for detecting the temperature change of any biological process, such as cancer or amyloid aggregation in organelles. But it gives us hope that with further modifications of the structure, we can potentially create more sensitive rotors thermometers that work via fluorescence lifetime. Now, going back to our conjugated porphyrin dimer, you will remember that it works ratiometrically. So we have two peaks at low wavelength and the higher wavelength. Depending on the substitution, it could be 600 and 700 or 700 and 800. But so this one is 650 to 700, two peaks. But what I didn't tell you before is that this rotor is also a lifetime rotor. So if you measure the fluorescence decays in the twisted peak of the decay of the porphyrin dimer, then you'll be able to measure the viscosity using FLIM. So what we then set out to do is to check how the temperature affects the photophysics of our conjugated porphyrin dimer. And the results were very surprising. Well, first, not so surprising results. If we measure the fluorescence spectra in methanol glycerol solutions of different composition and different temperature, we actually have a perfect overlap of all the curves, even better than depuis. So there's no doubt in our mind that if we use ratiometric response of the fluorescence dimer, we get viscosity measurements without any effect of temperature. However, the story was completely different when we looked on the fluorescence lifetime. You can see here, especially for the dimer 2 and 3, so the structures are shown here, and they just change in the degree of biocompatibility, so how well they work in cells. So for 2 and 3, you can clearly see that the curves recorded for different compositions and different temperatures do not overlap. So when my very talented student, Arimas Vishnauskas, did this experiments, he was actually really disappointed. He thought it's an artifact and something is wrong, until we realized that we can actually fit all this data using a type of Arrhenius dependence with the activation energy. And so then what we have is we have a single dimer that you can measure the fluorescence lifetime and fluorescence spectra of. The fluorescence spectra depend only on viscosity. So by measuring the spectra, you know the viscosity for sure. And then you measure the lifetime, and the lifetime is, in a very nice calibration framework, depends on viscosity and temperature. But you already know the viscosity from your spectral response, right? So you can now use all the data to figure out the temperature and viscosity simultaneously. And to the best of our knowledge, this is the only type of molecule that they can do it in one measurement. And this could be important because if you can imagine a viscous environment, such as organelles and cells, and various temperatures will really, really change the viscosity of that environment. So you can't just assume that fixed viscosity is maintained throughout temperature variations. So this could be a handy tool for measuring both parameters simultaneously. I still have a bit more, but do I have time, or do I need to stop? Okay, that's perfect. Right, so far, I used my molecular rotors in such a way that they were freely rotating within an environment of interest. And then the lifetime of our rotors told us about the diffusion-like, viscosity-like environment within the cell. So in the last part of my talk, I'd like to talk about the case where we actually want our rotor to bind tightly to an intracellular molecule. And then the lifetime will depend on the conformation of the binding, and it tells us something interesting about the conformation of the biomolecule, namely DNA in this case. So most of us know that DNA is present in the double helix within the cell, which obviously is responsible for the storage of genetic information. But sometimes this helix has to unwind. And if the helix is rich in a particular nucleobase, specifically guanine, it can form in really strange and interesting secondary structures, such as, for example, G-quadruplex. So G-quadruplex is a tertiary composition of guanines that are linked through Hoogsteen rather than Watson-Crick bonding. And we are going to use our molecular rotors binding to this unusual DNA structure, quadruplex, and because it binds in a completely different conformation to the way it binds to a duplex, we'll see a different lifetime, and hopefully that will tell us about the presence of G-quadruplex within the cell. So why is it interesting? Because actually there are many cellular processes in which double helix has to unwind within the cells. And the efficiency of these processes regulate disease. So for example, the lengthening and shortening of telomeres is implicated in longevity and cancer. Transcription and replication are all very important processes, and quadruplexes are known to form during all the cellular processes, and of course they are tightly regulated by many proteins that are associated with them, etc. But detecting quadruplexes themselves is really, really tricky. There are a couple of antibodies that are available, but they can only work in fixed cells because you have to permeabilize your cells in order to get the antibodies in. So we are going to suggest a molecular rotor that is a small molecule that can work in live cells. And so in this case, let me introduce you to trianguliniums, which are aptly named for their triangular structure. But our triangulinium molecular rotors are quite special because they have these morpholino arms hanging off the structure. And due to hydrogen bonding interactions with quadruplex, morpholino groups will be taken away from the core of the triangulinium. And that means that when our molecule is bound to quadruplex, the quenching from morpholino groups to the core is almost completely eliminated, and we end up with a very long fluorescence lifetime, which is a lot longer than that in the duplex, shown here in green. And both of them are much longer than the lifetime that you see when the molecule is free in solution, and the arms are flapping around and quenching the triangulinium core. Okay, so of course we can calibrate against many DNA and RNA topologies. The quadruplex is shown here in red, and they all have very long fluorescence lifetime. And of course we can then perform FLIM, fluorescence lifetime imaging, where red pixels indicate the presence of these quadruplexes in cells. So what can we do with this kind of technology? Well, we can screen, for example, for drugs that are non-fluorescent in themselves, but are suspected to bind to G quadruplexes. For example, here, green banana is our molecular rota, and it binds to quadruplexes and produces a long lifetime. However, if we incubate our cells with a drug, but potential drug, which is the yellow banana here, if the binding is tight enough, then the yellow banana will bind and kick out our daughter triangulinium probe from the cells, from the quadruplexes, and the lifetime will shorten. And that's exactly what we see here in this titration with PDS, pyridostatin, which is a well-known strong G4 binder. So we know it for PDS, but we might not know it for many other drugs. Whereas if we use duplex binder, DAPI, here, it's known not specifically to bind to quadruplexes, and so there's no change in lifetime in this assay. We can also test for the enzyme activity. So, for example, many enzymes such as helicases are known to unwind quadruplexes at telomeres. So if helicases are active, quadruplexes are being unraveled, and you end up with a relatively short lifetime. However, if you knock out helicases from your cells, then the enzymes obviously are not present, not active anymore. You'll see an increased amount of quadruplexes and an increased lifetime, and that's exactly what we see. And we tested several helicases, and we even saw the effects of knocking out 2 helicases at any one time, and then you see a double increase in lifetime as a result of this. So a good activity test, potentially, which is not available via other means. We also have a specific probe that binds to RNA in the cell, so we can test for RNA quadruplexes and their effects through the fluorescence lifetime. And I think this is it, actually. So I hope I persuaded you that molecular rotas are a really useful tool to look at a variety of biological problems using basically spectroscopy and imaging, and also smart probes that can be designed for a particular application in mind. If you want to know more, we recently reviewed this for molecular rota viscosity measurements and for quadruplexes. Both are in Angivante right now. And of course, all the thanks go to my wonderful group of postdocs and students who work really hard on molecular rotas, and funders and collaborators. And I leave you with some pretty pictures, and thank you for your attention.
So, thank you very much, Marina, for a very wonderful talk. I see we have lots of hands showing up, and microphone over to Margaret.
Thanks, Marina. Very nice talk. I have a small question concerning these zinc dimers. The doublet that you see around 650, 700 nanometers, this is an excitonic splitting?
So I'm not the right person to ask, but so both the Q band and the SORI band of the porphyrin dimer is split, and that's because of the symmetry. And it has been established through experiments and calculations that if you stabilize the dimer using the bridging ligand in a planar conformation, there's no splitting, just a planarized form. However, so the 650 band, the twisted band, it characterizes all the different orientations of the dimer that are different at about 50 degrees and more. So at 50 degrees, the conjugation breaks, and then all these isoforms, not one form, obviously, but all of them are characterized by this higher twisted band. There's lots of theoretical and experimental work from the group of Harry Anderson and his collaborators, and Harry, of course, is the one who made all the dimers.
Thank you.
Yes. Dave Thomas from Uppsala University. Thank you, very interesting talk. So as you heard, this is not my field of research, but I was thinking about this complex environment where, in membranes, for example, where I could expect that the viscosity or diffusion is anisotropic. So, so if you measure rotation in one direction, will you get the same number for viscosity as if it would rotate in a different direction compared to the plane? Is this a problem or something you can utilize or some?
It's a great question. So we have to be really careful how we define viscosity. You know, when we measure viscosity in a homogeneous system and solution, then it's a true viscosity and it correlates one-to-one to our methanol glycerol calibration. However, in the membrane, of course, it all depends on the position of the rotor on the z-axis. So if you are really close to the head groups of the lipid bilayer, then viscosity is really low, actually, and probably the function of the rotor is going to be affected a little bit by interaction with other molecules. So, for example, the proteins that are membrane embedded or water that penetrates the bilayer. However, for all our molecular rotors, we know that they're deep enough within the tail region of the lipid bilayer. So essentially, they behave as if they're in a tiny test tube that is made of lipid tails. And so they literally sense the diffusion. And we can correlate it with the diffusion measurements using FRAP or molecular dynamic simulations at many temperatures, and we know it works. But change the rotor structure, and you have to do the whole characterization again, because you might not know.
Thank you.
Thank you very much for the great overview of these different rotors. But as the triangulum, this one was not a rotor. Right? What is the mechanism for its fluorescence quenching?
So it's photoelectron transfer dye. But the reason I call it rotor is first because it makes a good story. And secondly, it's because it's viscosity dependent. So you can correlate the lifetime to viscosity, and you see a really nice correlation. The thing is that it doesn't get a chance to be a rotor, because most of the time, when it's in the presence of the DNA or RNA, nucleic acid, it just binds to either duplex or quadruplex, and then it's not rotating anymore. And it's the position of the morpholino groups that are PET quenching the triangulinium core, right?
So the position of the external groups allow proton transfer or not?
They do. So if it's in access, if it's in solution, then the groups are kind of fluctuating due to Brownian motion, and the quenching is possible. However, if you are bound to duplex or quadruplex, the groups are taken completely away from the core, and then this PET process clearly happens through space, because then there's no quenching at all. You can also remove this quenching by protonating morpholino groups. So we had to be quite careful that that's not what happens, because you can also protonate, and then the lifetime goes up even higher, because PET is not energetically favorable then. But importantly, and we are trying to work this out, we haven't quite done it yet, if you change the structure of the triangulinium a little bit by extending the conjugation, so it's the sort of stuff that Bo Larsen does, it doesn't go to the nucleus of the cell anymore, and instead it localizes in cytosol and mitochondria, and it doesn't bind to nucleic acid, and it seems that then the lifetime is determined by viscosity. So we kind of are trying to then make them viscosity probes as well.
Antonio? Yeah, thanks a lot for this inspiring talk. I have just two short questions. The first one is about the G4. And my question was, can you also imagine to have a probe which could be dependent or sense the difference in topology of the quadruplex between parallel, anti-parallel, or hybrid, for instance? And my second question about the rotors, the first part of the rotors in the membrane. I mean, you are inducing this rotational movement, so are you also, in a certain sense, inducing some hyperthermic effect in your membranes?
Okay, so the first question about quadruplexes, it's a really good question, and we're thinking a little bit about that. But so far, we see the largest difference between free in solution, bound to duplex, and bound to quadruplex. And all the quadruplexes, whether it's DNA or RNA, actually are all pretty much on the same level. We had a candidate rotor, which is a helicene dye with morpholino group. And then helicene is obviously chiral. And we found that the binding of helicene is really different for different types of chiral quadruplexes, especially if they have an overhanging group on top that really prevents the binding. But unfortunately, then helicene didn't work for lifetime. So the binding is selective to different types of quadruplexes, but the lifetime isn't. So we don't have a selective rotor for a particular type of quadruplex. all of them seem to respond particularly well with lifetime, so really high lifetime to c-Myc, which is an oncogene, quadruplex, and is really commonly found in, U2OS cells or bone cancer cells. I hope I answered this part of the question. So the hypothermia question for the membranes, so we excite our rotors either using 1 or 2 photon excitation, and this produces mostly the excited state that deactivates really fast within, several nanoseconds. So we don't actually see any temperature increase associated with that, but I'm sure, there's some schemes, but you can induce the thermal effect by, for example, attaching rotors to the surface of the plasmonic nanoparticles, etc. But we haven't, it's an interesting idea because you can kill cancer, obviously, using temperature generation, but we don't see it with rotors as far as I know.
Thank you very much for this very, very nice talk. I just have a small question about the polarity. Is there any influence of the polarity onto your rotors?
Yeah, so really, really good question, and it's one of our main controls. So for depuis rotor specifically, which localizes in the membrane, we actually spent a lot of time, because it was the first rotor, characterizing it in different solutions. So if you do the calibration in methylene glycerol or in toluene castor oil, at higher viscosities from like 50 centipoise onwards, you see no difference whatsoever. So it looks like the predominant factor is viscosity rather than anything else. However, at low viscosities, I think the barrier becomes small enough that it's the position of the dark state that also affects the decay. And it looks like the position of the dark state is affected by the polarity. So if you measure methanol versus toluene, which are both similar polarity, similar viscosity, but very different polarity, you see a huge difference. So 600 picoseconds to 100 picoseconds.
Okay, I think we're running out of time for questions. I'd like to please join me, ask you to join me in thanking Marina for a very wonderful talk. Thank you also for including a front cover from PPS. That's a very nice touch. Thank you. I will now hand over the microphone to continue this afternoon's session.
So now we are moving on with the highlight of the health axis, and we welcome Anne-Sophie Deval from Lille, and more specifically Aucontail. So she will speak about photodynamic therapy. Yep.
Good afternoon. Thank you for this kind presentation. My talk is about the work led by the Aucontail unit, led by Professor Nadira Delem, and deal with the efficacy of pyropeg-Afin-mediated photodynamic therapy for the management of pancreatic ductal adenocarcinoma. Pancreatic ductal adenocarcinoma, most commonly referred to as PDAC, is the most common type of pancreatic cancers, accounting for 90% of pancreatic cancer diagnoses and concerning about 450,000 new cases worldwide in 2020. PDAC originates from the lining of the ducts in the pancreas. Such location limit access for palpation. Common symptoms are often non-specific, including abdominal pain, jaundice, and weight loss. Moreover, the aggressive nature of the disease is associated with the high potency of metastatic dissemination to adjacent organs, including liver and gallbladder. All these points considered result in a late diagnosis at metastatic stages in around 55% of patients. For this metastatic patient, the only treatment is palliative chemotherapy with an overall survival not exceeding 11 months. The common death by metastatic disease underscores the urgent need to develop novel adjuvant therapeutic strategy that target not only the primary tumor, but also the biological vulnerabilities of metastatic PDAC cells. Immunotherapy has been proposed as such a strategy and has been evaluated. Unfortunately, this evaluation revealed that pediatric tumor has a high immunosuppressive microenvironments that limit sensitivity to immunotherapy, leading to its failure. Photodynamic therapy has emerged as a promising candidate. Photodynamic therapy is an innovative therapy based on the interaction of three elements. The first element is the oxygen naturally present in the biological tissues. The second element in the photosensitizer or PS. A PS is a molecule that can absorb specific wavelengths of light and can transform them into useful energy. The PS or its precursor is administered to the patient sometime before illumination. This time enables the PS to accumulate more or less preferentially within the cancer cell compared to the healthy cells. Several generations of PS have followed one another with the aim of improving this preferential accumulation. Today, research is focusing on the third generation PS that enable targeted PDT of cancer cells through vectorization and conjugation. Third element is light. Light must obviously have the wavelength that can photoactivate the PS, but also the wavelength must be relevant to penetrate the biological tissues. When the three elements are brought together, the PS is in a ground state, absorbs light, and reaches next excited state. Excited states are very unstable, and several pathways allow the PS to deactivate and to return to its ground state. One is pathway involves the transition of the PS to its triplet state. In this state, the PS can interact in two types of chemical reaction involving the oxygen of the biological tissue and leading to the creation of cytotoxic reactive oxygen species, induction of an oxidative stress. The first therapeutic effect of PDT is the local destruction of cancer cells resulting from the oxidative stress. Second therapeutic effect that results also from the oxidative stress is the alteration of the vascular network of the tumor, leading to its hypoxia and nutrient deprivation. An adjuvant effect also occurs. In fact, the cells that are damaged by the two therapeutic effects expose or release molecules that cause the activation of innate and adaptive immune cells in the tumor microenvironment. Regarding its three effects, PDT could be a pertinent strategy in PDAC treatment. In the literature, there are around 1,000 clinical studies for PDAC. In these studies, apply in a palliative fashion to alleviate patients' pain, and illumination is achieved in a percutaneous manner under ultrasound guidance. The study concluded the feasibility of the procedure, but highlighted several blocking points. First, the various PS did not accumulate in a sufficient preferential way in the PDAC tissue compared to the healthy tissue, leading to adverse complications to adjacent organs. Second, the PS were not sufficiently efficient in generating ROS in oxygen poor condition. It resulted in limited ROS production and suboptimal outcome. Third, the PS were activatable at short visible wavelengths that limits the light penetration, and that making PDT less efficient in larger tumors. There is therefore need for novel PS more relevant for PDT of PDEC. The project for PDT led by Oncotai involves common stage before clinical application can be considered. The first stage aims to identify an existing PS or to develop a new specific one. We choose to use PS of third generation that has been recently developed in collaboration between the lab of Dr. Céline Frochot and Oncotai. This PS results from the linkage of the PS pyrophéophobid egg with the ligand folic acid. This PS has been specifically designed to target cells of peritoneal carcinomatosis from ovarian cancers. In fact, CPO cells are known to overexpress folate receptor alpha, and the strong interaction between this receptor and the folic acid of the PS has proven to result in the specific transport of the PS within the cancer cells. Many wavelengths could be used to activate the PS. We have selected this one because it offers the best balance between activation efficiency and the penetration depth. PDT using this PS has demonstrated to allow the selective destruction of CPO cells and therefore to enable targeted PDT. Based on the literature, PDEC cells may also overexpress this receptor and therefore may also enable a targeted PDT. The second stage aims to carry out in vitro study with different objectives. For these in vitro studies, we use a 4-cell line of PDAC and 1 cell line of CPO was considered as controlled. 4 objectives were addressed. The first objective was to determine the expression of FR alpha within the PDAC cells. This evaluation was first clearly demonstrated in a gene level for all the cell lines. The expression was also clearly established for the cell line at the protein levels. The second objective was to investigate the incorporation of PS into the cells. This investigation was performed by comparing the localization of the cell nuclei with the localization of the PS. For the cell culture without PS, expected only the nuclei were detected. For the cell culture with PS, rain staining reveals the PS incorporation for the 4 cell lines. The third objective was to determine the impact of PDT in terms of destruction of cancer cells. 4 conditions were considered. The condition involving both incubation and elimination was the PDT condition, while the 3 other conditions are control ones. To deliver PDT to cancer cells, we have developed a dedicated homemade elimination device. This device involving connecting light-emitting fabrics and enables the elimination with low irradiance and physiological temperature. Shown in figure, whatever the cell line, a reduction of about 95% was observed in the cell viability, whatever the cell line, and the total elimination was achieved within 4 hours and 24 hours post-PDT. This result demonstrates that the control conditions were safe and that PDT, as administered here, was able to efficiently destroy tumor cells. The fourth objective was to determine the impact of PDT in terms of activation of immune cells. This impact was first determined through the measurement of the concentration of two messenger molecules secreted by cells post-treatment. Regarding interferon gamma, an increase in concentration of about 50% was achieved for 3 cell lines. Interferon is known to exhibit a variety of anti-tumor immune properties in PDAC, and the increase in this production observed with the PDT condition should therefore amplify the properties. For the interleukin 6, a total decrease was obtained with the PDT condition for 2 cell lines. Interleukin 6 is a driver of PDAC pathogenesis, and elevated level promote numerous pro-tumor process. Reducing this high level, as PDT did, should therefore to decrease pro-tumoral process. The impact of immune system was also assessed through the effect of molecules secreted by cells post-treatment on human immune cells. The results show that the non-treated, light-only and PS-only condition significantly decrease the proliferation compared to the chemically active PBMC. That confirms that PDAC tumors has an immunosuppressive microenvironment. Regarding the PS condition, the reduction is smaller, and we therefore suggest that PDT allows to reduce the immunosuppressive effect. The first stage aimed to carry out an in vivo study. The objective of this study was to evaluate the efficiency in terms of tumor growth of PDT in a mouse model of PDAC. First, the mouse were xenotransplanted with a human cell line of PDAC, and then they were followed up for tumor growth by immunofluorescence. When tumor reach a given size, the mice receive one treatment among the 3 ones, and the follow-up continue until euthanasia. Here also, a dedicated homemade illumination device was developed. The result shows that the tumor continued growing for the 3 control condition, while a significant reduction was observed for the PDT condition. To conclude, the result of our study indicates that pyropeg-Affe is a relevant PS for PDT of PDAC, and that pyropeg-Affe mediated PDT could be a doubly effective adjuvant strategy for PDAC, combining a direct tumor destruction and a restoration of the immune system. Regarding this last point, PDT could contribute to turning cold tumor into hot tumor, and therefore could restore the sensitivity of PDAC cells to immunotherapy. More detail can be found in the corresponding publication. As regards the perspective, new PS that even more meets the requirement for a pertinent PS could be developed. Such development would therefore need the development of suitable illumination device. Moreover, the evaluation could be extended to 3D structure grown from patient tumor sample. In fact, such a tumor resumed to in vivo organization, and such evaluation would be more pertinent for further clinical application. All these points are addressed in the PEPR PDT, PDAC, je sais plus. Désolée. Céline, and will you present? I will thanks to all contributors and the partner. Thank you.
Thank you, Anne-Sophie. So the talk now is open for questions. Yeah.
Thank you for your talk. I was wondering about the structure, looking at the structure of your photosensitizer. So you have pyrophobite, then you have, which is hydrophobic. Then it's coupled to some hydrophilic structure, it is polyethylene glycol, and then you have the folic acid. So I was wondering if when you inject this or you administer this you incubate this with cells, it remains in monomeric form or it will self-assemble into micelles? So I don't know if I'm clear. So your molecule will self-assemble into micelles or it remains monomeric when you administer that?
I don't know.
Okay, thank you.
Any other question?
Thanks for the nice talk. I have just a question. You have characterized that, you have clearly shown that the cells are indeed dying. Have you characterized if they are necrotic or apoptotic cells?
Yes, we have, but not for this, not for PDAC. We have characterized that point for CPO. The experimentation are not finished because the galenic form of the PS is in development, and so we are pending for this new format to perform this expensive experimentation.
I have a question also. You can ask your question.
Are you ready? The microphone. Thank you. When you mentioned the in vitro then in vivo studies,
yes.
Actually, how long does it take to make these series of experiments, especially the in vivo?
In vivo, 2-3 years, because this experimentation requires authorization from, and this authorization are obtained are longer to be obtained, and to adjust the parameter, because when we inject cells to mouse, it may be it would delay. It's necessary to obtain a tumor of the corresponding size, and we don't know before.
Okay, thank you.
So, I have a question from a physicist. So it seems that you use continuous light, correct?
Alors, for in vitro experimentation, we use continuous light, in fact. For the in vivo one, no, we use fractionated illumination. I don't mention it because the time was limited, but we perform fractionated illumination to allow the restoration of the oxygen level during the dark period.
Okay, I see. So it's a long time, actually. I mean, fractionated is...
It's a long fractionation. It's 1 minute of light for 2 minutes of dark.
Okay.
In clinic, in our clinical trials, we perform also fractionation, but at shorter time. Say 2 minutes of illumination, 2 minutes and a half of dark.
Okay. And can we think about using optical fibers to penetrate deeper, actually? And because it seems that this is a problem, the penetration of light in the body?
The penetration of light is in fact a problem, but it depends of the organs in the liver of pancreas. Such insertion is not always possible because the ducts of bile, and it may be dangerous for the patient. For the glioblastoma, which is a tumor of the brain, we are developing a device with interstitial fiber, yes, inserted in the brain.
Okay, so thank you very much. We can end this. And so now we welcome the coordinators or the only one? Ah, okay. So Céline Fauchot, who will present the moonshot project of the health axis. So PDT PDAC.
Yes, thank you very much. Thank you to everyone to be here. I should have been with Vincent, but Vincent could not come because of personal problems, but I'm sure he's behind his computer. So, coucou Vincent. So, before we did a lot of brainstorming when we applied for this project, and with all the chemists and the biologists, and during maybe 2 hours, we were thinking what kind of cancer we want to treat. And it was the first question, because it could have been many types of cancer. And we decided to focus on pancreatic cancer because of what it has been done, what it has been said before. The 5-year survival rate is 5%. There is no real solutions. And there will be more and more people who will have this kind of cancer, you can see that. So it's very necessary to find new therapeutic solutions. So PDT can be one, but of course alone, but for sure in combination with others. So now you know what is PDT because Marina explained, and also Anne-Sophie. So it's another way to present it. So effectively the light, you can put the light with LED, with light, with sun, with fiber. Everything can work. It depends on the cancer you want to treat. You need oxygen, and it's true that when you do fractionation of light, then you allow the reoxygenation of the tissue. And photosensitizer. So the photosensitizer, it can be injected in blood, but it can be also a cream, depending on the kind of cancer, and you can also have it in a water, and you can drink it. PDT is done every day in the world, in Europe, in France, even in Paris. So mainly in dermatology, but also there are clinical trials nowadays for brain cancer, as you said, Anne-Sophie, but also for lung cancer. So it is really something that is developed for clinical application. But if we add this project, it means that there are still things to do. And these things to do is that there are still some improvement to do. Concerning light, there are many chemists in France who do very nice molecules. I am a chemist, so I can complain. But there are not so many people who deal with dosimetry. And if you have a very good molecule, but you don't send a good amount of light, no way. So dosimetry is very important, and you have specialists in this group of people who know how to measure the photons, how to give a way to really send the good amount of photon at a good place. The light penetration, if you have fibers, it's not a problem, but sometimes we cannot use fibers. So the different way we want to try is to use biphotonic excitation, because then you can have a higher wavelength or a deeper penetration of light. There are more and more studies about using X-ray. So low energy X-ray, because then you can really go through the body. Cherenkov, because it's a blue light, and it appears that most of the porphyrin have the solid band in the blue, so it can be a solution. And ultrasound. Oxygen, you already told about that. And for the photoactivable molecules, it's true that most of the photosensitizers that are used in clinics are not very specific. So we want to synthesize some targeted photosynthesizer or using nanoparticles. So in this project, so we are 14 laboratories. We would like to use, sorry, I don't know how to say that, 2 different platforms. So there will be chemistry, photophysical analysis, dosimetry, and light device, and of course, biological studies. So first of all, so it's normal because the aim of our project is maybe one day to go to clinics. So I cannot say anything, so I will spend 10 minutes to say anything. Not bad. So we will develop different kind of photosynthesizer. So it can be some, you can see it's ruthenium complexes, it can be some porphyrin or other type of porphyrin, and also some nanoparticles that can be excited by X-ray. The first part is to develop a peptide. So to develop a peptide, so we checked the literature. We decided to target 2 receptors that are overexpressed on cancer cells. These receptors are MUC1 and UPAR. So first of all, we synthesize peptides that are described in the literature to check if they really have a good affinity for these receptors. And this peptide, we will analyze the contribution of each amino acid, and we will design some new ones that can be patented. After that, the idea is to couple, it's to couple this peptide to a photosynthesizer, so different kind of photosynthesizer, and also to nanoparticles. So this is what we have done nowadays. We developed some peptides and some photosynthesizers. The second work package is light matter interaction. So it has still not started yet. The postdoc arrived 1 month ago, I think. So we will start soon. Of course, we can already detect singlet oxygen in solution because we can do that in our lab. But after, for all the physical model of wave propagation and the Monte Carlo simulation for short-term dosimetry, it will be done in the next year. Concerning the in vitro biological studies, for sure, for this kind of project, we need some molecule. So we need to synthesize the molecule, and after we can do the biological studies. So it didn't start, but we already order all the cells. So all the cells culture has been done in Lille, and all the cells have been sent to all the biologists who want to work in this project. So then we will work onto the same cells in different laboratories. So for sure, if we didn't do in vivo experiments, we still didn't do in vivo experiments. But as Anne-Sophie showed, in Oncotype, they developed some specific device that can be used to treat several mice together. So the partnership, so 14 laboratories. I think we should find some people in Bretagne, because you see, there is no one. Management framework, so I am a project leader with Vincent. The VP manager are Valérie Heitz, Annabella, Gilles Gasser, Nadir Adelem. The scientific committee, so are all the people involved in this project. And what is very interesting, I think, for us, is that we have an advisory board. And in this board, we have Serge Mordon, who is the co-founder of Emerion. So Emerion is a French company founded 5 years ago, who developed the system of illumination and the photosynthesizer to treat glioblastoma, which is the brain cancer. It's in phase 2 in United States. So it's very important in our consortium to have some people who really know about what they, because chemists, they are very nice, they do many molecules, but at the end, they have to go to the patient. We have also Nicolas Jonquier, who is a specialist of pancreas, and we have 2 surgeons. And for us, it's very important to have surgeons, Because if they believe in what we do, then it proves that we can do something. And so it's already 1 year. So in this 1 year, we synthesized a molecule. We started the photophysical study. We order the cells, and now we will have to work hard. Maybe yes, I thought that we do not have any specialist of viscosity and PDT. So maybe I will ask Marina to join our consortium. Thank you very much.
Thank you, Céline. And actually, we have time for questions. If you have 1 or 2 questions. Not, yeah.
Thank you, Céline, for your presentation. So you showed that you will use 2 different peptides and many other for targeting, but in the previous presentation, if I'm not wrong, so she showed already that folic acid work to how to target folate receptor. Why you don't use the same strategy?
Okay, I have to think. No, the previous molecule, there is a patent. And there is a patent, and it's specific for ovarian metastases. So we don't want to use this. Maybe we can use folic acid for this type of, for sure we can use, because folic acid receptor is overexpressed. But we thought that peptides are also quite interesting, and we have a laboratory with a specialist in peptide synthesis. And folic acid, sometimes it's tricky.
Okay. There is another question.
Yeah, it's a naive question because I'm far from the field. So how long does it take from the synthesis of the amino acids to the clinical applications, to the patients, I would say?
It depends on the chance. No. The peptide synthesis, we have a robot that it goes very fast. So it's not the problem. Then you have to find a peptide that has a good affinity. So then you have to wait to have the result of affinity. Then this peptide has to be very stable. Then you have to wait to have the result for the stability. And then if nothing happens, then you go back to the beginning. So if you are lucky, the synthesis and the coupling of the photosynthesizer, it can go quite fast. After, all the in vitro studies take some... It depends on what you want to prove, but if you do immunology, it can take 1-2 years. In vivo, it's even more. And then after, it's just the beginning of the problem. Because you have your molecule, you have your system, then you have to patent, and then when you patent, then after you have to find money, at least 1 million. And then after, you have to do all the GMP synthesis and the tests. We had the patent in 2019. There was the COVID, so it was not so fast, but we just start to approach, to find money to go to clinic. So it takes some time.
Thank you.
Years.
Okay, thank you. I think that we have to move on. So you will have time to discuss with Céline later. Thank you.
So now we are going to have a short session on the ultra-fast infrastructure. So first I will give a few words about the infrastructure, and after we have 3 talks, 2 from platforms and 1 from users. So Jean-Pierre this morning showed you the Operando infrastructure. Ultrafast is the sister ship of Operando. So you will find the same application protocol. You will find the same funding process. In fact, what is different are the challenges involved. So we had 4 challenges. The first one was to make attosecond and femtosecond sources accessible, and especially accessible to new users. The second one was to expand the wavelength range available in France namely to go from XUV to terahertz in order to analyze new photochemical, new photophysical, and new photobiological processes. We have also the challenge to go forward toward time-resolved micro and nanoscopies in order to be able to analyze more realistic, more heterogeneous materials, in order to go up to the device, real device that, for example, are prepared by the Apollo prototyping facilities. And we have also the challenge to make more easily accessible the femtosecond micromachining tools, especially the one available in Saint-Étienne. So this translates now in 12 platforms. 7 are already available, 5 are expected next year. You have a large amount of investment associated with this new infrastructure, so 3.6 million euros in order to update or to upgrade the platforms. And we will have almost 3,000 days available for the whole project, which translate in about 400 projects that can be submitted. We count about 7 days per project in average. So a few examples of the update and upgrades that have already been made. So you have many more examples on the posters. Maybe you went to look at them during the lunch, but you still have the coffee break next to go and discuss with the people from the platforms. And of course, most of these platforms deal with pump probe experiments. So I try to make a summary of the probes that are now available. So we have a strong effort on vibrational spectroscopies. So mid-infrared, far-infrared spectroscopies. We have also femtosecond Raman that will be presented by Manuel. We have femtosecond optical microscopy, near-field measurements. We have also ptychography in needle. And we have also a system dedicated to gas phase measurement with VMI and AZMS. So the application process is the same. The portal is the same as the one that was presented this morning. So now I give the floor to the science, on to the technique, with Manuel, who will present you first the femtoraman.
Thank you. Okay. First of all, thank you very much to the organizers for giving me the opportunity to put in the spotlight the femto-Raman platform, especially because Raman is a technique that everybody knows that exists, but nobody uses. Everybody thinks that it's quite difficult, and then if we do femto-Raman, I'm pretty sure that none of you think like one of the techniques that you can use to characterize your samples or to work on your samples. So I hope that after these 5 minutes, at least you can consider, and then you can come to talk to us. So the platform, it's the visible, where is the laser? Here. The visible face of the platform is Bruno Robert, but we work very tight between him, myself, and Juanjo Romero, that is a young scientist that we hired recently, and also he will give a talk, I think, tomorrow. So we are located there at the I2BC, and basically we use this platform to look at the vibrational modes of the excited states. That means states that they are living very short. We have a temporal resolution around 150 to 3 nanoseconds, and we can cover quite a wide spectral range, although visible is the most visible at this moment. Okay, so what is interesting about this? Well, to do Raman, we need a very narrow lasers in order to prove each one of the different vibrational modes. The problem comes that when we go to very short times, like femtoseconds, basically, due to the Heisenberg principle, we cannot reach such a narrow bandwidth. So basically, we have a time limitation. The technique, basically, if you know transient absorption, normally pump probe, is normally an actinic pump that excites the sample, and then we prove the sample with a supercontinuum. What we do here is to avoid this. Basically, we excite the sample, and then we have a Raman pump that is spectrally narrow but temporally wide in picoseconds that is giving us the spectral resolution and creating the Raman modes. And the Raman probe that is temporally narrow, and basically these two beams interact coherently and they enhance the Raman modes, giving both temporal and spectral resolution. What is that interesting for? So that is especially interesting for samples that they are very complex or that they have very excited states evolving at the same moment. Biology normally is the most complex things. So that will be, doesn't matter much, but it's a photosynthetic antenna. And they have plenty of bacteriochlorophylls and carotenoids. And we know that once a photon is absorbed there is plenty of different processes happening in parallel. Plenty of people have been studying that. There is a lot known about this, but basically still is not figured out how the energy moves so efficiently through this antenna. So basically the idea of this technique is that that will be the transient absorption spectra, and we know that everything is happening there. So we can get this Raman probe, and we can subselect and make different selections of parts of the spectra. And we prove specifically each one of the excited states that corresponds to this absorption. What we end up having is basically for each one of the Raman probes that we put, different spectral maps with change the vibrational mode within time. And we can do that for different Raman probes. That gave us selectivity. I don't need to explain exactly what is one of these spectra, but you can see without knowing anything about photosynthesis, even about Raman, that clearly for each one of the different maps, we have different vibrational modes. And we also can see how each one of those vibrational modes can evolve with time. We do that with photosynthetic systems, and it's quite nice because we are able to separate specifically each one of the vibrational modes without any kind. That is just raw data. So there is no any kind of analysis. Of course, later we can do some kind of modeling and even improve it. So the idea is that we can do that with very complex models. We can do that also with artificial systems. Juanjo will show you some of the data later. And ideally, you have to start considering that Raman is a technique that sometimes may be a little bit difficult, but can bring a lot of information. So I will encourage you and also your students to come talk to us, see if this technique is right for the science that you are doing, and let's see if we can make some nice measurements. Thank you. Yeah.
Thank you. Yes, I think it's a very nice demonstration how you can selectively get the Raman spectra of different chromophores there. What is the ultimate spectral resolution?
Spectral resolution at the time resolution, or
really in the spectra, the
spectra,
the Raman spectra.
Around 5 wave numbers. That depends if we are looking at the UV part or at the IR part.
Okay, because the looks rather like 20 wave numbers in the spectra you show there.
Wait. The width of the vibrational mode depends a lot of what and the spectra that we are looking at, and also that is done at room temperature. We know that when we go at low temperature, we can get better resolution. Sorry.
Thank you. Should I continue in French or in English? Okay. Thank you. So I am Benoît Claudel from ICB. Where's the laser? Sorry. From ICB in Dijon. So we are newcomers in the PEPR LUMA, since we are a new platform that you will have access to, hopefully. And I would like to mention first that Smart Light is first an Equipex Plus project that we are implementing together between ICB in Dijon and Femto-ST in Besançon. And the goal of this Equipex Plus project is to build a French infrastructure devoted to optics and artificial intelligence, and the different manners optics and artificial intelligence take benefits together. So this is a picture we proposed to the international jury, and actually we are implementing more than 20 projects dealing with artificial intelligence optimization of existing optical systems, optical materials, and on the contrary, how to fabricate photonic hardware to implement a new generation of photonic computers which are faster and more energy efficient. Now, this project is an open research platform you have access to, and we have implemented different facilities which are sorted in 4 technological clusters. Each of these clusters are addressing some specific technologies. The first one is related to high-speed optoelectronics, and I'm just putting the spotlight on the best feature we can propose and which are almost unique in France. So in optoelectronics, we can address optical and electronic signal in real time at 1 gigahertz rate, which means that we have a 10 picosecond real-time resolution to monitor optical signals. For the multimodal microscopy, we can achieve sub-wavelength resolution up to 10 nanometer on nanoscale devices such as plasmonic devices or any other nano-optics nanostructure. On the third cluster is about 3D optics. So we have some facilities to fabricate fibers with a local specialty on mid-infrared fibers made of chalcogenic glasses, which are highly transparent in the mid-infrared. And we have newly installed a 3D lithography system enabling 3D printing on fibers and any wafers, and also realignment capabilities on photonic integrated chips. And the last cluster is hosting all our femtosecond laser line, which are very different depending on the application we are playing with. I mean, in terms of repetition rate, we are ranging from the kilohertz range to the megahertz range, and we are covering UV to mid-infrared up to 16 micron. So I will not explain all the equipment we have on the platform, and if you want more information, please visit our website, and we will have a full detail of all the equipments in the different clusters. And if you visit the website, this is also good for our referencing on Google. I will just finish by putting the spotlight on one illustration that we made recently and which may be of interest for some people here who are playing with chirality and plasmonics. And this is a near-field image of a gold nanodisk which sustain a dipolar mode resonance. And this is the near-field images of the complex field of this nanodisk, which is made by near-field microscopy, implementing an heterodyne detection. Basically, you have a sample, you shine the sample with a laser, and then you scatter the local field with a probe. And you make this scattering interfering with part of the incident lights. So this is an interferometer. You put that on a lock-in amplifier, and you manage to extract the amplitude and the phase of the optical field. If you excite this, as usual, with a linear polarization, you have a nice picture here of the dipolar mode, and with the phase shift and the phase jump in the mode. But if you move to a circular left or circular right polarization, then you are able to excite a vortex. And probably this will be of interest for people working on chirality. That's it for me. Thank you for your attention.
What is the dark? What is the dark circle in your? What does it correspond to?
Here.
The small one, yes.
Well, this is because there's a double topography step. You have the big disk, which is on a small pedestal of silica around, which is under edge.
Okay.
So don't hesitate to get in touch with me during the coffee break or in front of the poster.
Thank you. Thank you. So the next speaker will be Sylvain Bétoul from LCPMR, who will speak about his experience as a user in Celia.
Yes, exactly. Hello, everyone. So Sylvain Bétoul, and I will present you the experiment we did at Celia at Bordeaux, because our motivation was that we have another experiment that is planned at Soleil Synchrotron, and we want to study the iodoconfor here in Corchel at Synchrotron Soleil. But the sample we got of iodoconfor from a company was not really characterized in terms of enantiomerical excess. So we wanted to characterize, and so we used the LUMA funding and the platform at Celia to characterize it, and by the study of the photoelectron dichroism of the iodoconfor. And to do this, we needed a source in the visible range for 515 nanometers. And the analyzer was a VMI spectrometer that can measure the kinetic energy of the electron emitted and resolved it angularly. So the beam time was of 1 week at Celia Laboratory. Many thanks to the host team that prepared all the setup 2 weeks before, so it was really helpful for me. And then all the acquisition and the analysis was done in collaboration also with the host team and with my team at the LCPMR. So first, to explain you what is photoelectron elliptical dichroism. When you ionize a chiral molecule by a circular light polarized, you will see an asymmetry forward-backward in the probability of emission of a photon. And this asymmetry is along the axis of propagation of the light. We can describe it by the G function that just do the difference between intensity forward minus backward, and then renormalized. And so this is what is interesting is that when you change the enantiomer, you have the exact same amount of asymmetry, but opposite sign. And this is also the case when you change the left polarization from a right polarization. So now, what about elliptical polarization? So we can describe the polarization state with a third parameter of Stokes. When it's -1, your circular left, then elliptical, 0, your linear, elliptical, and 1, your circular right. And we could assume that there is a linear dependency with the amount of polarized, circular polarized light. And this is right, but when you are in one photon ionization. The experiment we did, we were in multi-photon ionization with a resonance state here. And when you're in that case, you can see something that is not linear, that can have here a maximum for an elliptical polarization. You can see also a change of sign there. And so this is interesting because you add a degree of liberty here that can give you this kind of spectrum, and that is really sensitive to each sample, as that gives you a probe for analytical chemistry. And so this is why we use this technique to characterize the iodoconfor. So here as the first result, we studied the iodoconfor, we compared it with the confor, and if we just first focus on the iodoconfor spectrum, we can see that our sample plus and minus are well reversed, so we can determine a relative enantiomerical excess between both samples that is close to 1, so now we are confident to use it at Synchrotron Soleil. And what was pretty surprised is that when we look at the confor spectrum, it was really different from the iodoconfor, so that shows that this technique is really sensitive. And so now we want to pursue also in this way this measurement and to try to explain why it is so different. And so there is another LUMA project that was accepted that will help us to investigate these differences between both behaviors in terms of photoelectron dichroism. So thank you for your listening.
Thank you. Do you have some questions? I have only one question. What beamline will you use on Soleil?
It's a Pleiad. So the goal is to be in the range of iodine core shell. And so it's around 30 eV. And so Pleiad can go between 10 and 1,000 eV. So this is why we used Pleiad.
So you have an overlap with Celia in terms of energy?
Not at all. So that's why if we had an overlap, we could do this experiment at Soleil. No, Celia it's more at 515 nanometers, so it's more 2 eV. So it's a bit less than the minimum range of Soleil. And at Celia there was also all the setup with to measure this kind of spectrum that is not at Soleil. That is also an argument.
Thank you. Other questions, or one is going to see the posters, of course, and maybe take some coffee. Thank you.
So we should be back in half an hour, I think, in the program. Thank you.
No, no, that's not mine. It's me, but it's not mine. Picture number 3 was mine.
So good afternoon. I think it is time to start this last session. So my name is Muriel Chavarot-Kerlidou. I'm from Grenoble, and I'm coordinating with Philippe Gottico the Moonshot project on the energy and environment axis of LUMA. So it is my great pleasure today to introduce Professor Leif Hammarström from Uppsala University in Sweden. So Leif is a physical chemist. He obtained his PhD thesis in 1995 in Uppsala before moving to Bologna for a postdoctoral fellowship with Professor Vincenzo Balzani. So maybe for the youngest in the audience, Professor Balzani was at that time one of the most famous photochemists, and he played a major role in the rise of inorganic and supramolecular photochemistry. So after this stay in Italy, Leif returned to Sweden, and he has been a full professor of chemical physics since 2004. So Leif's group is highly active in the fields of artificial photosynthesis and also proton-coupled electron transfers, and more specifically on fundamental mechanistic studies of molecular systems using a combination of electrochemical, photochemical, and time-result spectroscopic technique. Leif Hammarström is internationally recognized for his leading contribution to these fields, and for many years now, he has been the chairperson of the Swedish Consortium for Artificial Photosynthesis, and is also a member of the Royal Society of Science in Sweden. So Leif, the floor is yours.
Thank you very much, Muriel, for this very kind introduction, and thank you also for inviting me to give the talk. I enjoyed this meeting. It's great to see how a joint grant is fostering or rising in the entire community, creating new collaborations that hopefully will lead to more substantially funded individual projects. So what I've talked about today is mechanism of artificial photosynthesis. So this is Ångström Laboratory where I work, and also most of the Swedish Consortium for Artificial Photosynthesis work in this part of the building. We started long ago with building mimics of the electron donor side of photosystem 2 with the chlorophylls, and the first donor is a tyrosine Z. When it's oxidized by the chlorophylls, it transfers a proton to nearby histidine, and later then it takes back an electron from the manganese cluster, which is a water oxidation catalyst. Oops, sorry, I must have. So we made models of this with ruthenium instead of porphyrin, but the proton-coupled events of the tyrosine was there. So I will talk about proton-coupled electron transfer and how important it is for molecular catalysts as well. And I will also talk about some hybrid systems of inorganic materials with molecular catalysts. So this is basically the outline. And I will also eventually go back to some excited states in exciton diffusion in polymer dots, if time allows. So molecular catalysts, most of the catalysts that are used today in the field of artificial photosynthesis, the vast majority are heterogeneous. And molecular catalysts have a struggle to keep up with those, but there are some good examples where molecular catalysts have actually been quite successful. And I think in the long run, they have the potential to be much better than the materials. And one of the arguments I have is that especially for more complicated chemistry, like doing CO2 reduction compared to proton reduction to hydrogen, is that we're working with very, very small molecules. And if you look on the CO2 reduction in an enzyme, CO dehydrogenase, you see how the CO2 molecule is held together with interaction with two different metal centers and several different ligand interactions. So it's a tight network in 3 dimensions where distances and angles are controlled with distances on a length scale of much less than 1/10 of an Ångström precision. This is very hard to achieve with even with nanomaterials. So for comparison, I just showed the size of a very small nanoparticle. And it's very hard to imagine how you can control length scale that short and also 3-dimensional structure. with only materials. But, and molecules, of course, have, you can tune them much more, but if you have many knobs to turn, it's harder to turn them right. But eventually, I hope that we will get there. So, enzymes are very good at doing this. They are molecular catalysts. Why are they so much better than the synthetic catalysts that we use, mostly? This we don't know, but we can have some clues. And one of the points that they are doing that is very good, which is important for solar fuels, is the coupling of electrons and protons. Because of course, when you're doing solar fuels, you're making hydrogen or reducing CO2, you need to add electrons and protons together. More than one electron, more than one proton. And oxidizing water, of course, you need to take away several electrons and protons from water. So, PECET, proton coupled electron transfer, why is it so important? It allows for charge neutral steps. You don't need to go to high energy potentially high energy intermediates of single electron transfer or single proton transfer. And you can keep charge neutrality. This is especially important when you are dealing with multi-electron processes, because if you try to accumulate holes or electrons without proton compensation, you're going to build up charge and make it harder and harder to add the next electron and next proton. Very important for catalysis. And of course, you see in nature many examples where you, for example, couple long-distance electron transfer and transport to a proton translocation to generate ATP. This is an example of a copper electrochemistry. We use electrochemical CO2 reduction in proton-coupled electron transfer schemes. You can also do activation of CH and NH-OH bonds in photoredox catalysis by proton-coupled electron transfer instead of the traditional hydrogen atom transfer, and reach much higher effective bond dissociation than you do with the traditional methods, and also different kind of selectivity. So, how to describe proton-coupled electron transfer? If the electron and proton are transferred in a single step, you can describe it with a similar, of course, if they transfer in one step, electron first, you have Marcus theory, and you have a similar related theory for proton transfer. Also, if they transfer in a single step, concerted, you have a similar theory like the Marcus electron transfer theory. The idea is that if you transfer charge in solution, you polarize the environment. And if the charge is on the left and then the charge goes on the right, the polarization needs to change from the left side to the right side. And you need to find some compromise in the middle with some semi-polarized state where the energy of the reactant and product states are the same. In the free energy landscape, you draw the famous Marcus curves, the blue one for the reactant and the red one for the product. And when the solvent changes polarization, the energy goes up and down. This is the equilibrium position. And eventually you come to a crossing point where you have equal energy. Isoenergetic reaction is allowed to go into the product. And here the proton is tunneling. And you go down. The difference here is that both electron and proton tunnel at the same transition state. And in the small insets here, you see a different coordinate, which is just a proton tunneling coordinate. The proton needs to go from the left side, from, for example, sitting on an oxygen to going on the nitrogen. And when it's back here, it's not very favorable. And here it's very favorable. And here you have somewhere in the middle where the proton can tunnel. And you see the wave functions indicated here. And it's very important to have a good overlap between the wave functions. So the wave function overlap is critical to determine the rate of proton-coupled electron transfer. And we demonstrated the first series of molecules that probe the distance dependence of proton-coupled electron transfer. So here we have the ruthenium as a sensitizer, which we photo-oxidized with a laser flash and an acceptor. And then we had different tyrosine units with an internal base linked with different oxygen-nitrogen distances sitting here. And for these four molecules, the distance dependence was huge. So over only 0.2 angstrom, the rate changed by a factor of 100, giving a beta value, which is a slope of this line, of 27 per angstrom. For those of you who are familiar with electron transfer, the beta values are typically 1 per angstrom. So this is about 30 times more distance dependent. So if you're thinking of designing a catalyst, and your rate determining step of your catalysis is a PCET step. And if you're down here, if you then could make a small modification of your catalyst just to go up here, you would gain a factor of 100 in rate of your catalyst without wasting extra energy. This is just the proton tunneling distances. It doesn't require more free energy input. You could do that, you would like to do that, right? Which means that you need to know where you are. Do you have a PCET reaction step? How can I optimize that tunneling? So I've been arguing, as you see here, for 15 years about this thing, that a concerted reaction is really the favorite part for, you should really design your catalyst so that the rate determining step is a concerted, have low barrier, and you should also make sure that the tunneling distance is good. And this has become quite popular to add these second sphere bases, acid base groups in the vicinity of the metal center to improve catalysis. And, but maybe up till then, maybe we were spending too much time thinking about the electron transfer part of the problem, which is easier, and the proton transfer part is harder. Note that all these effects are ignored in the most common theoretical analysis of solar fuels catalysis. But a factor of 100 cannot be ignored. They are not small effects. One example of a well-designed catalyst is the di-iron center of iron hydrogenase. It has a turnover frequency. It produces up to 10,000 hydrogen molecules per second at very low overpotential, meaning low energy losses. And the active site looks like this. It's a little bit unusual ligands for being a living organism. And it has a nitrogen here, and I mean, that can be protonated. And when it's protonated and reduced, it's believed the proton is transferred to the iron center, forming this hydride. So this is a critical part of the mechanism. Then it can be protonated again, and here you see then you have a proton and a hydride looking at each other, ready to form a bond. So that's the proposed ideas of the mechanism of hydrogenases. If you look at, there are by now several hundred molecules made, inspired by these sites, that are shown to make hydrogen, but much less efficiently, much less rapidly. They're not at all as good. And one of them is this, looks very similar. And the question is this nitrogen, protonated nitrogen, is it able to form these hydride species? Initially, it could be it could be terminal hydride and then swings back to bridging hydrides. We were looking at several of these complexes by time result infrared spectroscopy. So basically, it's a nanosecond laser flash photolysis, but instead of the xenon lamp, we have an infrared quantum cascade laser and an infrared detector to look at the signals. So we can photooxidize the ruthenium complex with a donor in about 100 nanosecond, and in less than a microsecond, it has transferred the electron to the catalyst, and then we can see what happens. And we can do it in the presence of acid. So what we asked ourselves was, there were groups claiming that this shuttling mechanism of proton forming the hydride was working also in this synthetic complex. The turnover frequency in electrochemical experiments were estimated to be 1,000 to 10,000 per second. So the mechanism would be one electron in, one proton here, then it shuttles to form the hydride, and then you can reduce and protonate again. We thought, okay, can we see this shuttling occurring? We should be able to see this with infrared spectroscopy because of the very nice carbonyl groups. So we did some, with the laser experiments, we couldn't see any evidence. It was too slow. So we had to go to slower timescales and stop flow. And to see, and simply we had an excess cobaltocene as a reductant and some acid. And we could, sure enough, we could generate this singly reduced, singly protonated state. And we were looking at that, and it stayed for a second. And what we actually saw, we think, is turnover going back to the starting state and making hydrogen. And if this is stable on a second without shuttling the proton, it cannot sustain catalysis of 10 to 3 to 10 to 4 per second. So this is direct evidence that this mechanism is not right. This complex does not work with this mechanism. So acid-base groups in the second coordination sphere may look good on paper, but there's no guarantee they're going to work. It's very sensitive with distances, orientations, and energetics, of course. More recently, this was in the summer, we worked on a system that actually does work. So these OH groups in the coordination sphere of a manganese tricarbonyl BIP complex for CO2 reduction. Interestingly, this makes both CO and formate in different, and our postdoc, Samir Chattopadhyay, he could find several intermediates in this mechanistic cycle, including the ones on the pathway going to formate. So he could see the direct formation of manganese hydride followed by CO2 insertion to make the formato complex. And there he found direct evidence that the proton that is used to form that hydride comes from this ligand. So you could see the difference in infrared spectroscopy. So this was about proton tunneling in PCT. The energetic requirements here and the balance between the different mechanisms, stepwise versus concerted, is very important. So you can go in different ways. Electron transfer first, followed by proton transfer first, followed by electron transfer, or a concerted. And experimentally, it's not necessarily easy. Mostly, it's not easy to decide definitely which pathway it goes. But this cartoon here shows how you go from in this case, a tryptophan with a base to the tryptophan radical where the proton is transferred. This is a direct concerted pathway. And here you have the stepwise mechanism of electron transfer first or proton transfer first. And you can, this is mainly to show that there are completely different transition states involved. And since this is the lowest state, going from here to here should have the lowest barrier because it uses all the free energy available in a single reaction step, while these are much less driving force and often are uphill. So energetically, this should be favored, but at the same time, it could be that it has the complication of having two particles that need to tunnel at the same time. So it's basically, as I see it, a combination of these two factors. A better lower barrier, classical barrier for the concerted reaction on the one hand, but less complicated tunneling for the stepwise mechanism. And the balance between these factors that decide which way it goes. And this may sound complicated, but if you think about it in simple terms, if you have a very strong oxidant, you tend to go electron transfer first. If you have a very strong base, it tends to go proton transfer first. But if both oxidant and base are weak, then you tend to go concerted. And both oxidant and base being weak means that you have an energy-efficient reaction with low overpotential. So this is what you want. This is one of my arguments why you should design your catalyst to go in a concerted pathway. Unfortunately, almost all molecular catalysts seem to show stepwise mechanism. We were asking some years back, is it possible to actually have a metal complex, a metal hydride being oxidized can we go along the diagonal? Instead of electron-proton in different pathways, can we go along the diagonal, either forming or oxidizing the hydride? This is, so here we're not talking about hydrogen atom transfer, but instead separate acceptors for electron and proton, which is what we have in solar fuels. This had not been shown before for a metal hydride, but the metal hydride, as you saw, is a very important intermediate in catalysis. So what we did was take a tungsten hydride as a model complex and see if we can oxidize it with metal BIP complexes and different pyridine bases. We changed different iron and ruthenium oxidants and different pyridine bases to change the driving force for the reaction. And long story short is that we could go along all pathways, stepwise electron transfer first, the proton transfer first, or the concerted, depending on the different strengths of these oxidants and bases. So this is an example of what the data looked like. So with a strong oxidant, we see when we don't have the base or add the base, it doesn't matter. The rate constant is the same on the logarithmic scale. So this is clear signature that it's an electron transfer limited mechanism. Just electron transfer and then the proton goes. When we have a weaker oxidant instead, the iron complex, you see a slope here of 1 per 50 millielectron volt. This is exactly what you expect from Marcus' theory for low driving force reaction. This is a clear signature of a concerted reaction. When we have an intermediate oxidant, we see that it still have the same 1 per 50 millielectron volt, but it's faster. This is 150 millivolts stronger oxidant, the gray one compared to the yellow. 150 millivolts correspond to 2.5 pH units. For a concerted reaction, it shouldn't matter if you put extra driving force on the electron or on the proton. You should get the same rate. And indeed, if we shift that line by 2.5 pK units, they line up. This shows a very clear symmetric dependence of the concerted reaction. How can we increase the rate? The rates were not that impressive without wasting more free energy. Yeah, we made linked compounds instead to increase the proton tunneling probability. And in some comparisons, we could actually get more than 1,000-fold higher rates. And I'm not going to test you on all the numbers here, but this just basically shows you that the different slopes here show that you have different mechanisms going from the first proton transfer to concerted to electron transfer first as we increase the strength of the oxidant. And this is the same data, but instead of the different pK values, we plot the different pK values there and the different oxidant strengths there. And we see the expected slopes for the different mechanistic regions. This was the first system that where we could show all the three mechanisms for the same system by systematic variation of the driving force. And I think to say that this is the best example of a determination of the mechanism, and in this case using free energy dependence. The numbers here are kinetic isotope effects. So we have an inverted isotope effects because of the different 0-point energies of the hydride versus the pyridinium. Here we have a more normal effect for a concerted reaction, and here essentially no effect because it's limited by electron transfer. So driving force dependence. Marcus theory for electron transfer. That was one of the most important points with the Marcus theory, describing what is reaction coordinate and how the driving force the driving force dependence of the rate constant. And the most controversial part of his theory was that the rate goes up, it levels out, but then it goes down again in the inverted region. And it took 30 years before it was finally experimentally proven and accepted. The inverted region is when the driving force is larger than the reorganizational energy. You see, for a spectroscopist, it means that the potential energy surfaces are nested. So this lies inside that one. So then instead of having a barrier on this side, you get a barrier on the left side instead. And this is very important to keep charge separation in photosynthesis, because you can have a large drive. You can store a lot of energy without just losing it at the same time. You have a lot of free energy, but still a barrier. So this is an important concept. For proton-coupled electron transfer, it was predicted by my collaboration partners, Sharon Hammes-Schiffer, now at Princeton. She predicted that you're probably not going to see this for proton-coupled electron transfer, because you can just put more energy, put the extra energy in the inverted region into vibrations. So if you just put 1 quantum, 2 quanta, 3 quanta into the proton vibration, you're going to have a barrierless recombination anyway, right? And these effects, I mean, you can argue why, but we can talk about it later, but these effects are much more important for a proton than for a heavy nuclei in electron transfer. So together with Jim Mayer's group made this series of molecules, an anthracene that is excited, or a cyanoanthracene, and then it is oxidized in a proton-coupled electron transfer fashion by a phenol-pyridine. So the phenol is oxidized, the proton goes to the nitrogen. And we have substituents here. So we have 8 different compounds with different driving forces. And we can see that the forward reaction was in the Marcus normal region. And the back reaction for these compounds in 3 different solvents were in the Marcus inverted region, was still concerted reaction. And that showed that under certain circumstances at least, also PCET can show a Marcus inverted region. For the experts in the audience, we are fully aware that you should not put data in different solvents in the same Marcus plot. This is why this is not a fitted line, it's an indicative region of behavior. So you should, if you should do it more rigorously, we should have multiple curves here. But the solvent dependence itself is an extremely good proof that it is inverted region. It's just a question, you have to just give some idea on how to think about those data in the line. But this is in science, so you cannot go into detail in the plot. So we found this by looking at the femtosecond visible and mid-infrared. It was relatively straightforward. We had a local excited state on the anthracene, lived for, on the time scale of 5 to 20 picosecond, depending on which complex we looked at. And that was easily recognized as an anthracene with stimulated emission. Then we had a Charles-separated state at a very different lifetime, depending on the solvent and which molecule we had. But it has the very clear signatures here of the anthracene reduced state, with some extra contribution here of phenoxyradical. The cyano group was a nice probe in the mid-infrared, and you bleached the ground state. In the excited state, it shifted out down here, and then when it was reduced, it shifted back a little bit. All consistent. The kinetic traces here show that in dichloromethane, tried 1, 2, 3, showed this behavior. So 1 was the slowest, 3 was the fastest. Even though this had the highest driving force, this had the lowest driving force. So this really shows inverted region behavior. And when you go to more from polar solvents, the DMF, to dichloromethane, the lifetime of the Charles-separated state becomes much, much longer, because not only does the free energy change, but the reorganization energy goes down, so you get deeper in the inverted region. So this was a very nice result for us. And these molecules showed to have much longer life than we thought. We had several papers on this, and most interestingly, it was a completely unexpected result, complete serendipity. I will not have time to talk about it too much, but it may interest some of the photophysics people in the audience. This is a proton-coupled energy transfer. So when we went to this, this is the, when we go to a rigid medium, for example, of 77 Kelvin glass, the Charles-separated state is destabilized, and we open up for a different reaction, where the excited anthracene can transfer its excitation energy to the phenol-pyridine in its keto form. The enol form is too high in energy. You can see the blue, this is the absorption spectrum of the enol form, this is the absorption spectrum of the anthracene. You cannot go from here to there at 77 Kelvin in 50 picosecond. It's half a volt uphill. Problem is that you can also not transfer the proton without transferring the energy, because it's also more than 0.15 volts uphill, and consequently you never see a direct absorption of the keto form. This would be going from here to here, right? So there's no absorption here. So you see anthracene fluorescence here, no absorption, but you see the fluorescence from what we call local electron-proton transfer state, which is a keto form. So this is clearly sensitized by the anthracene in spite of no overlap. So singlet energy transfer without spectral overlap, but it allows sensitization of dark states thanks to concerted proton transfer. It's a new elementary reaction. I'm good. I have time to even explain. So, why did we see the concerted electron transfer here? Concerted PCET in the Marcus inverted region, in spite of the fact that Sharon had predicted it probably not going to be seen. Well, one thing that she did when she did that prediction, she was thinking about relatively harmonic proton potentials. But if you look on more realistic proton potentials, they look something like this. See the red one is a double well with a relatively low barrier. The effect is that when you look at the blue curve, which is a short-separated state going back to the ground state, and the real ground state is probably down here. This is now with three quanta, 4, 5, 6, and 7. I see with adding 7 quanta gets you to this state where you have a barrierless recombination. But the 7th state is a very oscillatory wave function. So it just cancels out. The total overlap is 0. And the best compromise is 0 to 3 transition here, where you have some barrier, and you don't have the great overlap, but sufficient overlap. Of course, with the 0-0 transition, you have much better overlap, but then you have a much higher barrier. And these effects are there because you have this very anharmonic potential. And it turns out that in Sharon's calculations, many systems actually have much more anharmonic potential than we usually think. And this is the explanation why we saw the inverted region in spite of her earlier prediction. This is not necessarily universal. We are looking to try to design a system that doesn't show the inverted region with more harmonic potential. We'll see if we manage. Okay, enough of PCET. Now, let's talk about quantum hybrid systems. So this is a more detailed story. It's basically a single paper story. First this and then another one on polymer dots. So this was a collaboration with Muriel and Vincent Artero. And we had already started working with copper indium sulfide quantum dots. They're quite tolerant to off-stoichiometric ratios between copper and indium. And we're interested in pushing up the conduction band a little bit with low stoichiometry copper. And they are made by, we can make them in aqueous synthesis, which is nice, benign environmentally. They are quite reducing. And we didn't, the only passivation we had no shell here, but there was just L-cysteine and iodide. And then we're interested to see, could we have a molecular catalyst on this surface and see electron transfer? And could we actually demonstrate that the catalyst is reduced? Because up to that time in the field, no one had shown that. They assumed that if the quantum dot is quenched, it must be electron transfer to the catalyst. There are many reasons why things can be quenched. So I think we thought that it could be a good thing to show. And if you look at the absorption spectra here in black, you see not a very distinct spectrum, but this is typical for most quantum dots. And you see photoluminescence here in the red. So the band gap here is around 2.4 electron volts, 520 nanometers. So with these quantum dots, we could actually show the signature of the reduced catalyst here by the infrared absorptions of the carbonyls. But then in collaboration here, we worked instead of a better catalyst, which is a cobalt catalyst that they developed in Grenoble. And when we did the photocatalytic experiments here, we could see that we got quite decent hydrogen generation, and over 8,000 turnovers per catalyst. So they were quite robust. So this is 24 hours irradiation. What is interesting here is that we use two different catalysts, one with a designed anchoring group, one without that anchoring group, and they show essentially the same results. This surprised us. So one is attached, one we thought was not attached, but they work the same. Another thing which is interesting is, of course, that with just 1 micromolar, we get about the same result as with 10 micromolar. So adding more catalysts doesn't really help in this range. So 1 micromolar seems to be sufficient to take care of the reducing equivalents. And then, of course, that means that the total number per catalyst is best for the low catalyst concentration. We looked then first to characterize the binding here by fluorescence spectroscopy. So we're looking at the quantum dot fluorescence, and this is with different concentrations of the quantum dots and the two different catalysts here. And we see this upward curvature, which is exponential. So if you take the logarithm of that fluorescence intensity ratio, we get very nice straight lines up to quite large numbers. So this can be explained by a Poisson distribution of quenches over quantum dot particles. So it's enough with 1 catalyst to totally quench the quantum dot. In the lifetime measurements, we saw no difference in fluorescence lifetime, because then we only see the ones that don't have a quencher. If you assume a Poisson distribution, then the probability that the quantum dot has no quencher decreases exponentially with an average number of quenchers per quantum dot. That means that the fluorescence ratio F0 over F increases exponentially. This fits very well with the data, and if we normalize for the quantum dot concentration, here we get essentially the same slopes. Here we get a little bit more variation, but it shows that even with about 1 micromolar catalyst and a little bit less than 1 micromolar quantum dots, we get almost essentially complete binding, even with a compound with no binding group. So they really like each other. And this is interesting, because usually most people say that the limiting factor in such systems is the electron transfer from quantum dot to catalyst, because they need to diffuse together. That doesn't seem to be right here. It's clearly not right here. In transient absorption spectroscopy, we could also see direct evidence. So this is about the average number of quenchers is 0.7. So here we see in the mid-infrared, we see in blue without catalysts, and green and red the two different catalysts. They're indistinguishable, but they're clearly faster. We see the electrons in the conduction band disappear faster than presumably because of they reduce the catalyst. The ground state bleach recovery see a similar increase in rate, and they end up in a positive absorption. And if you look after 2 nanoseconds at the spectra, you'll see that there is still a bleach here without the catalyst, but with the catalyst you see an increased absorption here, which we know from the reference measurement of spectrophotochemistry is the reduced catalyst. The direct observation of the reduced catalyst. So it's clear that the change in dynamics is really because of electron transfer to the catalyst. And this is on a time scale of average lifetime of about 10 picoseconds for the electron transfer. So I didn't talk about that, but we assigned the different bands in the transient absorption of the Q dots. We have a strong binding of very different molecules. We tried with molecules with opposite charge, they bind. We tried molecules with no charge, they bind. Not exactly the same, but similar-ish. So if you try ferricyanide, methyl viologen, and an uncharged iron complex, and they all bind, we cannot blame it on electrostatics. And I'm a physical chemist, so what do I know? But I can't really see the chemical common denominator between these three, except that they're able to quench the quantum dots. So I don't understand the nature of this binding, which is interesting, but it works in our favor. We have direct evidence for ultrafast electron transfer catalyst, and this is not rate limiting for photocatalysis in these systems. And the photocatalytic performance was comparable to those that have a zinc sulfide shell to protect from charge recombination. So we can, of course, debate if this is which one is better, but they were surprisingly good. Finally, a little story on exciton diffusion in polymer dots. First, what is polymer dots? You know about organic semiconductors. They are used in solar cells, for example, and for the photocatalysis. The good point of making them in small dots, nanodots, less than 100 nanometers, is that you have a shorter diffusion length that is needed to get from where you excite it to the surface where catalysis happens. So you have a better chance of doing charge separation at the surface than if you have a bulk material or thin film. In general, they are interesting materials. These P dots, they're easily to tune, easy to synthesize. You can modify them. Relatively good electron and hole mobility. And my colleague here in Uppsala, Hein Tiang, he was the first to show proton reduction many years ago with his P dots, that he called them. Okay, they're also biocompatible, but that's not my talk. So the question here, if you now form an exciton somewhere in the polymer dot, they can recombine in the bulk, they can recombine at the surface, but they can also dissociate at the surface. And the question is, what is the fraction, how many of these excitons are actually reaching the surface where they can do useful chemistry? There were 2 previous studies of the PFBT molecule, which is a common polymer. We were not very happy with those. It only had fluorescence intensity data. Some of this was very confusing. For the aficionados can look at this plot and tell me how the hell that is supposed to make sense. And they didn't agree with each other. There were also some large defects. So we thought that can we do better? We took the PFBT polymers together with a polystyrene PEG to stabilize it. So PEG stabilizers with a hydrophobic core. And then we doped it with small amounts of perylene red as quencher. The PFBT perylene red has a first radius of about 3 nanometers. And then we're looking at both steady state and time resolved spectral fluorescence to see if we can get a consistent picture from both experiments. And we did analytical fits instead of computer simulations of the dynamics to fit the data. So the hydrodynamic radius is 50 nanometers from DLS. The core, the hydrophobic core, is less than 10 nanometers based on the relative masses that we know. For 1-to-1 ratio of these two is about 8.5, I think. And when we have 3 times more of 3 times this and 1 times that, the core is a little bit smaller than 8.5. Okay. In the absorption spectrum, you see PFBT, and when you add small amounts of the quencher, you have to squint to see the absorption of the quencher, but it's here. But in the fluorescence, it's very clear that you quench the donor fluorescence, and instead you get the fluorescence from the acceptor. But if you look somewhere here in the middle, you continue to quench the donor, but you don't get more fluorescence intensity from the acceptor. So here we think that if you go more than 15 nanomolar or something like that, we start getting aggregation, the interaction between the perylene reds. So it turned out we avoided that region. And here we assume a Poisson distribution of quenchers. The difference in the previous case is that we cannot assume that the fluorescence is entirely quenched just because they are in the same volume. Instead, we have to use the we choose to use the Infeld-Attachia model that was developed for fluorescence quenching in micelles. This assumes a Poisson distribution of quenchers over micelles, and the lifetimes or the time traces are fitted by this equation where you have the decay rate constant without quencher, average number of quenchers per micelle, or in this case per volume that the exciton has time to explore. You have the quenching rate constant for one quencher in the volume. And this is just to fit without quencher, and we had the bi-exponential. We needed 2 exponents to fit the data, so we pragmatically just said, okay, let's take 2 of these terms and add them together, one with this lifetime, one with that lifetime. We assume that the KQ is the same. This has reflect a slight heterogeneity in the environment. This fitted very well, data. What is different from the case with micelles is that the core volume can be larger than the exciton diffusion volume. In micelles, it's clear that it has time to explore the entire micelles, but what if the exciton cannot diffuses too slowly, so it actually decays before it reaches the surface? Then the volume that we get out from this occupancy will be smaller than the physical volume of the core. So the results here are simply like this, with 3 different concentrations. With 1-to-1 PFPT and PEG, we get very good correspondence of the occupancy and the relative concentration, and a quenching rate constant of about 0.5 per nanosecond. When we have the somewhat smaller cores, because we have more of the PEG polymer, we get about twice the quenching rate constant, which makes sense because the core is smaller. It's going to quench faster. And a little bit less good correspondence here, but it's okay. And then we get quenching volumes in the 2 different cases of 2,300 cubic nanometers. This is equivalent to 8.2 and 6.6 nanometer spheres. This fits within all experimental error of our estimate of how large our cores are. We think that these volumes are actually limited by the cores. So good. This is a very efficient exciton diffusion in the entire core. So, but what is then how can we compare this with measured exciton diffusion lengths? Exciton diffusion length is the root mean square displacement, typical textbook definition. But the question is, if you have a root mean square displacement of, let's say, 8 nanometers, it doesn't mean necessarily that you explore an entire ball of 8 nanometers. What's the relation here between these? Look here, this is a random walk in 3 dimensions. If I don't know exactly where this is supposed to start, but let's say that this starts here and ends there. This would be the root mean square displacement. And you clearly see that most of this area is void. It hasn't been there. This is another picture. If you want to see for this random walk, how large volume has it explored, then you have to draw, then you see the particle moving here. And in our case, the thickness of that tube is going to be determined by the first radius. If there is a quencher nearby and the first radius is 3 nanometers, then it's going to be quenched. Otherwise, it's not. So then it explores this volume. What is that volume for a root mean square displacement of a certain number? sounded to me like difficult problem, interesting problem. Someone must have solved this in a completely different context than polymer dots. I looked for a long time. I didn't use the right keywords. I can tell you what keywords I should have used, but you will see it. It's a Wiener sausage volume. Because these are called Wiener trajectories. And if you then put the volume here, this is your Wiener sausage. Ha, ha, ha. How funny they can be. Statistical physics. Our student loved it, of course. So this is basically the thickness of the sausage here is, the slices here are determined by the Förster radius. So this has been apparently a problem in statistical physics since the 1930s, and this is a very nice paper. I could understand the important parts in Journal of Statistical Physics. Amazing. And from the equations they presented for three-dimensional, the relation between volume and the mean square displacement is this, 2.1 times the Förster radius. It means that we get an exciton diffusion length of 90 nanometers, which is about 1.5 and 2 times longer than was reported in the previous studies. And I think, we still have to remember that it's limited by, if our polymer dots would be larger, the volumes may be larger, and maybe the real exciton diffusion length is even longer. So we used an analytical solution to time-resolve quenching data and got satisfactory fits. And it seems that the exciton are able to explore the entire core volume. Much longer diffusion lengths suggested, which means that, the bottom line, the exciton should have a high probability to reach the surface, which is important for photocatalytic applications. And with that, I'd like to thank all the people involved at Uppsala, my senior colleagues in Uppsala for different things, Vincent Muriel at Grenoble, Princeton, Sharon Hans Schiffer and a group, Yale, Jim Mayer and his group, the people who gave us money, and you for your attention. And a shameless advertising. I'm associated for ACS Artificial Photosynthesis, a new journal, which is in collaboration with Westlake and Dalian Institute of Chemical Physics. So these are editor-in-chief, and we are the 3 associate editors. We accept all high-quality manuscripts in all areas related to artificial photosynthesis. So I encourage you to consider our journal for your next submission. Thank you.
Thank you, Leif. So we have time for some questions.
So thank you very much, Leif, for a really wonderful lecture. Enjoyed it very much. I wanted to go back to the inverted region for the proton-coupled electron transfer that you showed us. You really convincingly demonstrated how important the reorganization energy was in having this proton-coupled event. And then I noticed that you actually chose solvents that had very low reorganization energies because they were non-polar solvents like dichloromethane. And so I was wondering if in this case you weren't decoupling the electron transfer and the proton transfer, which kind of brought you back a little bit more to something similar to the intramolecular inverted region seen by Gerhard Close and Miller.
It's an excellent comment. So we have done this all from DMF down to toluene. And of course, what happens when you go to too low polarity solvent, we start destabilizing the charge separated states. So then we have this proton-coupled energy transfer competing. But in these solvents, we didn't see that. It's still a concerted reaction. You may think that dichloromethane is, it's actually quite polar. So it's not, you still have a large polarization of the solvent because of the charge transfer. Then if you go to the classical Marcus theory based on dielectric continuum, you may wonder what happens in toluene. In principle, toluene or alkanes should have zero reorganization energy. This has been shown by lots of theoreticians that this is not the case. The reorganization is much higher than the continuum model says. I don't have a personal opinion on that from our data, but I think this would certainly apply also for a PCT reaction. I think the reorganization energy is larger than at least many cases.
Right, thank you.
Other question?
Thanks, Lev, for the talk. It's interesting that you started with something molecular and then you ended up with something material. And I think my visualization got lost now with the P dots because of course you first talk about this exciton and forming, let's say, the charge on the surface, but now I miss the charge accumulation needed to do, let's say, proton reduction. So I don't know if you can comment on how these things would change now that you need to accumulate 2 electrons and 2 protons, for example, to do hydrogen evolution.
Yeah, no, so the transition from molecules to more materials probably reflects my neurodegeneration, but but seriously, obviously here we are looking at an isolated part of the problem, just the excited states. So one can discuss, are we really accumulating charge in the P dot? We think that we don't really have separate charges. We have excitons in the P dots. Do we have 2 excitons at the same time under solar radiation? Probably not. They have too short lifetime. So the accumulation of charge has to happen here at the catalyst, which we didn't study in this paper. We have, of course, studied in other papers. But if we have a platinum particle there, it's hard to count the electrons. But for sure, the systems as such work for proton reduction and CO2 reduction. My colleague Heining has shown that. But for the accumulation of charges, we have to rely on the catalyst part.
And does it also include the part where you now oxidize something to have the complete one, or it's sacrificial source for this?
Yeah, in his experiment on photocatalysis, they have been sacrificial, but he has managed to get some hydrogen peroxide. So not a good system yet that combines the two, but as separate half reactions. And Kevin Sivula has some very nice work where he actually used organic material for water oxidation. It sounds like a suicide thing, because they're usually easily oxidized, but he's shown that with the right tricks, you can actually get them to last quite well.
Thanks.
Thank you. Any other question? Yes.
Yes, sorry. Thank you very much for your beautiful talk, and so giving a lot of fundamental aspects on photophysics. And I have a naive question regarding also this proton-coupled electron transfer. In my mind, I thought that proton transfer could be also driven by tunneling effect, and so very quick, I would say, process. And so I was wondering to which extent here you are not considering, for instance, water, where also it can drive at a very long distance some proton transfer. So my first question is how tunneling effect can be taken into account, to which extent also water can also help, this proton transfer. And finally, have you tried also to investigate this proton transfer in deuterated or with deuterated molecules?
Yeah, sorry, I was trying to get back to that.
Sorry.
No, you're absolutely right. The proton is tunneling here, But and of course, the tunneling step itself is very fast, but when it tunnels, but there's a probability which depends on distance. So when I said that, so with this rate dependence on proton tunneling distance, this is a probability. It's not a slow migration of the proton. It's really one-step tunneling in all cases. We have shown this in some cases. We have some small synthetic proteins, for example, where we have shown that the buffer is not the proton acceptor, it's water. So we can, by simply varying the concentration, for example, we can see that it must be water that is an immediate proton acceptor and so on. But yes, you're absolutely right there that water can be very important. In some of these systems that I showed with the inverted region, for example, we didn't have water. But in these small proteins, we have some intricate effects of water there because there we have a tyrosine or tryptophan buried with very little solvent exposure, and still it seems that they are oxidized happily. So there we think that we have some indication that some partial unfolding of a chain that allows one water molecule to come in and act like a proton bridge, if you want. Maybe this is similar to what you think. So absolutely, you're right.
Thank you, Leif. So, thank you for this very nice talk. Okay, so the next talk will be the highlight on the chirality axis, and it will be given by Cyriac Genet. So Cyriac is CNRS Research Director at the Institute of Supramolecular Science and Engineering in Strasbourg. His research activities deal with light matter interaction in complex systems using tailored light to reveal new phenomena in contexts ranging from chiral light matter coupling, stochastic thermodynamics, and quantum materials. So his talk today will be on optical twist on chiral systems.
Thank you very much. Okay, so thank you very much. Thank you for this kind invitation to talk about chirality in maybe in the broad sense, but clearly with a physics perspective. So I'm working in Strasbourg, and I am part of the moonshot Tornado, which deals within the PEPR along those problematics of chiral light matter interactions. So to start my, sorry, I'm just checking the, yes. To start the talk, I will go with Kelvin's definition of chirality, which is a very simple definition, but it's a very rich definition because it gives an operational way of characterizing a chiral system, and it also implies the fact that chirality has to be understood as the possibility to have pairs of objects which are mirror imaged. And we know that this simple definition actually accompanied the fantastic history of chirality throughout the 19th century, from hemihedral crystals to chiral molecules. And also the way chirality is absolutely central in a molecular chemistry as a way to encode functions into forms, and through that to perform replication through recognition. So the concept of chirality is very important. Jacques Ress, has written a beautiful lecture on those concepts quite some time ago, 20 years ago, which I strongly recommend. So in fact, there is a paradox behind chirality, is the actual existence of enantiomeric forms. And this has been recognized in the advent in the developments of quantum physics by Friedrich Hund, who realized that the molecular Hamiltonian is parity even, and so does not yield the possibility of having molecular enantiomers. And so Hund conceived the problem of the existence of chiral chemical forms as a metastable problem, where you have where enantiomers, left or right, corresponds to metastable states of a global bipotential. And so that the existence and the fact that you can find in nature chiral systems is a problem of spontaneous symmetry breaking. So it's a problem of initial localization. And the stability, so this is for the existence, and the stability of the enantiomeric forms comes from the possibility to have extremely long tunneling time in the interconversion between left or right-handed forms. So Martin Kwak, who has worked a lot around those concepts, coins this as a de facto picture, spontaneous symmetry breaking. Chemists would call this kinetic control, and the physicists are really looking after external systematic bias that could explain the lift of degeneracy between enantiomeric form, and this is called as the délégué picture. Thermodynamic control, in other way, proposing you a solution to explain why one enantiomeric form is more stable, thus more present in nature than another. And there is a very large activity in physics trying to find some representative chiral coupling mechanisms that could explain this délégué picture. So this is very much consistent with Pasteur's view, which I synthesize in this way. You have a chiral system immersed in a chiral environment. You have vertices of interactions, and those vertices of interactions become enantio-dependent, both from the environmental and system point of view. And this kind of picture should lead to the possibility of chiral symmetry breaking, chiralization patterns, asymmetric evolutions. There are many examples in chemistry actually showing this at play. I just give two examples. The possibility to perform asymmetric synthesis using chiral light, so circularly polarized light irradiation, and also the possibility to perform chiral liquid crystal NMR that Philippe Lezeau has developed a lot in Saclay. So in nano-optics, there was a surge of proposals, experiments, theory work, all aiming at searching for such coupling mechanisms. There can be purely optical problematics like optical spin-orbit interactions, more related to chiroptical spectroscopy, trying to find new chiroptical systems where you could perform enhanced chiroptical spectroscopy. But now, even recently, moving towards a quantum regime with chiral quantum sensing and chiral quantum materials. I will give a few examples. If I want to address more fundamentally this reason why nano-optics has been so much concerned about chiral light-matter interactions, I think it comes from the fact that an interface already yields an interesting chiral signature. If you break 3D invariance by having an interface, and if you let an optical mode propagating at the interface, you are essentially forced to get complex wave vector with a very strong imaginary component perpendicular to the surface. This is well known, this is evanescent optics. And the consequence of that is that you need to allow your electric field to be longitudinally polarized. That means to have a vectorial component along the direction of propagation. And when you characterize the spin density of this light mode propagating at the interface, so you know that if you have propagating light, the spin density, which is connected with the helicity, is directed either along the propagation or opposite to the propagation direction of light, circularly polarized light being left-handed or right-handed. If you do the same calculation for a mode at the evanescent at the interface, you end up with a spin density which is transverse with respect to the direction of propagation and which is locked to the direction of propagation. Locking is represented by the fact that if you move rightward, the spin points towards you, and if you move leftward, the spin will be in the opposite direction. And this is a clear manifestation of a mirror symmetry breaking. And it can manifest itself directly in the interaction context. If you let a spin polarized dipole, a rotating dipole, and that you immerse this dipole in such an evanescent mode, you end up in having two different coupling rates, or emission rates, for instance, depending on the propagation direction of the mode. So this is exactly this is the simplest example of a chiral coupling that you can implement in near-field optics. Near-field optics is also well known for giving you the possibility to tailor optical mode by nanostructuring the interface of your interface. And this is also very rich from a chiral point of view, because in fact, when you mill, when you write any topography on an interface, and you shine light on such indentation, for instance, you are confronted with the problem to having source accompanying local frame. That is, if you want to describe the resulting effect of the light excited on that system, you will adopt a point-light perspective where light is launched at each side of your structure. And then you integrate over the extension of your structure the resulting field. And this integration has an interesting property. This dyadic term, in fact, tells you that the polarization state of the excited light will become space variant. And this spatial variation, once integrated over any kind of topography, will lead to specific geometric phases. And this is connected immediately with chirality because it is very simple to, for instance, mill chiral nanostructures on metal film. And by the sake of this source accompanying frame, you can calculate the incoupling matrix that you will get with such structures. And you end up in realizing that the resulting near-field mode, that is the mode excited on the surface, bears an azimuthal phase, which is nothing but the orbital angular momentum of light. So you can induce orbital angular momentum of light playing with chiral nanostructures. And this has been also explored a lot these last decades in nano-optics, and with very interesting possibilities to tailor the near field so that in the far field, that is far away from your nanostructure, the light that you generate is chirally manufactured, if you want. And in this context, these modes are characterized by specific values of orbital angular momenta. These discussions have been reconnected by a way I will now just explain to very, old, ancient, so to say, discussions about the way to quantify and characterize optical chirality. And this work by Lipkin is very famous in optics, where you can end up in characterizing an optical film from the chiral perspective by two quantities, a density and a flow, which obey conservation law for free field situations. If you deal with harmonic fields, those quantities have very simple meaning. The chiral density corresponds to the helicity of light that we know well. The chiral flow is connected with the spin density being associated through the wave vector to the helicity. So these are well-known quantities. But this is much more general, and you can use those quantities to characterize your chiral field. And I think the new interest in those old concepts comes from this paper by Tang and Cohen that decided to re-evaluate circular dichroisms. That is the differential excitation rate you can have between a left-handed or a right-handed molecule immersed in a very generic optical environment. And what Tang and Cohen realized is that the imaginary part of the chiral susceptibility that is naturally engaged in CD response is multiplied by the chiral density, by this K factor, the chiral density, giving the possibility to dream of enhanced chiral spectroscopy as soon as you have designed systems which display chiral densities larger than the chiral density you have in your CD spectrometers, which work with circularly polarized propagating light. This has driven a very strong activity in the field, coined as super chiral fields for such situations where you can enhance the chiral density. And of course, in this context, chiral nanostructures, chiral nanoantennas, chiral nanoparticles have been playing a key role. Now I will discuss a simplified view of a chiral molecule to give you another example of a chiral light-matter interaction. So I take the simplistic view of treating a molecule, a chiral molecule, as a chiral dipole. So a chiral dipole is typically a pair of coupled electric and magnetic dipoles, so that the electric polarizability and magnetic polarizabilities, which are usually associated with the dipole response under the presence of electric and magnetic fields, are now accompanied by cross terms, which are of chiral nature. These are the chiral susceptibilities. The presence of those non-diagonal elements ensure you, following Kelvin's definition, that indeed this system is truly chiral. And with the definition of with the general definition of the chiral light fields that we now have in our hands, we can think about coupling chiral dipoles with chiral light fields. In this context, coupling enantiomers with field enantiomorphs. And one simple way to get access to this coupling is to look at optical forces. In other words, to immerse in such a chiral field, such a chiral dipole, and calculate in the classical regime the Lorentz force law that we know from electrodynamics. And what is extremely interesting is that this force law, once time averaged, decomposes itself in three components. One purely electric response. So this is the standard and well-known optical force component. One magnetic response, which is much smaller. And one response which engages solely the chiral susceptibility of the matter part, the dipole, and a vector field which is connected with the chiral content of the light field. So if you decompose this chiral term in reactive and dissipative components, you end up indeed in separating optical forces in two different components. One reactive one, as I said, directly proportional to the real part of the chiral susceptibility times the gradient of the chiral density of the field, and the dissipative part as the imaginary part of the chiral susceptibility and the chiral flow of the field. So densities and flows and real and imaginary parts of chiral susceptibilities separate in reactive and dissipative components. And the interesting thing about those forces is that they become enantio-dependent. In other words, you simply change the sign of the optical force if you change the enantiomeric form of the system you have put into such chiral fields. And so this is a direct route for chiral all-optical separation. Many groups have been working on this. I just flashed the theoretical proposal of Rob Cameron, who demonstrated indeed that if you flow helicins through chiral light sheets, which are formed playing on the gradient of the chiral density, you can separate in a Stern-Gerlach manner. You can separate the chiral entities. These ideas were thought to be new when we first derived those expressions, but I found out, like always, you always find an old paper by 1996 by Schechtman and Kosirka. It's a beautiful paper. These people were coming from thermal molecular beams, and they already had the idea to send thermal beams of molecules in standing wave pattern with quarter wave plates forming a cavity with the chiral standing wave patterns in a way to separate the thermal beam. Another thing, and I would like to finish the specific presentation with this, another thing which is very interesting with chirality is that it yields some very unexpected and apparently anomalous effect. One example is the possibility to cross linear and angular momenta in the interaction. And again, with the point of view of optical force, this appears very simply. So if you take the standard optical forces, the dissipative component of an optical force, which we know as radiation pressure, is proportional to, let's say, the orbital part of, let's drop the orbital part to the Poynting vector. So a linear force, linear momentum, is associated with the linear momentum of the light field, and the optical torque, so the effect of light that rotates object, is connected with the spin density, so with an angular momentum. So there is a one-to-one match between linear and angular momenta in this non-chiral part. Now, if you look carefully at the shape of those chiral forces, the chiral radiation pressure is associated with an angular momentum. So you have a cross term between angular to linear momentum, and the chiral torque is associated, so this is an angular momentum from the matter part, is associated with the linear momentum from the field part. And so those cross terms are typical and are typical of chirality in the context of interactions. And it gives a very simple ways to propose, these are only proposals, but to propose tricky things that you could perform in optics, in particular to reverse the direction of radiation pressure assisting the reversal through chirality. So you have a chiral object, you shine light on it. Light will not push the object, but light will attract the object towards the source. And you can do the same thing with torques. And these situations are known as pulling forces and left-handed torques. Those kind of problems and situations have driven many researchers on that way. I want to emphasize the beautiful work done by Étienne Bracelet in Bordeaux, Loma. He was the first to demonstrate the possibility to separate chiral objects with such chiral sheets of light. And many people also have been working in this context between the problematics of all optical chiral separation to chiral lateral pulling forces. Today, there is a strong activity, in particular in the group of Daiqing Quan in University of Bonn, trying to push these ideas in the quantum regime. And one idea is, the images have not been going well. So one idea is to push the proposal of Cameron to the quantum regime using chiral van der Waals interactions between chiral molecules and chiral mirrors. And another proposal by Lequin was to use these chiral light matter interactions to drive motionally in specific direction cold atoms. So I would like to, these are examples of what you can do in the chiral regime. So I will summarize in 3 different parts. The problem of chiralization, so this question of understanding the emergence and eventually the stability of chiral forms. Where does the chiral bias come from? Can we find models of thermodynamic control? So this is where our optomechanical models are interesting to set up. The role played on this chiral landscape by nano-optical systems, really the possibility to manipulate transverse spins and orbital, to manipulate spins and orbital angular momenta in specific geometries, and the connection with the field of singular optics. And the chiral forces, I think, gives new opportunities, first to understand precisely what chiral light matter interaction is about, but also to propose new schemes for chiral separations. Thank you very much. I will just finish with thanking the people in my lab in Strasbourg and my collaborators with many members of the Moonshot Tornado. Thank you.
Thank you, Cyriac. We have time for one short question.
Thank you, Cyriac, for this very nice lecture. Just one question at the very beginning of your presentation. I understand very well the kinetic separation between enantiomers, and this hypothesis is easy to understand. It's more difficult on the thermodynamic one. Which would be the origin of the difference of energy between the two enantiomers if they were one?
It's a difficult question. I have a model, but we can discuss it because it will take. So it's difficult. Let's say, imagine let's take a chiral separation in HPLC column. Then it's clear that you have a thermodynamic bias through diffusion, preferred diffusion between left-handed and right-handed molecules diffusing in a chiral polymer. I'm not a chemist, so diffusing in a chiral polymer. So if you want to model the thermodynamics of this system, you will end up necessarily with a biased potential, because time flowing, you will get, if you say my ground state is when the molecule exceeds the system, you will get a preferred ground state for one enantiomer with respect to the other. So in optics, we say you change time in frequencies. And so this is where my model comes from. Optomechanically speaking, it is simple to describe the thermodynamics involving only forces where one chiral molecule is preferentially driven with respect to another one, and spatially driven means spatially separated. So it is possible to design potentials which corresponds to separation. What is complicated is to explain from these kind of models the problem of for instance, the problem of homochirality. So whether this délégué picture of quark is really operational in the problem of homochirality. I don't think my response is very clear, but
so thank you.
Okay, thank you. Thank you very much.
If you have other questions, you will have time later during the cocktail. So now we will have the presentation of the Tornado Moonshot by David Hagenmüller.
Thank you, Muriel. Good afternoon, everyone. So I'm glad to be here to talk a bit about Tornado. Yes, so Tornado is coordinated by Valérie Blanchet from Celia and myself, sorry. Yes, and so Tornado stands for multi-scale, multidimensional approach to chiral light-matter interaction for enhanced chiral optical responses. So in this presentation, in this short presentation, I will just explain quickly those keywords in a at a very basic level. So just a few numbers first. So in Tornado, we are 38 permanent researchers across 14 different research units across France. So we've planned to use 2 ultra-fast LUMA platforms in Bordeaux and Saclay, and 1 Operando platform in Metz. So the project started last year, so in July 2024. And as of now, we've recruited already about 50% of students and postdocs. Okay, so as you know, chirality is a truly universal phenomenon that is present at all scales in nature. So from elementary particles to galaxies. And in between those extremes, we have chiral molecules, supramolecular assemblies, and also chiral nanostructures. So with length scale ranging from nanometer up to hundreds of nanometers and micron scale. And in Tornado, we are typically interested in those length scale and this type of systems that we want to probe in 2 complementary ways. So on one hand, we want to probe the chiral properties of those systems using chiral light. And also the other way around, we want to use chiral matter to shape and control light. So as you know, an object is said to be chiral if it cannot be superimposed onto its mirror image. So the object and its mirror image are called enantiomers. And also these 2 enantiomers have the same physicochemical properties. They can have very different biochemical activities because they interact very differently with chiral receptors. And actually, this distinction lies at the heart of many challenges in chemistry, and one of them is enantioselective synthesis, which, so the goal is to produce a single enantiomer instead of, rather than a racemic mixture. And actually, so the concept of chirality can be extended to light, as Cyriac just explained. And chiral light can be obtained, can be achieved in the lab by structuring the electromagnetic field, so by playing with the spatial inhomogeneity and the polarization degree of freedom of light to make it chiral. So for example, when the polarization vector is rotating, of a wave is rotating, this corresponds to a spin angular momentum with two possible states, so left or right-handed circular polarization. And similarly, when the wavefront phase rotates, one talks about orbital angular momentum, OAM, with different states that can be, with either left or right-handed optical vortices. So the interaction between chiral matter and chiral light actually gives rise to charo-optical effects, and such as circular dichroism, for example, so that's the basic example. And circular dichroism is observed as a difference in absorption between right and left-handed circularly polarized light. So as was mentioned this morning, so this effect is typically weak because of magnetic dipole coupling. And so there are different strategies actually to enhance charo-optical effects. So one powerful strategy is a specific spectroscopic technique called photoelectron circular dichroism, where the idea is to use a circularly polarized light beam to, with frequencies typically from the visible to the extreme UV, to ionize gas phase molecules and then detect an asymmetry in the forward and backward scattering of those photoelectrons. That depends on the interplay between the helicity of light and the handness of molecules. So this effect only depends on the electric dipole coupling, and then it's actually it gives rise to a signal that is enhanced by orders of magnitude. But this can be only used in gas phase actually. So in condensed matter, again, as Cyriac just mentioned, another strategy is to use nanostructures to confine the electromagnetic field in very small volume, so sub-wavelength volume, to enhance the strength of the light-matter coupling and then the chiro-optical response. Yes, so up to now, I've been talking mainly about chirality as a static property, but actually, chirality has also a dynamical aspect that is equally important. And a simple way to understand that is through, for example, molecular vibrations that can give rise to transient chirality in an otherwise achiral molecule. And similarly, an achiral molecule in its ground state configuration can become chiral for a certain amount of time when excited in an electronic excited state by a light beam. So in Tornado, we are interested in a wide range of time scale, ranging from the attosecond, femtosecond, which is the typical time scale for electronic processes, up to microseconds, which is relevant for chemical reactions. And so we are also interested in a broad range of length scale, so from the angstrom up to micrometer, so which is relevant for some systems that we want to study in Tornado, so liquid crystal thin films, for example, and other nanostructures. And another distinctive feature of Tornado is that we want to explore chirality across different phases of matter. So from gas phase molecules, which I just mentioned before, to liquid. Okay, so this is an example. So again, liquid crystal thin films. And to more complicated condensed matter systems like van der Waals heterostructures based on transition metal dechalcogenides, for example. Okay, so let me give you a few key challenges of Tornado very quickly. So we have different work packages. In the first work package, we are mainly interested in chemical reactions, and in particular, to understand the ultra-fast dynamics of photoisomerization, photoracemization chemical reactions, and also to explore the possibility to use chiral optical cavities for asymmetric synthesis, so enantioselective synthesis. In the second work package, we want to identify new type of chiral emitters with enhanced chiral optical responses, and also to understand, to control chiral light through hierarchical nanostructures, and I will give an example in a minute. And the third work package is dedicated to the control of the topological properties of chiral matter with chiral light fields. Okay, so now I would like to highlight very briefly, so Valérie is going to give more details about this tomorrow morning. So this is a recent work, a preliminary work done by two teams at Soleil and ISMO on static photoelectron circular dichroism of binol molecules which have an axial chirality. And this is actually the first step towards future time-resolved experiments where the idea is to study the effect of the torsional motion of this entering torsional motion on chirality. So this is another recent work done in Celia, where they were able to show, to directly observe the chiral potential of a Fenchon molecule using a strong field ionization. In the second work package, there is a recent work done at CBMN where they deposited helicine molecules which have an helical chirality on a silica nanohelix. So this is an example, actually a typical example of hierarchical nanostructure, where the idea, so this is actually a unique platform to study the interplay between chiralities at very different length scales. So also on the theory side, there is a recent work done involving Syriac, where they derived a microscopic model for chiral light matter interactions, strong chiral light matter interactions in a Fabry-Perot cavity. So this shows that the chiral light matter coupling can give rise to a new type of polaritonic states. Another theory work in the third work package, recent theory work. So there is also actually an experimental work, a previous experimental work by the same team, Étienne Bracelet in Loma, looking at thin films of nematic liquid crystals. And this work shows that one can imprint the chiral properties of a light field directly onto the orientation order of a liquid crystal. And lastly, so this recent work done at Celia demonstrated that one can observe exotic quantum states called Floquet states by driving a two-dimensional material, here a tungsten diselenium, with a chiral light field. Okay, so this was very quick. We'll have more details tomorrow, and with this, I'd like to thank you.
So is there any questions? You really would like to have a question? Yes. Thank you.
So the very last example is an ARPES experiment, the one about
exactly, yes.
Okay, yes. Good, thanks.
So now it's time to welcome Stéphane Hacker. So he's coming from the IPCMS of Strasbourg, and he's been working in ultra-fast spectroscopy for years for different applications, fundamental science, energy, and biological applications.
Thank you. Thank you very much for the nice introduction. Yeah, I hope your head is not too much, or your brain is not too much twisted now after all the chirality. Let's come back to, yeah. I'll talk a little bit in the line of what Leif Hammarström indicated. I will try to give you a few examples. Yes, okay. On how ultrafast spectroscopy can really serve for looking into all the photochemical mechanisms, photochemical steps which are important in different contexts related to light energy conversion. So here, I will basically introduce different examples from our research over the last 15 years with different chemistry partners. Our lab in the Institute of Physics and Chemistry of Materials in Strasbourg is physics-based. You will see the members in a minute. But all these collaborations, be it about iron complexes, where with different chemistry partners in France or in Germany, or here the molecules for transparent solar cells with Fabrique Audobel and Frédéric Sauvage in France. A few first announcements. Our team, Biodin, is one of the members for the open user facilities. You'll find our poster here on the left-hand side if you leave the room. These are the laser sources which are available. We perform ultrafast transient absorption and fluorescence spectroscopy in the UV to near infrared spectral domain. Jérémy Léonard is a permanent member of the team, as well as Alexis Boyer. She joined our team this year, and she will develop femtosecond photoelectron spectroscopy. These are the different axes of our research. Retinal protein isomerization in retinal proteins is still active. Margaret and I started this together with Margaret 25 years ago in Lausanne. That's developed into biomimetic photo switches. I won't elaborate more on this. We will go into detail here on this axis on photo energy conversion, photo iron-based photosensitizers. So can iron 2 be the new photosensitizers? And what about these transparent solar cells? How can you make solar cells without light absorbing? Without having them transparent? And I will also, of course, indicate the link with the Moonshot project, energy and environment. Can iron 2 be the new photosensitizers? It's all about making photochemistry with earth-abundant metals. Life also talked about this. Ruthenium is known as a photosizer here. Michael Grätzel with his well-known dye-sensitized Grätzel cells use ruthenium together with a palladium photocatalyst to make hydrogen generation, two-step proton reduction. That is all demonstrated, works well. So yes, one can say that these metals, ruthenium, iridium, platinum, palladium, are gold standards, but they are extremely rare, extremely expensive, and all these technologies have not made it really to on a large-scale development. So there are many chemists who work now since more than 10 years on implementing these photochemical functions with earth-abundant metals like copper, zinc, chromium, and iron. Why not? Why not? You will see. It's extremely difficult because the energetic structure in these in these 3D metals is very different from ruthenium. The fact is simply that it's all about the energetic structure. What I didn't say before is the photochemistry works with the electrons on the ligands. So the photoexcitation promotes electrons from the metal onto the ligands, the so-called metal-to-ligand charge transfer states, and the electrons have to stay there for typically a nanosecond for the photochemistry to occur. So that is easy in ruthenium. because the excitation goes in one of these metal to ligand charge transfer states. Okay, very rapid relaxation to triplet state, but here these so-called, these are states where the metal center, these are the states where the electron will fall back on the metal. They are higher in energy, will not be reached. So the lifetimes here are in the hundreds of nanosecond or microsecond ranges. But in iron, this is the typical iron bispyridine complex. Here the ligand field splitting is much smaller. These metal center complexes are low in energy, and the lifetime here on the triplet state is not longer than 50 femtoseconds. Margette showed this. McCusker, Collet worked a lot on these different systems. This is simply, it comes simply from the fact that the d orbitals on this iron are much smaller, really, than in metals with more, when you talking here about the 4d or 5d electrons. And in these smaller 3d d orbitals, simply the electronic interaction with the ligands is less. And so one talks here about the ligand field splitting, this difference that is smaller. Yes, so there was a partial breakthrough in that area more than 10 years ago. Kenneth Wernmark in Lund was able to design here these iron complexes with coordinated here with carbene. And these carbene ligands provide much more electron density. It was able to increase the ligand field splitting, but not really shift these metal centers upwards. But nevertheless, instead of 50 femtoseconds, the lifetime now was 9 picoseconds, but still too low to make really photosensitizers of it. Nanoseconds would be the aim. And so, there were different approaches to design new molecules with more sigma-donating, pi-accepting ligands. With Philippe Gros, he had the idea, we could enhance the conjugation on the ligands and stabilize the MLCT states. Okay, we can gain here 7 picoseconds. It was shown that you need at least 3 carbon dots in order to come into the in the picosecond range, but it was always, these lifetimes were always limited by the lower lying MC states. So the one parameter that is important is the ligand rigidity, because the transition from ligand centered to metal centered always enlarges the molecule a little bit. And here is a very nice proposal 2 years ago from the University of Illinois with these very rigid ligands. Doesn't need to be a very complex pyridine moieties. Lifetimes of nanosecond were obtained. So it is possible. But okay, I will come back and say, here is what the femtosecond spectroscopy allows us to characterize the excited state lifetimes. Philippe Gros had the idea to replace the pyridines by pyrazines, extend here another phenyl group to the imidazoles. Okay, nice. Here we observe in the transient absorption experiments the excited state features. This is really the signature of the electrons on the ligands. These are all the signatures when the ligands are, the pyrazine ligands are reduced. Also this feature here is related to electrons on the ligand. And the decay of these features tells, okay, 33 picosecond for that molecule. A little bit different design gives 21, 22. Yeah, okay, nice, but not sufficient, not the nanosecond time range. We look back on 10 years of collaboration with Christina Sebri and Philippe Gros. Antonio Monari, who is in the audience, he also contributed initially 25 publications. We studied more than 50 different bidentate, tridentate complexes. Now, this year, we realized that, one actually has to think of mixed MC and MLCT state. The story of is the electron here or there is not the black and white picture is not correct anymore. We really have orbitals with partial localization either on the ligands, either on the iron. And here 100 picosecond lifetimes were obtained. Renanville worked 3 years on these different complexes, made all kinds of femtosecond studies, including mid-infrared spectroscopy, fluorescence, compared radiative rates, you name it, and that, we now conclude that here we have, together with the computations, it's actually, the orbitals are partly delocalized only over the MLCT. The best result we obtained was with Philippe Gros and Maria Chiara Pastore, who designed this molecule here. And this molecule here with the very extended ligands, they pushed forward the so-called the principle of homo-inversion. What you see here is the fact that now the ligand pi orbital is the highest occupied molecular orbital. In particular here, that this state here is 25%, according to Maria Chiara's calculation. 75% of the orbital is ligand-centered, but 25% is iron-centered. And that in contrast to the fully iron-centered, lower-lying homos. This is the situation for all the complexes I discussed before. Now, these ligands have higher energies, and the ligand to homo-LUMO transition here is a charge transfer transition, partially from the MLCT, but partly inter-ligand charge transfer. And the result is that we have here now a complex that has the desired lifetime that it needs, 3.5 nanoseconds. This is simply the luminescence decay, luminescence quantum yield of almost 1%. This is one of the really quite competitive among other iron complexes here. But yeah, we cheat a bit because we mix here very strongly the ligand singlet nature into the spectroscopy. Okay, that is to be published. Let me say a few words now about, this is about the transparent solar cells. The motivation is building integrated photovoltaics. What you will see here now is a new development, bringing Grätzel cells into these semi-transparent solar cells into the near infrared, so that the solar cell is completely transparent. Here, the dyes that we use are absorbing only near infrared, so the average visible transmission is 76%. Color rendering is great, but you see here very disappointing power conversion efficiency, not more than 4%. Yeah, this is clear. These solar cells will never replace silicon on the rooftop, but that's not the purpose. Here, the idea is to use all the larger surfaces, windows, really use our windows, and for making photocurrent, for making electricity. Yeah, so that was this is the project that we are working on with Fabrice Audobel, Frédéric Sauvage, since now 8 years. Ilias Nikolinakos made his PhD study about this. So the ultra-fast mechanisms can be completely characterized here, in particular charge injection rates and yields. We are facing, and I will develop this a little bit, the problem of molecular aggregates and energy transfer competing with charge injection. But we work here on the full of these small prototypes of solar cells, fully assembled with electrolyte and everything. I don't think I have to completely explain what is going on in the solar cells. You have here 2 glass plates. One glass is covered with titanium oxide nanoparticles. That is the design that Grätzel invented. Now we graft here on the titanium oxide nanoparticles infrared absorbing or near infrared absorbing dyes. If you excite them, well, they have just the LUMO level is just above the conduction band edge of titanium oxide. So the electron spontaneously transfers into the titanium oxide, and then the charge migrates through the nanoparticles, is collected by the FTO glass, and the circuit, the electrical circuit is closed. The electrons go back into the electrolyte, and the electrolyte then resets back or regenerates the dye at the end. So we can use one and the same dye several times. You will see in a minute that we will search for the spectroscopic signature of the cation. As soon as this cationic feature arises, we know that the electron has transferred into the solar cell, into the titanium oxide. But the main loss channel are molecular aggregates. And yeah, you will see that in a minute. These are the molecules that Fabrice Audebel and his PhD student Thibaut Baron fabricated. Here now with these push-pull Hagfeld groups, these are the ones that the latest developments not published. But when you graph these dyes on the semiconductor surface, some of them are, yeah, if they are far apart from each other, then they are considered as monomers. But some of them are, yeah, too close to, and then their van der Waals interactions make them form dimers. And in a dimer, well, you have the Davidoff splitting, the excited state, two levels in the excited state appear, and this lower level is now not high enough in energy for the electrons to inject in the conduction band, so that many of these monomers excited will actually not transfer the electrons, but rather due to energy transfer, and this is super efficient here as we showed by spectroscopy, the energy transfer will rather excite these aggregates. And that was identified by Martin Ziolek already 10 years ago as a main loss channel for different solar cells. When we worked initially on cyanide dyes, we also came to the same conclusion. But the situation is a little bit different, or seems to be different for these new decatopyropyrrole dyes. The aggregates appear here in the absorption spectrum. So this is a comparison of the absorption spectrum of the near-infrared absorbing dyes. You see here 700 to 800 nanometers. The dyes in solution this is the full line. But when you graph them on aluminum oxide or titanium oxide, then these additional transitions appear, which are the sign of the aggregates. And the aggregation, the energy transfer can be measured when you look here. This is the fluorescence decay on aluminum oxide, or on titanium oxide you have energy transfer and a carrier injection at the same time. We can work out all the numbers, determine the average energy transfer rate, the injection rate, and we find here, despite the relatively high aggregation number, the injection yield is 80%. And these are the power conversion yields, and you see that the power conversion, is low. Maybe one could improve the device, but it doesn't really change whether or not the aggregates are present. And similarly, so this is transient absorption spectroscopy. After the initial excitation, after 500 femtoseconds, you observe here this feature rising. This is the cationic absorption that prevails actually for a nanosecond or longer. So that really allows us to say, okay, we have here charge injection times of 3 to 15 picoseconds. It's all distributed inhomogeneously because the situation is different. Now again here, no matter how many aggregates we have, the injection yield is very large. So we come to the conclusion, ultrafast spectroscopy reveals all the photochemical scheme for these dye-sensitized solar cells, 50% aggregations. They seem to contribute nevertheless to the photocurrent. It's very likely that they also contribute here to this injection, but that remains to be really proven. And for that purpose, we're now working on the so-called 2D transient absorption experiment, where by making something like a Fourier transformation of the excitation pulses, you can have a very precise or wavelength resolution of how much aggregates contribute to the injection. And some final words now. Yes, all these technology will be integrated or will contribute to in the framework of the Moonshot project that Muriel and Philippe will develop in a minute. 19 different partners. Advanced spectroscopy is present not only in Strasbourg but also in Lille, Paris, here with the Synchro du Soleil, and in Lyon as well. I thank you very much for your attention. Here are the conclusions. We really need the broad choice of femtosecond methods that all the platforms of LUMA allow us to access to terahertz, mid-infrared, up to X-rays emission. Thank you very much for your attention.
Thank you. Thank you. The question on the iron complex that you showed at the end with this very conjugated ligand. So you reached a couple of three nanoseconds or something lifetime, which is similar to what you would expect for a generic organic dye. So the question: do you know if the MC states are even involved there, or do you get the energy so low that it's really more like the ligand-centered transition that dominate, and you could ground state?
Yeah, we can talk about it in detail. So there are within the absorption band, you have many different transitions of different character. I didn't show the transient absorption data, but the transient absorption data depend very much on the excitation energy. You can really promote the classical MLCT transition and have in the transient absorption the signature of ligands of ligands reduced, and they live 5 picoseconds only. So there are relaxation channels that involve the metal centered, but these transitions that I showed responsible for the emission, with the charges really delocalized on the organic ligands, they don't seem to be coupled to the MC states.
Interesting.
Thank you. It's very interesting, but we will have to go soon because we have to be at the top of at 7 o'clock exactly. So maybe we can. You can ask questions during the cocktail. Thank you very much. So then the last talk, 10 minutes exactly.
Or less.
So, okay, just go.
Yeah. Okay, so it's a big task to end this seminar, so we will go on a lighter note. Maybe you will not see even chemical structures or results for this one, but it's really to give you a general overview of the innovation or the challenges that we want to address on our Moonshot project, Synflux Lumicals. So it was already great that Stefan presented our consortium. So this is the biggest consortium among all of the 4 moonshots. So it has 19 teams, and it's really a combination of 2 consortiums before that tried to merge together to try to solve the problem of energy and environment. So I will go back to a more basic idea, because for the past presentations we observed today, we really focus on monochromatic, light-intense sources. And now we actually ask ourselves, can we go back to a more natural source of light, which is sun? And there's really a famous quotation that says that 1 hour of solar irradiation is actually enough to power the annual demand of Earth. So sun at its core presents a relatively good and sustainable potential for supplying our energy demands, and it gives a much more potential compared to the other renewable sources, and it's a sustainable alternative compared to the finite reserves that we have from fossil fuel sources. And the question about sunlight is that it's actually intermittent and dilute, and it's even dispersed unequally among the world. So that's why there's this mismatch of energy supply and energy demand. And the idea is we want to try to get all of this excess energy where the demand is low, and try to capture the solar energy, try to create charge separated and convert it to useful charges, and eventually store it into a chemical form that we can use as a fuel at the end. So photovoltaics have focused on the first two, converting sunlight to electricity, to useful charges. But then we have solar chemistry that tries to store all of this solar energy to chemical bonds, which we can then use on a later stage to serve as a fuel. And because we're on the axis of energy and environment, we wanted to look actually on a much bigger scale of the problem of climate change. And we really have this plot of having CO2 increasing at higher levels now. But if you try to look further or magnify the system, you really see this oscillation of up and down and up and down. And this is really caused by a natural phenomenon of photosynthesis. And I'm glad that Leif didn't introduce it earlier to just give you more of a cartoonish representation of the system. The idea is you have all of these so that's the problem. Okay. You have all of this assembly of chromophores that are assembled in antenna system that then gets or harvests all of this solar energy and directs it to the reaction center, so photosystem 2 and photosystem 1, where now the reaction center separates this charge. The holes are used to oxidize water to oxygen to produce electrons and protons. And then you have a cascade of electrons that are then energized in photosystem 2 that are stored in reducing equivalents in NADH. And of course, you have ATP that enters the Calvin cycle, where CO2 is then transformed to an energy-rich substrate, which is in the form of sugar. So it's very complicated, but I like that more and more people are trying to get inspiration from this complicated system in order to solve our current needs. And really, if you try to look at it on a more childish kind of sense, you have all of these ingredients or building blocks to build all of this photosynthetic apparatus that now we wanted to try to mimic in artificial photosynthesis. So again, the color scheme is the same. We tried actually just to combine all of the chromophores, having them assembled with multi-electronic catalysts, doing reduction or oxidation catalysis. And this can be in the form of photocatalytic devices, where you have this kind of scheme. But we can have as well a photoelectrocatalytic device, where we now try to heterogenize all of the system into photoanodes and photocathodes to have a separation of the products that we have at the end. And really, up until today, there are really few standalone devices that try to combine all of these chromophoric units, or people trying to develop the multi-electronic redox catalyst and having a little bit of rare examples of having all of these hybrid assemblies. So then this actually converts to low energy efficiencies of the final device at the end. So these are the current challenges that we wanted to look at in Symflux Lumicals. So the idea is, how do we efficiently collect all of the photons? So then should we look at panchromatic absorption of these antenna assemblies? Importantly as well, how do we now transport these useful charges, and not just transport them, but accumulate them on proper places where they are being used for redox catalysis? And third is, we wanted now to understand and control interfaces. As you see, you have all of these building blocks, but they are controlled with electronic relays as well as membranes that position them spatially and temporally in time in order to have the efficient utilization of charge. And lastly, the problem of photostability, because now if you want to look at the final device at the end, this is really what governs the system. So the idea of our Symflux Lumicals is, of course, to answer all of these challenges and looking at all of this interplay of gears between photovoltaic advancements in looking at the design of molecules and materials to do catalysis. And of course, all of this are being fueled as well, or being investigated by spectroscopy in order to see and build mechanisms behind it. So that's what led us to Synflux Lumicals. So it's about synchronizing all of these materials. So from photons to charges to molecules for improved sunlight conversion into fuels and chemicals. The innovative character of the system, again, it's about control. We can think of control as passively looking at how charges are being transferred once from photon absorption to charge utilization. But you could also think of it as how do we actively or dynamically change these fluxes in order to bring or to control the substrates that we have, as well as the products that we want at the end. So the idea is we want to build passively hybrid structures by combining different kinds of materials, from molecules to materials, from inorganic, organic, and biological materials, in order to have a control of space and time on how these charges are being accumulated in certain spaces. And hopefully by understanding this system by transversal modeling and spectroscopy techniques, have an integrated functional device at the end that tries to meet our target. The work package are 3 ways. So we build it in a way that it first have a complementary or an incremental progress. So first looking at light harvesting and charge separation. And this is really led by Fabrice Audebel from Sésame in Nantes and Vincent de Wael spectroscopy in Lille. And then once we look at all of this co-sensitization and organization of assemblies into panchromatic absorption of solar irradiation, we now look at catalysis. How do we use the separated charges to do the catalysis that we want? So this is led by Zachariah Lim in ICMO in Paris-Saclay and Nathaniel Schneider from IPVF as well in Saclay. And finally, once we try to interface both the photon absorption to charge transport, accumulation, and catalysis, we now look at integrated devices, not only using simulated sunlight, but actually performing an actual external sources. And at the end, we have all of these transversal spectroscopic and characterization techniques in order to understand the system, in order to improve in a cycle of optimization of design and testing. Again, these are 19 teams with around 60 months of project and around 92 workforce of people, which is almost 50% permanent and 50% non-permanent people, looking at the expertise of molecular chemistry up until advanced spectroscopy. And of course, we will try to complement our team with the platforms that LUMA already offers, from the ultra-fast techniques from I2BC and IPCMS, in order, and also look at operando techniques in order to test our devices at the end. So this is Synflux Lumicals, and we will nourish you with more results tomorrow, but tonight we will enjoy the cocktail dinner. Okay?
Thank you.
Thank you for this wonderful day. And just one word, so we can go. I mean, all those who have registered for the cocktail, including actually those who were in the waiting list. Everyone in the list could go to the Zamansky Tower, actually right now. And we have to leave this room in something like 10 minutes. So take all your stuff with you and see you at the Zamansky Tower for the cocktail or tomorrow morning. Thank you.